Okay, well, I'm Bobby Lombardi. I want to introduce the team, actually let them introduce themselves. Up next.
Yeah, hi everyone. My name is Prashant. I am part of the ADC team and taking care of the ADCx India initiative.
Hi, everybody. I'm Derek, part of the ADC team, also part of the ADC mentorship program, which I'll speak about in a little bit. Happy to be here. Welcome, everyone. Let's see more of those hearts and those laughing emojis.
I love those.
That's all I see. That's all I see for recognition. Perfect. Thank you. They can hear us.
Thank you, Derek. Thank you, Prashant. Yeah, sorry for that rocky start. Way too many windows open and too early. And that was actually kind of funny because I realized it started doing a loop and adding, going, oh, wow, we have a looper going on too. This is great. Well, welcome everyone. And what makes this possible, I wanted to thank our sponsors. During the event, you'll see some great sponsor cards, and actually you explore, gather, you'll see the logos and banners everywhere. And just want to say thank you because they make all of this possible. You're here today because one of the things we wanted to do is share with the community this essentially the space we've built out for the Audio Developer Conference online. And we realized that the only way to experience the space is to attend an event. And attending those events costs a little bit of money. And we realize it's a barrier for people to explore ADC. And so the thinking was with ADCX, why don't we have an event like this that's open and free to the community? You can explore what we've built out for the Audio Developer Conference. Specifically this year, because we are in Bristol, UK, ADCx Gather has a little bit of the Bristol vibe. So if you're familiar with the city of Bristol, you will recognize many of the cityscapes and the buildings that are built out in the environment. Last year in London, for example, or last year in London, you'd realize we built it out for London. So we try to recreate the spaces we're in. And it was such a wonderful environment that's built not just for the sponsors and the attendees. It's really all about getting together, networking. We wanted to create something that just was not another Zoom conference. We really wanted to inspire attendees to meet each other, collaborate, get excited together. And I'm really excited for everyone to enjoy this day and explore around. So let's just jump in and talk really quickly about just some of the basics of what you'll see today. Certainly there's the schedule, so be aware of what's going on. We have some great talks for you today. In fact, there's one right after this welcoming address, but also there are meetups going on and poster sessions. So the whole point today is that you explore the Gather space and see what's going on. Look around in the Gather space for the schedule, because if you see something that looks like information and says schedule, walk up to it, hit the X key, and that will bring up the schedule. But also in your onboarding email, you'll see that you click the link, the conference.audio.dev schedule-ADCX-gather will take you also to the schedule. So there are many places to see what's going on. And then on the screen, for those watching on YouTube, you will see that the schedule will come up as cards in between sessions. And I should mention that a lot of what I'm talking about on the interactive side of things is not available to attendees today who did not register. So if you did not register ahead of time and you're attending via YouTube, you will be able to see all of the live talks today through YouTube. You just won't be able to interact inside of Gather. So just keep that in mind. If I make a reference to Gather, the YouTube participants will not see that, but you will see all the live talks all day long. So Discord is important to mention if you have registered. Discord is how we use our chat system for the entire ADC and also today for ADCx Gather. You will have to do an onboarding sequence with Discord. It's also in your onboarding email. Basically need you to go to the verified channel and type !I verify to start the process. And then once you're in Discord, I would say get that set up first because you really want to have the chat going on. This is where you would submit a help desk ticket, then go around and explore the Gather Town virtual venue. How do you get to the virtual venue? Again, that's in your onboarding email. Just go over to GatherTown, click that link, and that'll get you around. You will be starting that experience inside of what basically is a getting familiar tutorial room where you get it used to the keys, and then you'll take you inside the venue. If you get lost at any time in the venue or you want to take the tutorial again, just look at the bottom left side of your screen and you would click on your name and it says respawn there. And that would allow you to essentially get back into that room where it was the tutorial. So if you're ever lost, just respawn yourself inside of Gather Town and that will essentially reset your experience. So once you're inside Gather Town, again, for YouTube, this won't be available, but if you're inside the Gather Town environment, go around and explore, because when you do, you'll realize there's other things going on, such as community partners are there with their exhibits. You've got meetups going on, poster sessions, and much more. And to tell you about one of those meetups is Prashant.
Thank you, Bobby. Hi, everyone. Welcome to ADCx Gather. So yeah, I mean, there has been a lot happening this year. Just to give a quick context, earlier this year in January of 2024, we hosted the very first ADCX India along with Music Hack Day India event. So these were basically 3-day long event where the first 2 days were the hackathon and the third day was for talks and panels. And we were really blown away by the activities that were that happened during those 3 days. There were some amazing topics covered in the talks. There were some really good hacks that were done during the hackathon. And what we noticed was that there was like a sense of collaboration that came in. We also came to know that a lot of people got recruited right after that event because people who were looking for talent and people who had those skills kind of met at the same place. And it was like a really good feeling for us to kind of see all of those collaborations happening. This was also like one of the main agenda to even host the event in the first place, because what happens is when a lot of people who are doing, say, activities as a hobby, especially like learning music tech and audio tech, or doing some things in different pockets across India, a lot of times people don't really know that there are others who are also in the same headspace. So bringing them together kind of worked really, really well. And we thought, you know what, if an event can actually bring a change, if an event can actually set up an ecosystem in India, why not just do that again? And so we are excited to inform you that ADCX India, along with Music Hack Day India, will happen again in January of 2025. The dates are 17th to 19th. And you'll be excited to know that some of the people who attended last year are speakers today at ADCx Gather, and some of them are also presenting their posters in the main ADC 24 event. So you really never know how a small event and a small initiative can kind of spark new ideas. So yeah, I hope that you will also meet me in ADCx Gather space today. Just like Bobby said, look out for different buildings. There's actually a fun one, which is named like Urban Tandoor. And there is like, if you go inside the building in the virtual space, you can actually see some links that can take you to the ADCX India webpage. There is also a posters room in Gather where you can also come and hang out. And just in case you are new to Gather and you're looking for somebody, like, for example, you want to get in touch with me, you will also be able to see the list of people who are attending right now. Right-click their name and just select locate. And that way you can just come and have a discussion. So I'm looking forward to having a chat with you. And for more information on how you can stay up to date with what other events are happening through ADC, I'll hand it back to Bobby.
Thank you, Prashant. It's wonderful what you've been doing with ADCX India. I had the pleasure of joining you earlier this year. It was absolutely wonderful. Okay, and also for those who are interested in those talks from ADCX India, on the Audio DevCon YouTube channel, you can indeed see all of the ADCX India talks. So something to mention, if you want to be alerted when these events happen, ADCX India or any other ADCX pop-ups. In fact, we do have a few other ADCXs that will happen in 2025. The best way to learn about them is to subscribe to the ADC newsletter. Once you do, you will hear about things like not just the ADC events, but also the call for papers for those events. Also, we do announcements for our community partners and their events and much more. In fact, there is an initiative that Derek is here to tell us about, which is also something you'd learn about in the newsletter.
That's right. Thank you, Bobby. Thank you, Prashant. Let's see by a show of, I was going to say in Gather, hit your Z button to do some dance moves. But since I only see, I think the responses from YouTube, Let's buy a show of thumbs up. Who's heard of the ADC mentorship program? All right, I saw one. Okay, more than one. Perfect. Oh, awesome. This is great. Wonderful. I'm going to give a quick overview of what it is, and just briefly talk about it, and then we can get back to the fun things. This is fun too, though. What is the ADC mentorship program? It's a way to ensure the health and the vibrancy in the future of the audio software development community. That's simply it. We pair mentors with mentees based upon their experiences and their backgrounds and what they're kind of looking to achieve, as far as guidance and as far as learning. That's really all it's about. There are those people at trade shows where you see them and they're veterans in the industry. They know everyone, they've been doing this for a long time. And then there are those people who are just getting started, or people who are just thinking about getting started in this industry. And so when you take a look at that, you see an opportunity. And really, that's what this ADC mentorship program is all about: connecting people and helping them feel guided and welcome, making them feel welcome in this community. The only way that we're going to grow this community is if people feel like they belong. And that's what this is really about. We've heard some amazing stories about experiences from the mentors and the mentees about what they've gotten out of this program. So I'm very, very excited about it. Right now, we're in our second session. So this is, I guess, the second annual ADC mentorship program. It happens once a year. We pair you up around the middle of the year, send out an email, and we kind of recommend 3 1-hour-long Zoom calls or Google Meet or whatever you decide to use, to make sure you kind of get a little bit from your mentor, and so that the mentor can guide the mentee as far as what they're looking to achieve, what they're looking to learn. It's really been an incredible program, and we're looking to continue it. Right now, there's over 200 mentors and mentees matched up, which is fantastic. This is a number that has grown since the previous year, but we need your help. Each year, we have to unfortunately send out some sad emails that say, sorry, we couldn't pair you because we don't have enough mentors. We need more mentors. So if you're in this industry, if you're giving a talk, if you have been at this for several years and you feel like you've learned something that you can give back, please sign up. And the way that you'll be notified about how to sign up to be a mentor or to sign up to be a mentee is to sign up for the newsletter. We keep circling back to that to be notified of things, because that's how you're going to be notified. In 2025, we're going to have another session as well. So please sign up to the newsletter to be notified when that does open up. I really want to thank all of the mentors and mentees who have contributed to this program. It's really quite wonderful, and I hope everyone has an opportunity to participate. So if you're in that mentor boat, please sign up, and mentees, please sign up as well. We want you there. So thank you very much. By a show of thumbs or hearts, who's going to sign up to the newsletter so they can be notified? All right. I like it. All right. I'm going to pass it back to you, Bobby. Thank you, everyone.
Thank you. You've done a wonderful job with that mentorship program, and it's so just heartwarming to see how many more folks showed up in your second iteration, and I can't wait for the third next year. So absolutely wonderful, and great to see mentees joining us as speakers this year at ADCX and ADC 24. Speaking of ADC 24, that is indeed in just over a week. So good. If you joined us a little late, just to mention, the whole purpose of ADCx Gather was to showcase what we've built out here for the virtual experience of ADC 24. So the whole Bristol, UK theme is based on the event that is starting on November 11th. There are still just a few in-person tickets available for ADC 24, and there are certainly online tickets as well. With online tickets, you will have access to all of the talks, 6 of 8 of the workshops, and including all the multiple track talks too. And if you attend online, we also record all the talks, and you'll have access to an archive for on-demand viewing during the conference and also for a limited time after the conference. So for those experiencing Gather today, just note that you would be able to do this again in just over a week with a larger audience and access to about 8 times the number of talks that you will see today. So absolutely wonderful. None of this would have been possible without our sponsors, so I'd be remiss not to mention them. Thank you, sponsors. You'll see their cards coming up and throughout the venue. Also wanted to just say, if you are interested not only in the newsletter, please follow us on social. All of our social channels are at Audio Dev Con. And today, if you're having fun, please screenshot what you're doing inside of Gather. Make sure you hit that Z button, do a little dance, and then there's the special F button, which throws some confetti. So I imagine there's going to be a lot of confetti to clean up after this event, but it happens. Luckily, it's digital, all good, but keep making confetti. So yeah, please post to #AudioDevCon, and we'd love to see you out there and interact with you. Most important is have fun. The whole purpose of today is to explore, enjoy, ask questions. We'll be answering questions on the YouTube stream, but also inside of Discord and Gather. So let's start chatting up. If you see anything, though, that is getting in the way of having fun today, we do take our code of conduct very seriously. Please go to Discord and open up a ticket on the help desk, or send us an email at conduct@audio.dev. We want to make this a very safe and fun space for absolutely everyone today. So wrapping up, go ahead and hit those Z keys if you're on Gather, do a little dance. We are going to get ready for our first speaker. That's Christopher Clarke coming up in just a few minutes. But I wanted to share my thanks to Prashant, to Derek, and to the rest of the ADC team that's on watching today. You are the reason why this event happens. There is no event without an ADC team. A lot happens behind the scenes, from everything from call for papers, reviewing papers, getting the schedule together, building this incredible environment and Gather, everything that needs to be done to get the on-site location going. The list goes on and on. We love you, volunteers. We love you, team. We love our sponsors. Go have fun. Great to see everybody. And I look forward to meeting some folks in Gather and on YouTube right now.
And next up, we have Christopher Clarke, who is going to present a 18-minute session. Chris, if you'd like to turn on your webcam and your screen share, that would be fantastic.
Yeah, just getting sorted right now. I've just shared my screen. Is everything okay?
Looking good, and there we are.
All right. Just starting my timer. And okay, hi everybody. Thank you so much for coming to watch my talk. I'm extremely grateful to be able to present at ADCx Gather 2024. And I would just like to give my thanks to the organizing parties involved for helping me along the way. My name is Christopher Clarke, and I want to introduce myself before I begin my presentation. After graduating with my PhD, specializing in AI and DSP, I joined the company in the DAW space as a DSP/software engineer, and I've been enjoying my time since. I've also served in multiple studios as a recording engineer as well as a mastering engineer, and I use this information to help inform my processes for guiding my research. So I guess without further ado, let's get started. So as a preface to this slide, my introduction slide, I would like to mention that this sort of strictly applies to CPU-based real-time audio neural networks, where latency between CPU and GPU is too much for real-time audio deadlines. I would also like to make the assumption that the model designer is not aware of any particular architectural information of the intended model to be trained. In that case, we first begin by clarifying some difficulties before I introduce what I'm going to present. And certainly I faced these difficulties in the past. As with the case presented, in a lot of situations, typically the parameter count of the model is either decided purely based on intuition or bounded by the computational resources available. And in these cases, it's usually left undetermined whether or not there's an optimum parameter count for the given problem. If time warrants it, heuristic or heuristic optimization methods are often employed. And this is not to say that heuristic methods are not good. I'll get to this in a later slide. The point here is to acknowledge that there's often not only no time, but also no ability to determine optimal resource usage, and such as across multiple platforms or varying computational situations. As with the theme of my previous talks, I urge everybody to try and tap into the research performed in the past instead of trying to take on new problems with white knuckles. Originally, I had planned for this to be a 50-minute presentation, but I had to cut it down due to the current time format. I'll address what I've removed from this talk at the end. Going through the list on the screen, firstly, this solution requires some effort on the part of the model designer, as it is a predicate to the model design process. In this talk, we concentrate solely on regression problems, where you are trying to invoke the universal approximation theorem to fit your model to an underlying discoverable function. So I will not be addressing this problem through the probably approximately correct framework, but we will make reference to it. To demonstrate the method, we'll first assume that your model is of the nature where, like shown in the diagram, it's a singular black box model which takes one input and provides one output. We assume batching to be arbitrary here, but in most cases, because of stateful designs or memory-based side effects from components like capacitors and inductors require state calculations, you might be stuck with processing one sample anyway. Later, we show some arbitrary nonlinear transfer function to provide some way to determine optimal parameter count for that. I hope you're able to abstract away from this example and not harp on the fact that it's an arbitrary function. Of course, depending on the complexity of your model, your results may vary. Some anecdotal evidence from a heuristic method like grid search, in a simple case where you survey a grid of varying neural network sizes. You're able to find some optimum size for your model, given some initialization weights and hyperparameters. So if you want to run the experiment, please feel free to try it out, either by writing it yourself or with the GitHub repo that I will attach in the Discord later on. So performing this grid search for a linear or dense ReLU network to learn a 10H function, I searched across widths and depths of 50. So that's 2,500 models to train and evaluate. So realistically, you wouldn't do that. You would do in like multiples of 4, right? And or something other than that to save some time. Also, I guess if you consider the lottery ticket hypothesis, you would also randomize the initialization weights and biases in the real world scenario. So I performed one grid search with 2 different dataset sizes. As you can see, the time scales very quickly. And considering a lot of audio dataset sizes nowadays, they're quite huge. So 100,000 data points is kind of on a small side. So which begs the question, could we limit this search to a much smaller range? And if we could find that point of some optimal parameter count, we could technically search combinatorially within that range. And before I speak of this method I'm about to talk about, I want to draw some inspiration from algorithmic alignment. I know the context was originally referring to graph neural networks, but we can abstract the logic underpinning the current problem at hand. I won't be breaking this and further concepts down too much due to time constraints, and rather I'll attempt to summarize their importance in the context of this presentation. So algorithmic alignment tells us that a particular neural network's alignment implies that the network not only matches the functional outputs, but for different learning algorithms A, we can target certain errors, epsilon, and with certain confidence delta. This is an important point and will become clearer later on. But for now, at least extrapolating from here, the literature tells us that approximating a target function with a given error leads to a given amount of algorithmic alignment. So to give a more concrete example, here we have a plot of a transfer function in blue and the orange plot to show how far it deviates from linearity. However, the main point is, upon first glance, I think many people would agree with me that it's quite hard to intuit what sizes are necessary for this model. As a result of that, a model designer might, and usually will, overestimate the parameter count necessary for emulation. And so we have our problem statement. We have a function that we want to model, and this function is bound within an interval, as is usually the case for recorded audio. We want to target a specified approximation error. For an example, you might want to use some dBu and convert that to a floating point value. So maybe like minus 60 dBu is 0.00 something, right? So that's your desired error. With this information, we then aim to find a neural network's architecture parameter count that will allow us to approximate this function with our given error. I believe many of us have come across the field of analysis in our work. So let's use that as our way into solving this problem. So let's try and define function complexity. If you're approaching this from the machine learning or AI framework, these function complexity measures are like features of a function that we can express to our model or method to provide some analytically based result. Here I show 3 ways you could do that, but due to time constraint, I will only describe the one we choose. And let's say moving forward, we choose the maximum bound second derivative. At the bottom right-hand corner, the maximum bounded second derivative is related to the curvature of the function over the interval. If a function's second derivative is bounded, we can define a constant m representing the maximum of these absolute values. These definitions are examples of how one can determine some level of function complexity. There are other methods like complexity classes, etc. But the idea is to define these features to some known complexity of your target function. An example of this would be if a function is non-linear time invariant, you would probably also want to consider that as a feature of your function complexity and come up with some analysis of the function for that aspect. Just to uphold the rigor, I define some metric to score a given function based on some chosen function complexity features. Briefly talking through this, a given error complexity C of a given function f with a defined target error epsilon is the lowest integer by which the set of function partitions produce epsilon from the given input x. This is not a new notion and was first introduced by Kolmogorov. I've only just defined it slightly differently in order to fit this context. With a bit of analysis and linear approximation theory, we can show that our desired error can be expressed in terms of the max bounded second derivative m and the step size h. This provides us a way to control the error by adjusting h. This shows, and rightly so, that for a greater m value, that we need a smaller step size leading to more partitions, which lines up with our current understanding of neural networks in the next slide. In the essence of time, here are some examples of literature relating to the leading the partitions to the parameter count of a dense ReLU network. I'll leave this to your further reading, and I'll be happy to answer questions in the Discord channel for this talk. I've also prepared a Python file in the repo for this talk. Feel free to use it. I'll post a link in the Discord as well. If we assume the number of partitions is linearly proportional to the number of parameters in the network required, in this case, I assume a fudge factor of 1.3 to account for a partition overlap and other such overheads, with my target function being y equals 10h of 2x. Again, to reiterate, this function is arbitrary, and in reality, you would probably not need to use a neural network to learn such a function. But in this case, I've input those parameters being my input and my output set, as well as some desired error, and calculated the number of parameters should be about 10,000, as indicated here. So if you plot the amount of parameters against the width and depth of a neural network, you can get a quote-unquote topographical view of the landscape. So this would give you the combinations of different parameter counts per width and depth of a neural network. So for example, if you know your target function at your desired error can be modeled with 1,000 parameters, you would then search within the set of layers and widths that can provide neural networks with approximately 1,000 parameters. To further prove my point, I did a grid search for y equals 10h of 2x across 50 neural network widths and 50 neural network depths, keeping the initialization weights and biases the same, using the same random seed. On the right, we see that the best performing network for a desired error of 1e minus 7 is 6 layers with a width of 44. If we overlay our parameter count, this tells us that we are indeed within the range of 10,000 parameters, being somewhere hidden layers and somewhere here, right? There was this value for this score on the previous slide. In reality, some functions have equally performing architectures, and one will need a way to reconcile which size is indeed the most viable and performant for the given use case. In this sense, we can propose a satisficing equation to further pare down which architectures we should choose. In this case, I've arbitrarily chosen to satisfy the AVX SIMD register holding 4 doubles, and this means we can optimize around that. You can and should choose principles that best fit your deployment or product, which will allow you to best maximize your resources. Lastly, I wanted to introduce this paradigm that has helped me when developing AI/ML models. I got this from Paul Lessard, I think it is, and it goes something along the lines of that we should approach our data sets and data like writing code, where the neural network is the compiler and the output program is our output function. So it is not a given that a large compiler will produce a reasonably performant program. The same way one should not expect a large neural network to produce a reasonably resolved function. I blindly demonstrate this with the target function of y equals tan h of 2x with only changes in the size of the data sets. You can see that the same target area of architecture still maintain their low losses compared to other similarly sized architectures in the right plot. I strongly emphasize that this is, however, not to say in any way that dataset size is not important. It is more to say that the flaw in this method is that it assumes an infinitely sized dataset, and you can only reach the desired error at the desired parameter count with an infinitely large dataset. So you need to account for that. This shows the satisficing equations results at optimizing for the lowest score and the lowest lost. We do not get an increasing or decreasing pattern in the neural network architectures, and rightfully so. In conclusion, since heuristic methods take time, we should account for this and other given constraints around that. I showed that the function complexity can be used as a form of feature analysis to determine neural network architecture in terms of parameter count. We defined a metric for this feature, and I showed how the method was used to derive this parameter count. Using a real-world, albeit arbitrary, example, we went through how the results can be scored based on deployment and product needs. Lastly, there is so much more I wanted to discuss that I had to remove from the slides. I thought it might be good to describe some of these future possibilities. Perhaps I can speak again next time in a part 2 of sorts. The next step to this would be to show you that you can reduce function complexity by pre-processing the input data with known non-linearities, and that we can score these neural network architectures based on real-world deployment data. And on top of that, perform the satisficing equations on top of this real-world deployment data. I'd also like to say it would be possible to extend this to non-memoryless problems, and that I had initially prepared some trivial methods into looking into that for this presentation. Lastly, for future work, I would like to improve the bounds estimation for focusing on specific circuit analysis methods, something like using the complexity of a given state space analysis or vector space to derive the bound for a given neural network architecture, like a CNN or an LSTM. Thank you. I really appreciate that you took the time to watch my presentation. Please feel free to ask me any questions in the Discord server. Unfortunately, there will be no Q&A, so we can try and meet in Gather Town if you prefer that. I'm happy to answer any questions. Again, saying thank you to all the parties involved, and thank you very much for letting me speak here. I guess it's on to the next speaker.
Okay, and so our next presenter is ready, and so if you'd like to turn on your screen share and your webcam, and off you go.
Absolutely, Jim. Just give me one moment as I find my window.
There we go, just need your screen share.
Yes. Give me just a second. Somehow my windows have disappeared in the ether. Okay. And I'll quickly share.
There we go, all working. Off you go. Thank you.
Okay. Well, Thank you for joining. I feel like we're joining from all parts of the world. So good morning if it's too early, good afternoon if you're in London, and good evening if you're on the other side of the planet. My name is Anurag, and I will be talking about building a simple, modern, and collaborative DAW for producers of all levels. And I know that's a meaty title, but I'm sure as we talk, we will break it down. So let me just start with something that is a pretty popular talk on ADC. David Rowland, who is the CTO of Traction, had previously talked about why you shouldn't write a DAW. And his entire presentation is kind of themed around this quote by Lex, which goes that if you really think about it, the economic incentives aren't there. And that it takes so long to develop a DAW that there is no innovation left that people can even imagine. But then today we don't live in that world. Even a year ago, we have GitHub Copilot, we have Cursor, we have Devin, and we even have Traction's own engine to really get us going and thinking about innovation. So really this whole presentation starts where David ended, which is innovation. And I'm just not going to give you an abstract, inspiring quote about innovation. I'm actually going to try and break down innovation into 3 pillars, which is simple, modern, and collaborative. And for everybody. And if you're someone who likes more prescriptive active voicing, then it's about driving simplicity, adopting modern standards, and enabling collaboration for producers of all levels. So let's just kick it off. Let's talk about simplicity and why that is important for a DAW. So very recently, Dylan Field, the CEO of Figma, had talked about in the config of 2024, where he talked about how people are kind of overwhelmed with the complexity of Figma. And he quoted this tweet where someone wanted them to remove features and to add more, which is why the focus of this new evolution of Figma was primarily about reducing complexity and other big feature updates, which really tells us that simplicity is the ultimate sophistication. It's not that Figma decided to strip away features. They decided to reduce the complexity. And it happened historically where whenever there are very complex status quo that are more attributing towards professionals, it is challenged and disrupted by another product which kind of reduces the complexity and enables more and more people to use it. We had Canva for Photoshop, we had Figma for InVision, we had Squarespace and Wix for website development, which really begs the question of what is this new DAW that could replace or at least complement the existing Pro tools that we have around, which kind of just looks pretty daunting for a new user. In fact, we went and researched about on Reddit and in person about people who are kind of using the DAW or have seen how a DAW is used and what their complaints were. And an overwhelming number of features was the top complaint through and through. So how do we go about reducing complexity? There are a few arguments that I have. The first one is against skeuomorphism. And if you've ever opened a DAW, you would have seen something that is like this. And it makes sense. Skeuomorphism is a term which denotes that people bring in or are motivated to bring in real world looks into the digital equivalents of them. And analog compressors and pedals are one of those. And it makes sense because it offers you tactile feedback. You kind of you have the same memory from when you've used it. There's nostalgia associated with it. The problem really lies in that the new wave of veteran producers haven't seen those analog equipment. And what they really crave is something that is more intuitive and something that is more speaking to their muscle memory from other products that they use outside of creative software or outside of music production. Another argument I have is, or another suggestion I have is making a product user flow evolutionary. One of the apps that I really like using and advocate for is Family. It's a crypto wallet manager. And one of the design philosophies is about how they evolve their experiences instead of just showing them all at once. And I really like their idea about making a product accessible to newcomers without sacrificing depth or power for experienced users. The final suggestion here is breathing room. We're just evolutionary. Like we have anxiety from looking at density, looking at sharp edges. And DAWs infamously are full of those. There are grid lines, there are small text, there is density. And there's a huge kind of push towards making it more breathable and friendly. With that, let's move on to modern standards. And this is going to be a lot. So I'm going to try pacing myself. But let's just kick it off with this classic phenomena called the innovator's dilemma. What it really is, it talks about how when incumbents have reached a stage of maturity, they kind of plateau in their innovation. And there is this fear of change, fear of losing your customers that prevents them from making big bets. And that's where newcomers kind of just like come in with probably a smaller user base, which is more niche, or a low-cost offering, which tries to challenge the status quo. And eventually they pick up while the incumbents kind of collapse because of lack of innovation. And the examples are quite many. Kodak, who couldn't get out a digital camera thing that Canon kind of invented. You have Blockbuster, who fell prey to Netflix's way of broadcast or having streaming movies. You have Nokia, which kind of did not catch up to the way Apple was releasing phones, and the Toys R Us, which fell because of Amazon. And the usual suggestions around fighting innovators' dilemma is around how do you go from a short-term focus to a long-term vision? How do you have more bravery in kind of moving away from what has made you prevalent in the user's mind and start again? Challenging complexity by partnerships and figuring out other people who are solving it. And being really a customer fanatic, that's, I think, a Bezos term, to learn more and more about how users are using your products. Which really brings us to the elephant in the room. And a lot of talks in ADCX and ADC are around AI. And my call to the audience here is that AI is no longer just a feature. It's actually a standard. It affects the way you architect your entire product. And the other argument I have here is that the only job that AI has is to maximize your creative headspace. So let's break it down. So if you look at how AI adoption has occurred in the world, in just business suite of software, we have 72% who are already using AI in their workflows. You have consumer tech, where most people have really adopted towards a large variety of AI products. And then you have music tech as well, where 2/3 have at least used AI offerings, and 1/3 have actually benefited from using AI. So people are getting more and more used to having a product be more fluid, more responsive, and more inspiring. And to be AI native is key, and those do affect how you start from the ground up. We actually, again, had a research where we read through thousands of comments to understand what is really the challenge in the creative process when it comes to music production. And what came out very loud and clear is that creativity is something that is an inspiration problem and a perfectionism problem, which narrowed down is a starting and a stopping problem. So AI here is the way you solve it is usually in a way where it maximizes creative headspace. If you offer too much control, that can be overwhelming. And if you offer too much convenience, that can remove the creative agency. So it's really the challenge for AI to make that come in the middle. Which is why you'll see a lot of movement from traditional DAWs, which are trying to take more steps towards introducing more convenience in the workflows. And then you have the more adventurous AI companies like Sin and Udio trying to come in the middle of giving more creative agency and having more control over the process. What really will come out as we move more and more closer to the middle is that the producers, brand, and their taste really come through in their productions, and they're able to get rid of the algorithmic processes. And there are a lot of really cool companies coming out in this space. Obviously, it would fill the entire slide if I mentioned all of them, but some of them that I really like is more Newtone. There is Ripex, there is Music Effects from Google, there's Ace Studio. So they're doing a really lot of cool stuff that kind of really expands your creative headspace. There are a lot of challenges, and again, it's a very deep topic, so I'm not going to talk a lot about it, but data obviously is a huge challenge when it comes to building your own AI pipelines. And there's I read somewhere where a third of the investment for AI-based companies, and especially in the creative space, is really going into licensing fees and collecting data. So one of the ways to solve this is by tagging data and creating synthetic data for being able to build those AI pipelines. Or you could also just use existing models to power your first few products, and then eventually lean more into the differentiating products. There's also the UX problem, which is how do you balance control with convenience? Then the next one is cloud. 2024, and we still have a cloud native issue with DAWs. And again, just to clarify, cloud native is not browser based. What it really requires or what it really provides is a seamless transition between desktop, mobile, and tablet. You get offline support. You have low-end devices finally being able to create music. But it's not easy, which is why there is still a bit of a fragmentation when it comes to what is cloud native and what is not. Obviously, there's huge data synchronization issues, and obviously it is yet to be fully explored, but with real-time databases with version control and bandwidth management, you can sort of compete with that problem. And then there is the latency and real-time processing. Again, this is not an easy problem, and you can kind of now think about building more client-side processing with web audio plugins, with web audio modules, where you can start to process a lot of stuff in the client and not send everything to the server. Then you have plugin compatibility and new standards that are coming up, like Clap, that kind of solve that problem where you wouldn't necessarily have the same plugin on both sides of the client and the server. But there's a lot of other problems. And since we have a lot to uncover, I'm going to keep pushing us through to more and more things in the modern standards, which is interoperability. Now, which really goes to the philosophy that I have learned through my experiences, which is we should not have cliffs when it comes to having a product experience. They use a term like spending hours on your product and then reaching a cliff. And how do you solve for that? A lot of the products today solve it by stem exports, where you can just have all your stems being exported. But then the other cleaner way is to just have files that can be exported to new DAWs so that you can incrementally add more features without worrying about users having a cliff problem. And the DAW project is really something that is helping towards that. And there are also experimental repositories like DAWvert, which I have a huge respect for, which actually understands binaries of each DAW and helps us build interoperability from the ground up. Finally, enabling collaboration. And how do we think about that? My biggest argument here is that collaboration is actually table stakes, and there is some data to back it up. If you look at how digital collaborative tools have emerged, they got a lot of adoption through the years from 2017 to 2020. There was a huge curve in people wanting more and more collaborative. Figma is a huge success story, and all of them kind of got into the whole bandwagon. But also, if you look at the revenue, it's kind of falling down based on just collaboration, which tells us that collaboration is more integral. It's just something that needs to be there. It's no longer a differentiation, which kind of reminds us that DAWs are still kind of struggling with real-time collaboration because despite all of these benefits of collaboration, that you get geographical freedom and you can resource optimize with studios and time, and then you have the synergy between two different musicians and producers from different parts of the earth being able to collaborate, it's not that easy. You have the same problems as cloud native. You have file format issues. You have different plugins at different clients, and some of them can be proprietary, and having to sync all of that is hard. You have timing issues if you have playback on both sides. And sometimes you just have hardware-specific features that are really hard to bring over and have a collaborative experience that users expect from other products like Figma. But there is still a lot of really good work happening here. BandLab and Avid both have native collaborative features. And on the right side, you have able to link in Cubase, VST Connect, which kind of solve for more specific recording problems, either on the local network or remotely. And the other thing is that you don't have to build like a whole real-time communication platform yourself. There are products like LiveBlocks and Ably that kind of give you that initial framework to build on top of. In closing, I really want us to be able to think beyond what we have already seen. Innovation is a continuous cycle, and the only way to think about the future, the only way to predict the future is to create it. This is an often used quote, but I really stand by it. And I think we've only scratched the surface of what can be a next generation DAW. I'm a founder of Ripple, where we're this very small plug, but we're kind of also solving similar problems and have the same idea of first principles and seeing where we can take this experience. And you can find me. I'll be in the poster session in Gathertown. I'll also be available on Discord to answer questions. I'll be coming to Bristol, so you can find me there, and I'm easily available on the internet. So with that, thank you.
All right, so next up we have Luigi, who will be presenting Mind Matched Audio. So Luigi, if you'd like to turn your camera and microphone on, please, and start your screen share.
Sure. Hello. And let's share. Whew, okay.
And remember to share your sound.
Yes, I think I did it. And share. Can you all see the screen? Yep.
Coming through great. Thank you.
All good. So I'm ready to go.
Off you go. Perfect.
So hello, everybody. My name is Luigi, and I am the founder of Oikla, a tech company that specializes in psychoacoustic software that aim to increase the perception of sound without making it dangerous for your hearing. But anyway, today I'm about to present to you a project of mine that I worked back in like a long time ago, 2015. It's a project that I really enjoyed working on, and I think it's time to showcase it, and I think the time is ripe. So what I'm about to present to you, here we go, is Mind Match Audio, basically revolutionizing reading experience through real-time sound and synchronization. So I have a little confession to make. Basically, I started this project because I used to hate reading, and I loved sound and music. So that passion led me to wonder, what if we could bring sound into the reading experience to make it more immersive and enjoyable for people like me? Imagine stepping into a story, not just through words on a page, but with an experience that immerses you in sound in real time. So basically, the concept is to make sure that when you read, sound is synchronized based on your imagination. And so let's look at why reading as a medium needs this kind of transformation. Whew. All right, so unlike movies or video games, in reading, the visual is hidden within the reader's imagination, which makes it incredibly challenging to synchronize sound with what the reader is imagining. Our goal is to bring the hidden visuals to life with sound. And that's why syncing the audio is so important. We weren't just aligning sound with text on a screen, but with the experience unfolding in the reader's mind. So a century ago, the movie industry changed completely by adding the sound to visual, creating the immersive experience we enjoy today. But reading has stayed the same. And I'm not talking about the audio book. That's a totally different thing. The reading experience, as we know so far, it's silent. And when we read, we rely entirely on our imagination, which is not necessarily bad at all. It's just that it's in our mind. So what we see and what we hear stays basically, we create it ourselves. And we create the atmosphere and depth. But why has reading stayed silent? And what does that cost us in terms of engagement and emotion? Today, I would like to show you how we can change that. So the project that we worked on rely on basically using eye tracking technology and real-time sound. So basically what we did is we used eye tracking to map where the reader is looking as they move through the text, but just matching sound to a location on a screen isn't enough. The real breakthrough is matching the audio to what the reader is imagining, and that's where the real challenge is. What you read, it takes time for your brain to process. You land your eyes on a word, understand it, and then picture it in your mind. Our technology takes this delay into account using smart algorithms that basically predicts. We have algorithms that understands the word difficulty, word frequency, context of what you're reading, and based on all of these variables, there are slight delays that are applied when you land on a specific word. Because the problem is, if we trigger a word a little too soon or a little too later, we might break the magic that synchronization will bring. When we watch a movie or when we play a video game, sound is perfectly synchronized with what you're saying, which is, in a way, a pretty straightforward way of synchronizing what we see with what we hear, right? Basically, when we work in post-production and we work on sound design, it's fairly simple to align a frame with sound. But when it comes to the reading experience, it's much more challenging because we have no reference as to when we need to play a specific sound in order to be matched with a specific imagination. So our technology, the most challenging part was to basically make sure that we could play the right sound at the right moment, so that the imagination would be the reading experience wouldn't be the sound wouldn't distract the reading experience at all. So in this way, the audio syncs perfectly with what the reader is imagining, not just where they're looking. For example, if the reading is about a storm, you'll hear the wind and distant thunder at exactly the right moment, making the scene feel real. Anyway, I also want to tell you that the talk is about telling you a little bit about this project, and unfortunately 17 minutes are not enough to explain all the work that has been done in this project, as it will take me more time to explain a bunch of things that probably are going to be a bit boring, because we're talking about the reading, how we read and how the brain processes reading, how the eyes moves, and so on, which are a bunch of challenges that we had to overcome in order to make sure that this synchronization happens. Because to trigger sound based on a location on the screen is fairly trivial. You have X, Y, and then if the eye strike this X and Y position, you trigger a sound. And I must admit that excellent that, and it required us to understand reading patterns and much more than that. That's all. So anyway, the next slide is about the demo. I thought that perhaps the best way for you to understand what we did is for you to actually see what we made in the first place. So I'll walk you through that. So here we go, we have a demo. And before we get into the recorded demo, let me set some expectations. You'll see how the system triggers different sound based on my eye movements. This is obviously a pre-recorded demo, so I'm not gonna read it live. And remember, the audio is synced with my gaze, not yours, as you watch. You also see a transparent circle on the screen showing where my gaze is in real time. So you'll see basically as I read through, you'll see basically a circle that shows where I'm looking at. You can try to follow it if you want, and I encourage you to do it. Even though my reading pace and obviously is going to be different than yours and so on. But I still encourage you to try and follow so that you can see how audio is triggered and how the soundscape change through the story and so on. And yeah, just focus on how smoothly the sound fits with the reading. This is what makes this reading experience immersive, I would say. Okay, so let's take a look. The first thing I want to show you is a couple of things. This is definitely the way we designed this reading experience is very different compared to your traditional reading of stories, and there are specific reasons as to why we designed it this way. Anyway, let's dive in really quick. So the first thing is as soon as we start reading, we only are presented with 2 lines, all right, the first and the second. So as I read through the story, you can see this little circle there, right? As soon as I get to the end of the first line and I am going to reach to the second line, right? The third line appears. Let me walk you through. As soon as I get to the second one and I go from the second to the third, what happens? The fourth one takes place to what it was the first line. Okay, and when I finish the third line here, and I go to the fourth one, the fifth one is generated instead of the second. When I get to the end of the fourth and I go to the fifth, the sixth one is generated. And you might ask, why would you have such system that is so distracting? And the reality is that we tested it against 100 people. And or you probably don't know, but basically when you're moving your eyes with quick saccades or long saccades, this is the term to say the eye movement. When you move your eyes, you actually don't see what happens. So you go blind for like a very short amount of time. And so because you go essentially blind between this spot and this spot, when the line changes, you don't see the change happening. And this allows us to basically allow you to read without having to click to scroll to the next page or getting distracted from the experience itself. This way, 3 lines, we can just keep going in rotation. So if I keep playing it, when I get to the fifth, the sixth, I get to the sixth, and when I get to the sixth, the seventh is already generated. So it's basically going 1, 2, 3, and then back on. Anyway, this is just to show you how you should follow up, and if you know, I hope this makes any sense to you. But the idea was that I will be able to read with an eye tracking that looks at my eyes, understand what I'm reading, and basically auto scrolls the next sentence for me ahead. And based on where I'm reading, certain sounds are instantaneous and others are more soundscape and they're more different. Anyway, let's play it, and I'll let you guys hear it. I hope you wear headphones. There we go. Play. I think that that's enough for as a demo. So as you can see, yeah, it just keeps on going, but I think it's too long to continue. So let's move on to the next slide. So we tested this reading experience with 100 people, and we found that 93% of all participants found that reading like this enhanced their experience. So that's obviously, that was an amazing finding for us. And another test that we did was that it's not just about using sound in a clever way to match the user's imagination and enhance the reading experience for the reader. We also found that by triggering sound at the right time actually makes the gaze duration shorter. What it means is that basically, if I were to play the thunder sound when you're about to read the word thunder, if you read the word without sound, it will take you basically longer. And if I play this, and if you were to read the word thunder with the sound, the word thunder with the sound, the thunder sound, it would take 63% less for you to actually read that word. And what that means is that what we think, we think that basically the reason why that happened is because sound is processed much faster in our brain than reading. So for you to read the word thunder and comprehending and understanding and picturing it in your mind takes longer than just play the thunder sound in your, just play it, as that will unconsciously give you the meaning and understanding of what is happening. You don't need to process it, it's just much faster. So if I play the thunder sound at the same time, at the right time, as you're reading the word thunder, because you're hearing the sound and you're reading the first part of the word, your brain understands immediately what is going on and requires less time to process that word. So in a nutshell, basically placing sounds at the right time not only makes the reading experience enhances and provides further tool to basically storytelling, because for example, you don't have to write that it's raining. You can just write about what is happening, and the sound of the rain can provide the context of what is happening. Or perhaps the reverb of a church, right, could perhaps provide how big the space is without the writer writing how big the space was. And again, I'm not trying to say that writer needs to change the way they're writing or there's anything wrong with the old system. I am just interested and excited to see how we can use sound cleverly by matching it with the reader's imagination to enhance the reading experience and to provide new tools as storytelling. And the reason why I kept this project for a long time in my bedroom, as this was my dissertation for university, was because 10 years ago, this wasn't feasible. But today with eye tracking devices becoming more and more small, and the fact that there are devices now like we can see the Apple Vision Pro and the Quest coming out. I think these kind of applications are way more feasible these days than they used to be. So moving forward, what we think is that we could basically use AI to basically generate sound based on the listener, on the text you're reading. So the audio is generated based on the text, and we can further use machine learning and AI to further understand even better how to personalize the reading experience with this. So I just see a message on Discord, so that's very nice. So just keep in mind that in order to make this happen, I had to basically build a small tailored DAW only for for this reading experience, because there's no such thing as the reading experience. They're not tools meant to basically match the reading experience with sound. So I had to basically create the whole a DAW just for this particular reading experience. So it was an amazing process back in 2016 to basically read and get the sound and get this this interesting concept, at least to me. And I am very happy that I made it. It took 6 months of hard work back then, but yeah, awesome. So I think this is using AI to tailor the sound and tailor the experience to the reader even more, because at the moment is made with algorithms that basically makes a bunch of calculation based on how difficult the word you're reading, how long it is, how frequent it is in the English vocabulary, and a bunch of other variables. Then we have delays to trigger sound. Anyway, I guess the last slide is to say a big thank you. This is not my main. I run 2 companies, and this is more like my little side love that I used to do. So I still would like to keep it, to move it forward, but differently than what I did with my other companies. So if any one of you is interested and want to ask me questions, or wants to, collaborate and make this, even further, I'm sure that there will be people interested in trying this. So thank you very much for your time. It's a bit different to be talking in front of a screen. I wish I could be seeing you and I could interact with you, but this is nevertheless great. I hope my talk wasn't boring or not too technical as the others. It would be too long to explain the whole thing, but thank you very much. And enjoy the rest of the day. Take care.
Okay, thank you very much. So we've ended slightly earlier than scheduled, so we're just going to go to a quick break now. Content will continue here at 2:50, so 14:50 UTC. Otherwise, if you're registered to attend the event and have access to the virtual venue, please head over there to join the poster session that will be starting at 14:20 UTC. Great, so we'll be back with content here to the stream with talks at 14:50, 10 to 3 UTC. Thank you very much. See you again soon. Hello, hello, hello. We are about to get started with our second block of talks. So our next presenter is going to be Allwin Williams. However, Allwin was originally planning to present live. However, due to various circumstances, particularly a firework display now happening immediately outside of his window, he's actually decided to provide a pre-recorded talk. However, Allwin is here, so Allwin, if you just want to turn on and say hi.
Hi, so this talk is mostly around me as a designer trying to learn experimental music and experimenting new interfaces. It's a little loud here with the fireworks and firecrackers around. So I've sent a pre-recorded video. I think that will be played. I'll be active in Discord as per the exact.
Perfect, thank you. So Alwyn will be on Discord and in the YouTube chat to respond to you if you want to leave your questions there, but otherwise we're going to roll the video now.
Hello, I am Alvin Williams, and I'm going to be talking about playful interfaces for experimental music. A bit about me. My background is in interaction design, and I'm currently consulting with a science center for their exhibits and installations around music and sounds. I am also a visiting faculty at design schools for tangible interfaces and physical prototyping courses. The inspiration for this talk mainly comes from me trying to learn audio synthesis and explore experimental music. I'll start with an example. Let's take these three doors. Each of them have a different type of handle. The first one has a knob, the second one has a bar, and the third one has a plate. Each of them will allow us to open the door in different ways. The first one allows us to open the door by turning. The second one might allow us to open the door by pushing or pulling. The last one would allow us to push the door to open. With this, I would like to introduce you to three design concepts: affordance, signifier, and feedback. Affordance is what the design allows the user to do. A handle that allows user to open the door by any action is an affordance that the design gives to the user. Signifier is the sign that points to the user about the affordance. If there is a sign saying push on a door with the handle, we would be pushing it. So this signifiers allows the user to understand about the affordance or the object. There is feedback where the user gets a reassurance and acknowledgement of their action from the system. For example, if it's a knob, the rotation makes it clear that the door is opening. If the knob is not rotating, the door is probably locked. And all three of these can be intuitive or acquired and somewhere in between, because not all the things that we know today are something that are always intuitive. We have to have acquired a bit of things over time through cultural and social context. What is a music instrument? A music instrument is something that creates sound and enables expressive play within a cultural context. So creating sound and enabling play becomes a major part in a music instrument. The characteristics of a music instrument is that it's fun, tactile, and expressive to play with. So if I broadly look at the elements of music instrument, there are functional elements which are about sound creation and the ability to control the sound parameters, and also the feedback that the system gives to the player. There are experiential elements which are about playfulness of the system and the ability where it allows people to express their emotion, and also the level that it can be mastered to seamlessly interact with the system. Then there are social elements which are about the cultural significance about the instrument and the context within which it can be performed, also the performance that it can do with other instruments within a social context. An instrument can also be looked at it from a HCI point of view, where the user actions are converted into quantitative values, which are then converted to another set of quantitative values through logic and further gets output through sounds. Throughout the history, the evolution of music instruments have always coincided with the evolution in the technology or scientific innovation. Any involvement in mechanical, mathematical, electrical, electronic, or digital innovations have always resulted in new ways of music production and creation. This allowed us to expand the boundaries of what a music system is and what are the possibilities of sonic interaction. Why do we need more music instruments? To diversify the sonic possibilities of what we can allow people to do, and also to evolve certain music trends. Music instruments have been key, and to embrace new innovations in technology, we should keep on trying to create new music instruments with the newer technology that is coming up. Over the last few decades, the music system through digitization have seen a lot of democratization, which may have inadvertently passed to a level of standardization as well, where if we look at claviocentricism, which puts keyboard instruments as the focus point of all type of music, where it embodies the Western music theory into a physical form. This has led to a huge democratization, but it also have excluded certain type of expression. Also, if we look at step sequencers from rhythm pattern generation, it allowed us for a rhythmic pattern generation, but it also put a restriction on how those patterns can be manipulated and be produced. If we look at the experimental music interfaces, I have put out some classification into broad categories. One are input from sensors, where we try to take input from varied sensors from real world and physical inputs, and these input values are used to control parameters of sound. There are a set of instruments which try to augment what a traditional keyboard interface can do with much more expression and control. There are modular and performance systems which allows us to manipulate sound at more abstract or more higher level. There are acoustic instruments which are focused on the form, the interaction, and the tactility that it provides to the instrument, and which are again being explored through various new methods. There is a growth of live coding where real-time and spontaneous performances through writing code becomes instrumental, and this pushes boundaries on the computational music and what it can do. Similarly, node-based systems provide the flexibility of creating music without much boundaries through a block-based connection system. There are digital music instruments which are embodied instruments which take digital value and converts them, and there have been really great improvements in the recent times. Then there are text-based prompts which are nowadays popular through generative AI, where a single text can be converted to entire blocks of music or song. Interfaces can invite or restrict certain explorations. So if we look at the brief of what we can do, if I think from a design thinking point of view, we can think about diversification other than democratization. Also, we can focus on exploration as the key thing before thinking about accessibility of the instrument or how well it can fit into all the context. So there are certain factors still to consider on how to make music instruments. There is expressive control, there is playability and learnability of an instrument, and the level it will push creative potential of people, and also the ability that it can be played for longer time, and also the flexibility that provides to the people to customize it for their own needs. What can be new? It can be new modes of input, new sounds, or new forms of expression, or new ways to communicate messages, or new levels of adaptability. All this will help us explore new soundscapes which are not been explored or been harder to explore before. From an interaction per patterns point of view, we can classify them into three categories. One is object focused, where physical or virtual objects become the control elements, where the user interact with these elements, and these objects are then measured by the system to create sound. Then there are direct mapping system, where users can directly manipulate the sound and audio parameters to create music. Then there are set of instruments where the focus is on the movement of the user, where the system responds to the user's movements, and through that response, it can be in multimodal and also in sounds. I would like to show a few examples which have been recently seen to explore music. There is Arbiter MIDI controller helps us playfully explore complex rhythms through a simple interface of circle where colorful dots can be placed across the circles to create rhythm patterns where it spins. Then there is Hackable Instruments by Instruments Lab, where the goal of the instruments is to design for explorable play, where the instruments can even be taken apart to a much more manner where people can customize it beyond the intention of the creator. Then there is A-Frame, which is a recent development of a digital percussion instrument which allows new playing styles and explore possibilities of what a percussion instrument can be. There are software modular synthesis like we spoke, which is optimized for exploration. Then there are software synthesizers like Dennis Noise, which explores complex patterns and new soundscapes through a different interface than what we usually been used to. Then there are modular controllers such as cycle controller, which I made, where the focus is on interaction, where spinning a wheel or hitting a beat can be a new form of interaction. Then there are music effect DJ, which enables more creative freedom to explore, even though it starts with a text-based prompt, but it gives much more creative controller to explore. What are some of the benefits of trying to explore new music instruments? There is a level of learning and understanding you would get by exploring new music instruments, no matter which background that you come from. There is a business potential if you are trying to build a new music instrument in a public platform like social media, or you can get it for a crowdfunding platform. Then there are ways to expand creativity of you as well as your collaborators or fellow creators through new music interfaces that you make. There is a level of increased audience engagement that you can bring if you are a performer, if you want to integrate new type of music instruments in your performance. There is a cultural influence if you are creating a new music interface which sets within a particular context. So there are other evolving areas of music where new musical interfaces are being explored, and whatever new technology comes, I think we'll be exploring new musical interfaces through them. At the end, great music instruments don't just make sound, they enable people to express themselves through sound. So thank you.
All right, thank you very much to Allwin. He's in the Discord and available to respond to any of your questions that you might have. Please leave them over there. However, next we're going to be joined by Arnab, who will be discussing various things around acoustic software, adaptive acoustic software. There you are, Arnab. Lovely to see you. Please turn your screen share on, and over to you whenever you're ready.
Hi, thank you all for tuning in today. I hope you guys had a lovely session so far. And I would like to thank my entire gratitude to the entire Audio Developer Conference team for letting me speak. So I'm really excited to present our ongoing research. It's about adaptive acoustic software for instrumental music, which can be used as hardware, products, and other kind of accessories. So for today's keynote, we have divided it into 4 different parts, So first we go through the company overview and what we do, and then we go for the acoustic software introduction and our research and approach and utility and use cases. And these are the primary sections, and last is the conclusion. Moving on with the company overview and what we do. So we are an experimental culture-driven brand, and we started off as a record label publishing works with ambient and experimental music artists across the world. And soon we realized we need to do much more events and stuff with them. And this went on for a while. We were doing events and stuff, and we started initiating research projects. And then we moved on to creating something more dedicated, so that we can make this a space where a lot of artists can connect with each other as well. They can network, and we can create a economy and a thriving ecosystem of products and solution in the realm of music, art, and technology. So what we did first was we built our own streaming platform, which was exclusively for the ambient and experimental music artist. So if you look at any other streaming platforms like Spotify or Apple Music or any other major ones, they are like a marketplace, where people from any genre are putting their catalog up there, and maybe the experimental artist or the ambient music artist, they are not specifically heard, their voice is not heard out there, since it's a marketplace. So we wanted to create something very dedicated, and that's when we started to nurture this artist as well and create much more a community, where we can make the connection between a fan and an artist so that the exposure is much more amplified in that community itself. And now moving on, so to the acoustic software introduction. So what this project is it's an adaptive psychoacoustic model that is designed for audio data for high fidelity instrumental music, which contains no lyrical attributes. Well, this is based on the idea of Brian Eno, who is a pioneering musician in this category. He once quoted I wanted to get rid of the element that had been considered essential in pop music, the voice. So another technical analogy that I've drawn over here is most of the audio codecs are non-adaptive. That doesn't mean they don't adapt to the kind of genre you're listening to, suppose if it's a pop music or if it's hip hop, it's very rigid. The way they are currently structured is there is no flexibility or room for different kind of genres adjustments, and they're fixed for the entire range of musical frequency and sound, what is audible for the human ears. So we wanted to establish new standard, overall create something groundbreaking that we can help these kind of niche artists, along the footsteps, who are following along the footsteps of Brian Eno, as well as other working artists in the film, as well as gaming soundtracks, etc. We'll dive into it in my later slides. So here comes a little technical side of things. I'm showing here equal loudness contour graph on the right hand side, and on the left there is a description. So if anybody asks today what is the entire music that humanity has created falls under instrumental music, the answer is 60 to 70% music that has been created by the entire humanity is in instrumental ambient music, there is no lyrics or voice, whatever. So despite that, there is no dedicated acoustic software or codec designed to enhance this specific range of frequencies. So as music evolves, we are again seeing like the appreciation for instrumental sound, whether it's in like the soundscape textures or be it in a club environment where there is like high-tech beats and really hard techno, so there also like lyrics doesn't come into play. Maybe like there can be a little overhead of lyrics, but it's primarily drum and synthesizer and these kind of driven sounds. So now when we look at this equal loudness contour graph, there is a very interesting thing to note: the voice frequency band. So this band is like, there is like the human voice is from 3 to 4 kilohertz, or maybe like, see, 300, it spans, it changes from female voices as well as male voices. There can be baritones, different kind of, but anyway, what we have noticed over here, the peak sensitivity is around 2 to 4 kilohertz. That's where the peak sensitivity lies. And again, like I said in my previous slide, there is no codec out there or no software out there who is optimizing this specific zone. So that is where we are coming into play to create something really groundbreaking. And we see a need of the hour, in a way. So because a lot of the musicians, they would love to have something like this in order to enhance their music, in order to enhance the listening experience. It can be a huge diverse thing, like where we can discuss much more. But anyway, just to be a little bit more technically sound, so studies indicate like the instrumental music enhances our cognitive abilities, like it's hands down. And as I end the slide, like on learn an instrument, then it might get easier to learn everything else, so there you go. Now, again, this is also a little technical graph. So over here on the x-axis, we have the frequency once again, and on the y-axis, we have the amplitude, And the warmer colors represent the higher amplitudes, and the cooler colors represent the lower amplitude. So this is like typically a heat map we have extracted from an audio file. And we are representing here like how different bands, like I talked about my voice frequency band in the previous slide. So over here, we are analyzing that from an audio track. We are getting all the audio data, and then we are splitting them into different color bands to understand how the voice frequency is affecting the overall response of the audio. And why is this necessary? Like, why is this required, Because that's what we are here to change. Our research and approach, I'm going to dive into this now in a little bit more detailed manner. So at present, we are developing a codec that optimizes this 2 to 4 kilohertz range, which is, like I said, the sweet spot for human frequency spectrum. But we have reimagined it for instrumental music. And our goal primarily, again, is to enrich this range, giving listeners more immersive and refined auditory experience. This is like a primary goal, like make the most high fidelity sound possible using the codec, So we have mapped out the key frequency behaviors, analyzed how timbre, harmonics contribute to instrumental sound. And here is the overview of our process in the next slide. So we start by analyzing the audio data, We extract the key audio elements such as genre, scale, tempo, tonality, different parameters that we can get from an audio file. And this allows the listener's experience to optimize to the specific characteristic. Like once we have all this data, we can use this data to process and fine-tune the audio as per the track requires. And this is the first step, like signal analysis, before we apply the processing tools, we have to analyze the signal down to its very core. Like we have to get all the fundamental properties from the sound. And once we got that, so over here, we are using our provisional patented algorithm. We apply cutting edge processing techniques. This is like very, 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 I mean, in a way, it's very new age and cutting edge. Yeah, that's exactly what I would say. So that's why we have the provisional patent on this as well. And again, our primary goal is to optimize the 2 to 4 kilohertz range, which is the most sensitive, and elevate the listener's experience of the instrumental sound. Now moving on to the frequency response after EQ. So here you can see again a plot of the amplitude and the frequency. We have the frequency on the x-axis, we have the amplitude on the y-axis. And as you can see, like the blue dotted lines are for the vocals before EQ and continuous line after EQ. And for red dotted lines, it's just instruments before EQ, and red continuous lines after EQ for only instruments. So over here, we have got a plot to understand how the algorithm is actually working, and how the EQ optimization that we have in place is working for different tracks and different scenarios. Because every sound is pretty unique in their own ways. So we have to keep all these factors in our mind when we apply such techniques to our audio. And lastly, we have the step 3 where we integrate AI, because see, like I was saying, like every other sound data is pretty much very unique. Even though we are trying what like in our algorithms, what we have been doing is like we have been processing like batch processing, so that the entire album gets processed. But that's the reason we are incorporating the AI into the audio data, so that even though like I mean, it's much more convenient for us to do batch processing because of the huge sound library and stuff, but it's still, we cannot ignore the factor that each track is pretty different. So that's why we want to take the help of AI, because they do much more better job than human does in some ways. So we want to have a interplay between the human and AI, So at the same time, we are trying to have a little human intervention and letting AI do some of the job, so that there is like this kind of balance between the music as well as human music, as well as that's not totally AI. So yeah, that's a topic for another debate. Anyway, moving on. So what would be the potential utility and use cases? So we have considered like a lot of different kinds of utility and use cases for such a codec and such an algorithm out there. Here are a few ones. So this kind of unique software can be used by many artists and collaborators, sound designers, record labels, who are working primarily with ambient, classical, and a vast array of experimental music. Then again, this is ideal for AR and VR environments and installations where immersive soundscapes are required, So this is unlike anything that's pop music, like wherever there is no lyrical attributes, we can use this codec to drive a much more impactful sound. That's the end result. And then again, like we are also doing this high fidelity streaming platforms. So this is perfect for niche streaming platforms. It can deliver pristine sound to listeners, like I discussed, setting a new standard in ambient and experimental music streaming. Like example, like iTunes did it pretty many years ago, when they had mastered for iTunes kind of thing. So even Dolby, we can have somewhat as a close competitor of our algorithm, but they are doing for cinema and stuff. but not specifically instrumental once again. So another application was like wearable devices and IoT. So our software and codec can provide a unique, high quality experience in wearables and IoT devices, catering to audiophiles and professionals, as well as film scoring, game audio. For the composers, the codecs quality and flexibility could translate intricate details. Again, like these are important because we really want to have a very immersive quality attribute to our end result, where when a listener is listening to any kind of audio that has been processed with our algorithms and codec. And yeah, I mean, this is the overall project, like the need of the hour calls for such a project, because all musicians are nowadays, like mostly the DJ artists and stuff in the clubs and everywhere, we could use such such codecs, like what Dolby did or Mastered for iTunes did a few years back. We could have something like that native, not something as like a mastered version of a track, but rather as a native approach for the sound designers in place in order to elevate the overall experience. Yeah, that's the primary goal for us as a company. And yeah, this is the last slide. So let's experience together how different genres, whether it's ambient, electroacoustic, or even DIY instruments, this is perfect for classical or DIY instruments. Like the market is growing for DIY instruments nowadays. Let's see how like the algorithm response, and again, it's AI based. So as we process and as we get more data, it's gonna improve its efficiency and stuff. So like I want to conclude this in a way, like let's make this a conversation, not just another session or presentation, And I would like all of you to reach out to us and discuss any kind of collaboration opportunities or research you want to do with us. You can even download our app on App Store and Google Play, or sign up for our newsletters and stay notified with our updates. Here are all the details in the screen. I hope you had an amazing time with this session and you got to learn some exciting and interesting news, So I hope you had a good time. Thank you so much. Over to Jim.
All right, thank you very much. So next up, we have Simon Schneider, who has provided a pre-recorded video. I believe Simon will be online to respond again to questions and other comments that are left along the way. So we're about to start that. So in just a moment, the video will roll.
Hey there, my name is Simon, and until exactly yesterday I was a master student at ZW School of Engineering. Today I stand before you, a free man ready to pursue his passion for audio software development without all the academic overhead. But before that, I am happy to present to you the results of my master's thesis, a GPU-based audio processing platform with AI audio effects. Some of you may wonder, why would you want to process audio on a GPU? The short answer to which is that I am frankly unhappy with the commercially available options for digital live audio processors. There are mixing consoles that can process hundreds of channels in parallel, but can't apply distortion to a guitar signal. Digital audio effect processors like the Quad Cortex offer a variety of complex audio effects and routing options, but lack the ability to create individual monitoring mixes. Laptops offer by far the most flexibility in terms of effects and routing, but lack the throughput and reliability to handle an entire band in real time. So with current hardware, there is this trade-off between throughput and flexibility. But what if I told you that you didn't have to choose? Well, this is where the GPU comes in. Thanks to the hierarchical grouping of its cores, the same hardware can be used to handle pretty much any use case that you can think of. Whether processing few channels with resource-heavy effects, many channels with light effects, or a mix thereof, the work is evenly distributed over the available cores for optimal throughput. Furthermore, GPUs excel at AI inference and are able to apply any audio effect that can be modeled using machine learning. So in theory, a single audio processing platform running on a GPU could replace about 60% of the digital gear my band needs to play live. Let's take a look at whether this holds up in practice. For my proof of concept, I chose a Jetson Orin NX for its small form factor and the on-chip CPU and GPU design. Audio capture and playback is handled using a USB audio interface. To abstract GPU processing time from the latency introduced by the USB interface and check, I measured the loopback and system latency using an oscilloscope. The communication with the USB interface is handled by check. I am sure that most of you know how an audio driver works in general, so I won't go into much detail. Suffice to say that the check server regularly calls the registered process callbacks with new input buffers and expects it to return the processed output within the time limit of 1 period. A period of 32 frames, the signal graph therefore needs to process within 0.67 milliseconds, and at a period of 122 frames within 2.67 milliseconds to avoid buffer underruns. The CUDA-FX processor can technically handle any period size that is supported by audio interfaces. However, these two periods signify the minimum buffer size that is practical for the 32-thread warp scheduling on the GPU, and the maximum buffer size that allows processing within the commonly agreed real-time monitoring limit of approximately 10 milliseconds. The signal graph gets its name from the directed acyclic dependency graph structure used to organize its audio effects. The reason for this structure is that the CUDA commands are not launched directly into streams. Instead, I am using the CUDA Graph API, which promises reduced launch overhead for repetitive tasks at the cost of a longer initial setup time. Launching repetitive work directly into a CUDA stream requires the scheduler to create a new execution plan at every process cycle. With a CUDA graph, this is done once at instantiation. At subsequent launches, the contained CUDA commands execute faster and with more stable processing times. Based on my measurements, the performance benefit scales with the number of individual CUDA commands within the graph. For example, using a CUDA graph to process a dilated convolutional network with 24 layers reduces the mean execution time by a third. Towards the right side of the graph, the audio effects successively contain less individual CUDA commands and therefore see less benefit from graph launching. Usually, each node in a CUDA graph executes a single CUDA API command, like launching a kernel or copying data between buffers. As a result, the graph of a multiband biquad EQ would look like this. First, the source buffer is copied into the process buffer of the first band. Then, the infinite impulse response kernel processes in place on the process buffer. Finally, the finite impulse response kernel writes its output directly to the process buffer of the next band. This process is repeated until the last band writes its output to the destination buffer of the audio effect. To simplify complex workflows, CUDA offers another node type called child graph node, which, as the name suggests, allows nested graphs to be added as single nodes to a main graph. Now, brace yourself for a lot of graphs. The signal graph specifies the dependencies between the audio effects. At runtime, each audio effect then builds its own CUDA child graph. These child graphs are then added as nodes to the main processing CUDA graph. And finally, the CUDA graph copies the dependencies specified in the signal graph to ensure that everything is processed in correct order. The beauty of this setup is that the only thing limiting the complexity of the signal graph is the capacity of the GPU and the period duration. Within that limit, users can define as many serial or parallel audio effects with intricate splits and merges as they like. The signal graph then takes care of all the memory allocation, and the CUDA scheduler manages the dependencies and synchronization. Now, before I dive further into the details, let me hand you over to Guitar Simon for a quick audio demonstration. Hey there, Guitar Simon here. To my left, you can see a currently very empty signal graph. And what you're hearing right now is my guitar DI signal being routed straight to the stereo outputs. Beautiful. But I play metal, so let's add some amps. Can you hear that? No, that's not the sound of people applauding the excellent tone. It's the noise of the cheap preamp of the Behringer UM2 audio interface I had to use because Czech for some reason decided to not work with my Focusrite. Oh well, silence. Till I do this. For full disclosure, I am not actually loading new audio effects right now, but rather I am setting the mix ratio parameter of already loaded effects from 0 to 1 to engage them. I show this as an example of how the CUDA graph can be updated with soft parameter changes in real time without expensive reinstantiation. Now the tone could still do with some fine tuning, so let's engage the EQ. There we go, nice and tight. One last thing, do you know what's better than one guitar? Two guitars. And while Guitar Simon 2 and I play a sick riff by the band While She Sleeps, let me hand you back to VoiceOver Simon. The dual guitar stereo amp signal graph that you heard just now has a mean execution time of about 2.5 milliseconds and processes within a 128 frame period at a success rate of more than 99%. Unfortunately, the remaining process cycles either experience scheduling delays or process stalling and can take up to 20 milliseconds to complete. And while these outliers scale somewhat with the complexity of the signal graph, even the most simple graphs produce occasional buffer underruns at a 128 frame period. So for this demonstration, I cheated a bit and ran the signal graph at a period size of 512 frames to get single takes without dropouts. Obviously, while this problem persists, the CUDA FX processor cannot be classified as real-time capable. However, with this demonstration, I wanted to show what it would be capable of once the outlier issue is addressed. This is not to say that I have not tried my best to solve this beforehand. First, I copied the input data from Czech into a memory location that was mapped into the virtual memory space of the GPU in an attempt to avoid host-to-device copies. Second, I ensured that every single CUDA command was included into a single CUDA graph to prevent the need of in-time scheduling optimization. Then I ran the application on 4 isolated CPU cores and killed any active processes that would schedule work on the GPU to ensure that nothing interferes with the scheduling of my audio processing pipeline. Unfortunately, all of that was to no avail. Finally, I separated the graph processing into its own thread because I had limited control over the process callback thread created by the check server. My first attempt with a blocking ring buffer between the threads produced much more frequent and extreme outliers. Turns out that the CUDA scheduler is known to perform poorly when work is launched from threads that were recently woken up from sleep. With a non-blocking ring buffer, the outliers returned to the previously observed pattern. Through various other tests, I have noticed that after sitting idle, the CUDA scheduler would always require some time to warm up before returning to optimal performance. So since I was already spinning the CPU while waiting for new data, why not also spin the GPU to ensure the scheduler doesn't fall asleep? Finally, I saw some actual improvements in the frequency and duration of the outliers. Still far from being real-time capable, but at this point I decided to focus on building out the framework to ensure that I had a working demo at the end of my thesis. Putting aside the question of real-time capability for now, let's focus on the unique selling point of the CUDA-FX processor, AI inference. The NAM audio effect from the demo applies distortion using a model from the open source neural amp modeler by Steve Atkinson. All I had to do is export a trained instance of his convolutional network to the ONNX format, parse it into a TensorRT engine, and then inference it on the Jetson. Sounds simple, I know. I thought so at first. Since I ended up dedicating an entire page of my thesis to the problems I've encountered along the way, I feel I deserve some of the credit. But Steve Atkinson is still the MVP here. I hope that you liked the demo riff, because I'm going to play it on loop to demonstrate the accuracy of the TensorRT inference. If you are not already listening with headphones, I recommend that you switch for this part. First, you will hear just the original amp. Since both stereo channels output the exact same information, you should hear a perfectly centered monosum. After that, I will switch the right channel with the inferences of the neural amp modeler VST and CUDA-FX processor. The resulting stereo widening is a consequence of the inaccuracy of the inference processes. The wider the stereo field, the more the inference differs from the original. None of the inferences manage a perfect mono output, but they are all accurate enough that at least I was unable to identify the original amp in a blind test. I am aware that producing yet another guitar amp modeler is hardly a noteworthy achievement by now. However, most commercial options use proprietary training and inference algorithms, and even the neural amp modeler requires models to be exported in a custom format. To my knowledge, the CUDA-FX processor is the first hardware that is able to inference audio effect models using a standardized and open source network format. I have mentioned before that the Jetson is just as capable of handling many lightweight channels similar to a mixing console. To test this, I have built a signal graph that mimics the input, bus and matrix stages as they would be found in a mixing console, where each stage has half as many channels as the preceding one. Each input channel is processed using a gate, compressor and 5-band EQ, and the bus and matrix channels are only processed using a compressor and 5-band EQ. At a 32 frames period, the Jetson can handle 24 input channels and 64 input channels at a 128 frames period. As it stands, CPUs and DSPs still get a bit of a reprieve before GPUs make them obsolete for audio processing. But I would like to highlight again the flexibility and scalability that a GPU could bring to live sound engineering. No longer would you need a specialized piece of gear for different tasks or instruments. If your desired audio effect is missing, profile it using machine learning, or even better, program it directly into CUDA. No longer would the processing power be split among 3 stages of fixed numbers of channels. If you need more input channels, sacrifice some bus channels. If you need more bus channels, sacrifice some matrix channels. Your use case is the design and only the GPU is the limit. No longer would you need an entirely new device if your use case exceeds the processing power of your current one. Simply add a second or larger GPU and crack on. Bold claims, I know, especially for a proof of concept that can't even guarantee a worst case execution time below 20 milliseconds yet. And admittedly, especially the scalability is still very much in vision stage and could prove much more troublesome than I expect. But yeah, if this presentation has not convinced you of the GPU's potential for audio processing, then I guess I have to work even harder until next year to try again. Thank you all for listening.
Alrighty, thank you very much to Simon for that wonderful presentation. We're actually running slightly ahead of schedule, which is quite a surprise. So we're going to just go for a quick break now. We had a 10-minute break scheduled just before the keynote session from Andrew Sheps, which will be coming up in just a moment. So we're just going to extend that slightly longer, so it'll be about 20 minutes, and the keynote will begin at 4 o'clock UTC. So back here in about 90 minutes, and we'll be joined by Andrew. So look forward to seeing you all very shortly. Hello, hello, hello. Welcome back, everybody. So we're about to be joined by Andrew Sheps for the keynote session. So this will be a slightly longer session with Andrew. So Andrew, if you'd like to turn your camera and microphone on and start your screen share.
Hello.
There you are. We can see you.
And there's that.
Looking great. Perfect. Over to you. Thank you very much.
Fantastic. Hold on. My presenter view just disappeared. This is the way this stuff goes, isn't it? It's all working so well. There we go. Hello and welcome. Thanks for coming back from that 10-minute break. But there's a big break afterwards, so if you can stick around, that would be fantastic. I'm Andrew Sheps. I'm a record producer, mixer. Basically, I make records. I've been doing that for a really long time, which is a little scary when I do the math, but yeah, almost 40 years now, because I'm kind of old. The genesis of this talk is from a conversation I had with Bobby Lombardi when we were taking a train up to Birmingham. And the thing I want to say about that first is he had stayed at our house after we went down to check out the venue in Bristol where ADC is going to be in just over a week. And I had gone down to meet him because I wanted to introduce him to a cake shop called Toots, which you can see in Gathertown. But it was a Tuesday and they were closed. And it's one of the most disappointing days of my entire life, going all the way to Bristol to find out that I wasn't going to get cake. So if you're coming to ADC in person, I would highly recommend you get over to Toots, but keep in mind, they're not open on Tuesdays. I think it's Thursday through Sunday, something like that. Anyway, we were on a train and we were just talking about interfaces, and there's a particular reason it came up, which I'll get to sort of at the end. And it's easy to sort of put together a title before you've done the talk, and then you realize that you put AI in the title of the talk, and then you realize, well, but I don't really want to talk about that too much. That is where we're going to end up, is sort of the AI tools that are available for making records right now and their interfaces, because it runs the gamut of very high-level interfaces to unbelievably tweaky interfaces, and I think that really all comes down to application and how the user is using it. So I'm not going to be really talking about using AI to create tools, because that's what you guys do, and you know a lot more about it than me. But I'm going to talk about eventually how that has impacted making records. But I want to start just with UI. I want to talk about UI for a bit, because I just find this stuff fascinating. Whenever I talk about anything, I end up diving into the history a little bit. And really quickly, one book that I found that is fantastic is called Push, Turn, Move. And it's interface design in electronic music. And it's about all the classic drum machines and synths and moving on to modular synths. And it's a really fantastic book by Kim Bjorn with a foreword by Jean-Michel Jarre. So if you're into electronic or ambient music from way back, you're certainly aware of Jean-Michel. And what it's got very close to the beginning of the book is this sort of idea about how to think about the interface you're building. And I found this really interesting and obvious. And whenever you see something that's right, it looks obvious, even if you've never seen it before. So basically, you've got three different areas you want to think of. So the first is the user. I mean, and if you're designing a UI for a user and you're not putting them first, well, then that's just an oversight. But the things that are important are, what is the skill set of the user you're targeting? Do they know what goes on inside of your product? Or do you just want them to have a vague idea of what it is they want to do and give them just enough controls to get through what they want to do without having to know what's going on under the hood? And they're really good examples of both styles of newer AI products. Another one is, what is the purpose of it? And I think this goes as much to the design of the product itself as it does to the UI, but it's obviously to do with what situation is it going to be used in. And there are a lot of UIs we'll see in a second to do with performance, where you need to be able to get around those very quickly and recognize things from far away at just a glance, rather than having lots and lots of buttons that sort of look similar because they could do different things. And there's some really good examples of that. And that also starts to bleed over into context, which is the environment it's going to be used in. And then also other considerations, like if you're building a hardware box, well, what are you going to make it out of? What's the supply chain like? How durable is it going to be? And if it's software, like how much screen real estate do you need? You're going to have multiple pages and things like that. So there's a lot that goes into this. And I'm sure you all think about this and actually know more about it than me, but I like the sort of high level thinking. So historically, let's just talk about music gear, because that's what I do and it's what a lot of you are into. Let's go back to the Wayback Machine of analog hardware. And in analog hardware, the UI was basically direct control of circuit elements, right? Every knob on that NEVQ at the bottom is controlling a resistor, basically. It just switches resistor values in a circuit. Fairchild, same way. LA2A, same way. The Studer A800 that's the tape machine on the top left, is a kind of interesting bridge between the pure analog, I'm turning a potentiometer that changes the resistance in a circuit, into some of the sort of earliest of the digital interfaces for analog hardware. And I'll get to that in a second, because that is the downfall of an entire decade of my life, is navigating these very small boxes that have a million functions and you can't get to them easily. So the poster child for this is something called the Timeline Lynx. So this was a synchronizer. It has a big multi-pin connector on the back, and you would have a different cable for whatever type of tape machine you had. And this synchronizer would get information about your position from time code and how fast the tape machine was running. And then you would hook up multiple units, and that would lock up the tape machines so that they would run in sync in some reproducible way, which is good, because if you're recording to a second tape machine, you want to be able to have that stuff stay in sync with the first tape machine every single time you do it. So this is really the innovation that allowed the multi-track tape recording that had been developed from sort of pre-Beatles, where you started off in mono, then you went to 3-track recording, but still monitoring in mono, then to stereo, and eventually sort of 24-track tape, a 2-inch tape with 24 tracks on it, became the industry standard, with some people saying 16 tracks sounds better and blah, blah, blah. But as soon as you wanted to go over 24 tracks, you had to start using more than one tape machine. Obviously, digital DAWs, recording to computers, didn't even really exist at that point. So you'd be locking up multiple tape machines, and as soon as you do that, you've got analog tape machines, which when you hit play, they sort of kind of run at the speed they're supposed to run at, but it's a phase lock loop, so they go a little fast, they go a little slow, and they're constantly slewing their speed around. And so then you would print a square wave onto a track of tape, and that square wave would be encoding time code. The Lynx would read it, the Lynx would have control over the transport, and you would say, I have 2 tape machines, and I want one of them to be the one that I hit play on, and that will be the speed that everything else needs to go at, and it would locate and control the speed of lots of other machines. It's a really complicated device, and I don't know if you can tell by the picture, but it's a half rack space. It's 1 rack space high, and it's only a half rack width. And there are a million options. So really quickly, kind of slowly, this is the installation and simplified operation manual, and this is the first 3 pages of about 70. And this basically, I'm going to glance over at the presentation itself, just because it's a little bit small for me on my presenter screen. It tells you how to set up the display. It tells you, you don't even get to the point, I think, where you can choose a tape machine. But choosing a tape machine on this box was an absolute nightmare. I mean, if I go back to the display, there is basically what you've got is you've got 8 segment displays. And so it would be spelling out words like Studer and A800. And so you'd have to find a manufacturer, and some letters really don't show up well on that kind of display. And then you would hit go and you'd get into the submenu. And so if you looked at a menu tree of controlling this device, it was an absolute nightmare. But the idea was that you would only do this in a setup mode, and then you would have a very intuitive interface, which is more like what we were talking about before, where you could very quickly glance, look at the lights, know that tape machines were actually in sync, and you had buttons to take things on and offline and simplify in that way. So actually running the software was an absolute nightmare, but you didn't have to do it that often. I want to go back to the A800 tape machine. This is one of the best sounding tape machines ever built. One of the things it could do is to vary speed. And you can see on the right, they've strangely, the manual, the left side of the page is in German and the right side is in English. And on the left side, it says vary speed, which is what everybody I've ever met in the universe calls vary speed. But they have translated vary speed to vario speed because you vario it or something. So this is a recording technique that unfortunately is a bit lost in present day digital recording. You can do a version of it in Logic pretty well. I would imagine you can in some other DAWs where you can basically just completely change the speed of the transport while recording. And then when you play back at your original speed, the pitch of that recording shifts along with the track. So the track goes back to your original tuning, but your new recording is pitched up or down compared to what it was when you recorded it. It was fantastic for when a vocalist couldn't quite hit that top note. You would slow down the track a half step. They would sing the top note. You'd speed it back up. The formant wouldn't have changed that much, and you'd get away with it. You could also slow it down to play a very difficult passage on guitar and then speed it back up. Recording percussion. It was great to record it a little bit too fast because when you slowed it down, it would naturally take care of some of the harsh high end that you would get off of a tambourine or a shaker. Huge part of analog recording workflow. I would imagine if I was in a tracking date, I would vary speed at least 2 or 3 times a day and sometimes all day, changing speeds. And an example of this would be on the Chili Peppers record Stadium Arcadium. If you listen to a lot of the guitar overdubs that John Frusciante did, they're very weird guitar tones, very glassy, some of them. And that's because a ton of those were recorded with the tape machine sped up or slowed down. Okay, this brings me to why this is such an absolute nightmare. You may have read the text on the right while I've been blabbing on and on about why we used it. So let's say that you wanted to slow the tape down a third. Okay, so you need to slow the tape down 4 semitones. Have I done that right? I've done that right. So if you look at the way you would set the Studer, it says that you're going to be shown a number. If you look at your the calculation there, Z is the number displayed, and V is the percentage you want to slow the tape down. Now, the problem is you're dealing with a logarithmic scale with pitch, and you've got a linear scale of speed. So this is only half of the battle. But you don't even set the value for the percentage you want to speed up or slow down the tape machine. You have to set some crazy number that when divided by 32,768 and taken away from 1 and then divided into 1 times 100% gives you the percentage you want. Absolute nightmare. But this still doesn't even get you to pitch. So we'll just have a quick look at what gets you to pitch. So you start off with this, right? Now, this means that the number I actually am worried about hasn't been solved for. I need to know the number that I want the tape machine to look at. So first we need to switch this around. I had ChatGPT do the math, and I had to put these in using LaTeX, which I'd never used until I made this slide. So if the formula is wrong, it's a concept. It's not a formula. But let's say that that's right. So now I've got a way to calculate the number I have to set the tape machine at if I know the percentage I want to speed up or slow down the tape machine. But that doesn't really help me at all because I know what the pitch is. So if I want to get the pitch out of percentage, I would use this formula, but then this formula needs to be switched around so I can actually get the percentage based on the pitch, and then I could take that percentage and I can plug it into the first one. And the reason I'm telling this incredibly long, boring story to a very quiet computer is that this is the very first piece of software I ever wrote. I had written weird like calculators and spreadsheets to deal with drop frame timecode versus non-drop frame timecode. I'm not even going to go into that. It's a disaster, and I'm so glad it doesn't exist anymore because we no longer deal with that. But I used a program called Real Basic, which in 1999 they came out with version 2, and it had a UI builder, and it was basically it was programming in BASIC, and it could build cross-platform apps. So I built an app, and it did nothing but let you say how many semitones you wanted to go up or down, and it would spit out this ridiculous like 6-digit number that you would then hold down several keys on the tape machine to make that number appear, and then it would show up. And so that was used extensively on that Chili Peppers record, to the point where I actually got a call from Ryan, who's one of the other engineers on that record, asking if I still had it about 5 years later, because he was working on a Studer tape machine, and there's no other way to do it. Okay, people got better at interfacing. This is when I believe basically what the idea was is they assumed there would always be a technician to set stuff up, and then there'd be idiots like me running the stuff and just pushing the buttons that were available. So I could push play and record. Someone else would come in and change the speed of the tape machine. But obviously, in a creative session, that's not the way it works. Things got better on the hardware side, but I mean, even drum machines, the Linn drum machine, when you set the swing, you had to go into a little sub menu, again on LED display, not LED, the little 8-character displays, and you chose from A through F, and those were the swings you had available to you for a drum machine. But let's go to digital land. So if you remember back to the first slide where I showed lots of analog gear, let me go back to it. There are very few controls, because those controls are controlling the things that will change the sound, and they're changing stuff in the circuit. So then you get into digital land, and you can do whatever you want. You can make the UI as exciting, as simple, as complicated as you want, and instead every single person in the world did an 1176. I'd like to say that we have enough 1176 plugins now. Now, if any of you are working on an 1176 plugin, then I would say that we only have enough minus however many you're working on. But when you're done with that one, maybe don't start another. This is not all of them. This is just, I love this screenshot because it's from an article where somebody actually compared all of them on drums and bass. I don't know who won. And also, I want to thank Anurag Choudhary for bringing up the phrase skeuomorphism, which is exactly what this is. This is bringing something from the analog tactile world into the digital world as a UI, because people are used to it, or because maybe you can't come up with another way to represent things that make sense. So you have this sort of interface design, which there's nothing wrong with it, because there was nothing wrong with the analog interface. The interface was very simple, and the only controls that were exposed are the ones that people needed to change. And then every once in a while, there would be something that maybe you might want to change, and they would put an extra knob or a screw on the back of the gear, like an LA2A, which only has 2 knobs on it, and only one of them actually affects the limiting that happens inside of the box, has a knob around the back that changes the frequency response of the detector circuit. And that sentence was complicated enough that most people who were using the front of the box didn't even know what that meant really. And so they put it around the back, where you'd have to crawl in the back of the rack and change this. And the idea was you could make a de-esser out of your limiter, which is now worth $8,000. So you could have the most expensive de-esser on the planet if you went around the rack with a screwdriver and turned this knob up so it only looked at high frequencies. Then obviously, as digital processing got more complicated, because you could do so much more in a box, and then processors got more powerful, so you could do so much more in an individual plugin in real time, the interfaces got more and more complicated. And then there was this sort of backlash to the one knob interface, or in the case of that really great plugin on the bottom right, 4 knobs. And this is another great UI design, I think, where you completely hide the complexity. And you say to the user, this plugin kind of does this. And if you turn the knob, you get more of it. And if you have too much of it, you turn that down. And then maybe you've got 1 or 2 other controls that are ancillary to your main control, but that's it. Now, that control could be controlling 1 parameter of the equivalent of a gigantic circuit, or it could be controlling lots of them. And the reason I put one of my plugins here is because this, on the bottom right, it's parallel particles, which I developed with Waves. And the idea was that I use a pretty complicated template for my mixing, which involves lots and lots of parallel compression and other parallel processing, reverbs and delays, but also less traditional parallel stuff like compression and frequency modulation, but also the words are flying out of my head. I use a lot of parallel stuff. And sometimes some parallel stuff feeds other parallel stuff. So you could have pre and post parallel stuff. And they had wanted to come up with a way to let Waves plugins users have that sort of setup, but in a way that wasn't going to be a nightmare. You didn't have to use 5 auxes to get the audio routing necessary to do the sort of things I was doing. And we were looking at inter-plugin communication and all kinds of stuff to try and build this so it would actually be what I did. And we realized after a little bit of time, and we did spend some time on it, that there were 2 problems. One was at that point, you really couldn't send anything other than metadata between plugins. It was really difficult to send actual audio. This plugin's old. It's kind of crazy to me, but I think it's coming up on 15 years old, which that's not really possible because I'm only 15 years old. So what we came up with instead was, all right, how do we build this into one plugin? And I said, well, how about we just go the opposite way and make it unbelievably simple and don't let anybody know what's going on under the hood because it doesn't matter. There's no reason to know what's going on if it would be too complicated for you to set up yourself. So the idea was there are 4 parallel processes here. There are 2 that are sort of frequency generators. There's an air, which is, if you're familiar with the ADCx oral exciters, it's that same kind of idea where rather than being an EQ to add high frequencies to a sound, it will synthesize high frequencies based on the upper mid-range frequencies. And this is really good for brightening things up. Let's say you've got a vocal recording where there's a lot of hiss, or there's just noise that's in those upper frequencies. So you can't just crank the high frequency shelf and have a nice bright vocal. But you could create some higher frequencies based on the mid-range, and you would get the feel of a brighter vocal, but without having to turn up the problems. And then sub is the same kind of thing, but rather than actually adding subharmonics, it adds the harmonics of these subharmonics. So it's more of a psychoacoustic process to make it sound and feel as though there is another octave below what you've got going on, but you haven't actually added a ton of stuff down at 20 or 30 hertz, and you start to trigger all your limiters, and then all of a sudden you've got a mix that sounds really good until you actually try to listen to it. So that's the idea with those 2. And then on the left and right, you've got something called thick and something called bite. They're basically parallel compression chains, and they're just different, and they do different stuff, and I had to come up with a name for them. So I called them thick and bite. And the idea is that as you turn the knobs up, you get more of them. So it looks like it's a very simple mixer, but what's going on behind the scenes is with the compression ones, at different points on the knob, you are turning up the input or the output or both, and actually changing compression ratios and also changing release times. And with the harmonic generation, you're changing not only the amount of the new harmonics, but you're also changing balance and EQ on the main signal, because as you really start cranking, I didn't want it just to get louder, because if it it's only a lot louder. Nothing sounds better than level, and people get tricked. And I thought, this is great. This will be 4 knobs. They all sound totally different. Oh, and there's also a lot of cross routing between the 4 of them. So the outputs of the 2 parallel compression circuits get summed in a way, but it's not as simple as just mixing them together. And then they go off to the harmonic generation stuff, and then it all meets up at the end. What I wanted this to be was I got something, it sounds good, I think, it needs something, but I don't know what, so turn one of these knobs. And if it's worse, turn it back down and turn a different one. And if some combination of these 4 knobs is not the thing you're looking for, well, hopefully, because it's doing so much stuff all at once, you would hear it kind of get close to what you wanted, and then you could go back to plugins that you know well, but have more, not necessarily complicated, but more complete interfaces where you could tweak and have a lot more control. The feedback on this was that everybody wanted to know what was going on under the hood and why weren't there gain reduction meters and what frequency were things at, even though there is a frequency for the little sub guy. And I think, you know, there's some people who like it, but it was not as big a hit. And it was really interesting to see this almost backlash to the very simplified UIs. And to me, it was sort of, you know, what do you think, I'm stupid? Like, I know how to run gear. Give me all the knobs and I'll run the gear. And of course, what that leads to is what's going on behind me, which is my favorite thing in the world, which is modular synthesizers, where everything is exposed. If you have an analog module, absolutely everything is exposed. And not only are all of the controls exposed, but everything in the signal path is exposed. And controls for everything that controls the signal path are exposed. And the complexity that you can build so quickly with this is, I think that there's a reason people like it is it's because you have very, very small modules that are generally, and we're going to talk about this in a second because it's not true at all anymore, but when it was analog modular only, the modules themselves were not very complicated. So they might have 15 knobs on them, but those knobs all made sense because that module did a thing. And the thing was not necessarily completely easy to understand, especially if you're using a buchla or something like that. But you knew what an oscillator was. You knew what an envelope was. And these are building blocks, but you can control them. Now, I mean, you look at some of the modules coming out, and it's insane what they can do. And that's because we've gotten to the point, sorry, where you have digitally controlled analog modules and then a lot of pure digital modules. And they're awesome. And I use them all the time. But you have gotten back to the point of having to remember to hold down these 2 buttons while you turn this knob, because that puts it into the other mode, where then when you hit the other button with your nose, you can make it do the thing that you can't do until you put it in that mode. But now all of the basic controls are gone because you got it in the other mode. It's awesome. But it's also interesting how we've cycled right back around in one of the parts of music creation that used to be almost, in some ways, you could say, the most pure. There wasn't some circuit hiding behind the front panel with some knobs in front, so you get to control a little bit of it. You got to control everything. You can still control everything, but if you had, like the modular, oh, you can't see behind me because I got a slide behind me. There's a big modular behind me. It's big. If it exposed every single control on all of the modules, it would be the size of my house. And my house is kind of embarrassingly large. So that would be insane. And you can't do it. So then you come back to this idea of how do I compress the UI so that people get exactly what they need, both in terms of control, but also in terms of feedback, but they can work quickly and it can be recognizable. So here are 2 examples of plugins that do that incredibly well. In the background is the FabFilter Pro Q3, which has no UI when you open it up. It's just a picture of the audio you're playing. And then you create the UI as you use the plugin. I want another band of EQ. I want another band of EQ. I want another band of EQ. And so the UI gets more complicated the more you use it or the more you try to do with it. But at the same time, they still hide everything because every band of EQ is just a dot, colored dot. Hover over it, you can see some controls, but it's a dot. And you use modifiers and drag the mouse around, and you can change most of the parameters you would need. It's really incredible. And, you know, they're not the only ones to do it. It's the first one that I saw that did it, to have a completely blank UI that was infinitely customizable, but also incredibly easy to understand what's going on. Just really, really smart. Then in front of that is one of the best plugins ever designed. I would say that, you know, you could teach a course in this plugin. All right, I'm kidding. It's because it's mine. This is a channel strip that I helped develop for Waves. And just, we developed this, I think this is over 10 years old now. Again, scary to me. But I use this all day, every day. So this was the, don't try and recreate what you do for other people. This is a, what do you want plugin. And for me, I had lots of plugins that I used a lot. There were probably 4 or 5 plugins that I would use all the time. Some for saturation, some for compression, some for EQ, and then a couple of special ones. And so I wanted them all in one window because I hated doing the same sort of thing on 20 tracks in a session. And instead of opening up 20 plugins, I would be opening up 60 or 70 plugins to get to all of the stuff that I wanted to do. And those things all interact. So when we designed this, one of the things I wanted was for it to be very, very flexible. So you can reorder the modules, but the modules don't change their look. But it's got a huge number of knobs on the front, and it can look really confusing and scary the first time you look at it, especially for people who aren't really that experienced with more complicated music workflows. They've been using stock plugins so far, some of which can be quite complicated. But the idea of a channel strip in a window this small, that's a hell of a lot of stuff you've got to control. So what our idea was, first of all, we were going to hide half the controls. So I should have had an open instance of this because then I could actually show you things, but you can get a demo. So if you see in the upper right, just underneath that white strip at the top of the UI, there's a little kind of zoom, window zoom box, 2 rectangles. I'm sure there's a name for that, and you know what that name is. And what that will do is that will open up expanded controls for each of the modules. So the very first thing we did was just hide them. And then the next thing we did was, we've got lots of smaller knobs. Those are all going to look exactly the same because they're smaller, so it won't be confusing, and they're too small to get any kind of recognizable visual feedback on quickly. But the large knobs are going to be different on the different modules so that it's easy to find things. And so we did stuff like with the larger knobs, you've got 3 modules that have them Bakelite. But the compressor module, which is all the way on the right, has the 3 main controls for the compressor itself on that silver background. So that's the compressor, really easy to find. EQ, it's all small knobs and there are tons of them, really easy to find. The de-esser is the only thing that has 2 of everything, and we gave that the silver colors because that's kind of a special module, and it's not necessarily one that you would expect to have in a channel strip, and so you've got that. Then the gate, I didn't even want the gate. They said we had to put a gate in, so I don't really care about that one. And then, that's not true. It does some really cool stuff. And then the preamp was built over the filters. So we thought, well, that's going to help differentiate it. And especially because you can reorder them, that became a huge consideration. We had finished the audio for this plugin, I think 3 or 4 months before we finished the UI. And we were right down to the last day before it got released. And we were still tweaking things because it needed to be this thing, you know, where you turn away and then you come back. And like, okay, the compressor is module number 3. And you had to be able to do that 10 times in a row, or we hadn't gotten the UI right. So I love the fact that you can have this sort of challenge to have no UI at all, or to have a huge amount of UI, but both of them need to be intuitive and usable. But I would certainly take the fact that mine is skeuomorphism all over. It's analog gear because it's an easy way to represent stuff. And there was a great presentation about designing a new DAW. that started off with a quote that you shouldn't design a new DAW. But touching on, and that's of course where the skeuomorphism came into the day. It's this idea that the workflow hasn't changed a whole lot, but the tools have. But because the workflow is kind of the same when you're recording music, that maybe the interface to recording should sort of be the same. And that's the way Pro Tools works, and I use Pro Tools all day, every day. It makes perfect sense to me because I know all about tape machines and I know all about mixing consoles, and you kind of get those two, and then it just does a million things on top of that. But there was this sort of revolution when Ableton Live came out, because it was the first thing that took the drum machine model and applied it to music. Now, there were lots of ways you could put loops in an MPC 60 and all kinds of stuff like that. This wasn't a brand new model, but it was a brand new application. I'd have to say that when it first came out, and the arrange window, like as far as anybody knew, that didn't even exist. Like this was it. This was the window. And there were so many people I knew who had done a lot of work with MPC 60s and things like that, who just lost their minds, because for them, this was the skeuomorphism of what they had wanted to work on for music all the time. Whereas nobody else had done this. Everybody had used that for drum machines and possibly sequencers, but that was it. So now all of a sudden you've got a new interface for creating music. And there have been a million of them since, and there's probably lots of them before. I put this together recently, and it's not like I've researched every DAW, but I do think that this was really a sea change, not only just in DAWs, because it changed the way you think about stuff, but it really started to open the door for people to think differently. I had a program called Sony Vegas, which only ran on Windows, which could time stretch loops as well as Ableton could. And it's got to be at least 5 or 6 years before Live came out. But the interface was terrible. It wasn't like this. It didn't feel great. You just you could make loops different tempos, and that was cool. Whereas this made it music creation. You're going to make a record in this thing. You're not just going to make a track that then you'll finish somewhere else. And then obviously, well, not obviously, but to me, what this did was then spawn a huge generation of hardware controllers where you could go back to this idea of just grids of buttons like drum machines, like the MPC 60, but have them be more like soft keys, because now you could light them up different colors. So you could have this sort of recognizability of function, but on a huge grid of buttons. So you could have way more buttons than you could on a drum machine where you have to label them kick, snare, or an MPC 60 where you could have 20 or 25. It just made things easier to make complicated in terms of the number of controls, but simple in terms of looking at a piece of gear and getting on with it. Now, there's still UIs being made. These are just 3 examples of things that are not the same as every other UI, those sort of based on it. The one on the left is called GeoShred, and it is a different way of inputting music. It uses a lot of the stuff that's built into MIDI 2.0. It uses MPE, but it also has this like smartly quantized pitch performance type thing. I watched the videos. I have not actually used it. It looks really cool. It is a different way to interface with things. And strangely, or not strangely, but interestingly, most of the sounds available for it are acoustic instruments. So it's meant to be a new way to perform traditional instruments, not a way to make new sounds so much. I mean, obviously there's synth stuff you can do as well. On the bottom right is the Rolly C-board, which basically takes the traditional keyboard, because there's nothing wrong with using keyboards to input music. It's the way, certainly in the West with the 12-tone scale, it's something that makes sense. But it adds this sort of fluidity for moving between notes, and then also it supports all of the new type of performance features that you can have given new MIDI and the way the synths are implementing it. And then up at the top, it's a little nod to the wind controllers, which started in the 80s. And the Iwi was one that used a couple of times. Yamaha made this wind controller thing. And it worked. It was just covered in spit all the time, though. It wasn't the nicest thing in the world. But they also made a breath controller, which could give you some very sort of human input. And I think what the point of all of these interfaces is to give you more than just off-on velocity kind of control over what you're doing, and just try and make things much more expressive. So now we'll talk about a little AI thing. So let's go back to our user purpose context Venn diagram, because I managed to make circles that have stuff. Well, what's the deal? Were you almost done? Good God. I've been talking a lot more than I thought I would. So just really, really, really quickly, the AI tools that exist right now are unbelievably cool. Here are 3 of them. Now let's talk about them individually, because all of these are using AI under the hood, but they present themselves in very, very different ways. So Isotope Neutron, it uses AI to figure out what settings to put on very traditional audio processors. So you get an interface that looks like any other plugin. I mean, this has the look of the Pro Q3. It's a very common thing now to show each EQ band as a dot on an EQ transfer function. And then you've got different modules that will all look sort of traditional. And then you've just got a button up top that says Track Assistant. So the AI is like, hey, let me take over. Just hit a button. I'll listen. I'll tell you what to do. But then you can come back and in a very traditional way, tweak all the stuff that it did. Then you got something like Spectral Layers from Steinberg, which is amazing. I use it all the time. This is meant to be a tweak fest. And it is a tweak fest. And interestingly, all of the tweaky tools are on display, and all of the serious trained AI stuff is hidden in menus. All of the unmixing algorithm stuff, it's like you got to go up to a menu and click it, and then you get a little dialogue, and then you hit OK. And then it does stuff that is absolutely mind-blowing. And then there's SynPlant, which is a great, cool synth from Sonic Charge, where it will generate stuff based on seeds. It grows things based on your seeds. And the really cool thing is the seed can be a sample that you put into it. And then you get into these really weird UIs. But you're doing something weird, and the UIs are actually unbelievably intuitive. I'd say if you don't know this plugin, definitely check it out. The use of UI in this plugin is extraordinary. It's really, really good. And then I wanted to, what's the deal? We got 3 minutes. Is that the deal? I don't remember if I'm supposed to go 40 or 50 minutes. What I'd like to do also, I know we've got a break coming up after me, but I'd like to go to the GatherTown main auditorium thing, which is where most of you are probably sitting. Because apparently if I go on the stage, I can stand there and then people can come up and actually ask questions. Because doing talks without feedback and Q&A is so weird to me. And it's why I'm babbling, and it's why I'm probably going over time. I just have a couple more things I want to mention. So the AI training models and having either 100,000 songs or, I mean, how you decide to train something to deal with audio, there are lots of different ways you can do it. You can use existing libraries, you can make your own, or you can use targeted ones. There was a great presentation at ADC a couple of years ago about the guy who had done the program that would spit out Drake rapping about whatever you wanted. And that's awesome. It's also, if you tried to charge money for it, you'd go to jail, but that's okay. But I wanted to just talk really briefly about what Peter Jackson's crew put together for Get Back, and then also now they've been using it on a lot of the early Beatles remix records, where it's a targeted set, much like, okay, we're going to listen to Drake songs and we'll figure out how to do his voice, but it's even more specific than that. It's, here's a song that has all the instruments mixed together. I want to get the bass by itself. Here are 5 other performances by the same person of the exact same bass part. And I feel like this is something, obviously their compute power is gigantic compared to everyone else on the planet, but this kind of thing in the hands of people who make records would be such a boon. It would be amazing to be able to extract stuff based on the melody and the performance and the tone of the actual instrument, instead of hoping that something like Spectral Layers model is actually something close to what you do in terms of the tones of your instruments. Because when it gets it right, it's unbelievable. And when it gets it wrong, it's hard to even do it manually using the other tools. Moving on very quickly, I don't know if any of you saw that this was announced. It's got to be almost a month ago now. Spike AI, Spike Stent, one of the best mixers in the history of mixing. Unbelievably nice guy. He's done a million records. And so he, along with his son, apparently, have developed a mixing system that uses something to do with Spike, whether it's his mixes or stuff he likes, or he's trained the model himself. I have absolutely no idea. I don't even know if there's a proof of concept build of it yet, but it seems to be further along than just a website. So this was the holy grail for a lot of software companies for a long time, is how can we mix? How can we make that happen? And I'm saying don't, please, because I like to eat and it's the only way I can make money, really. And then the last thing I want to end up on, and this is what I'd like some feedback on. This is sequencer plugins. And you might notice that they're all really, really, really complicated, except for the one on the top left. And that's because I wrote it, but I wrote it in SoundFlow and it's only in JavaScript. And I'd like someone to help me move it over to C++ and Juice so I could have a MIDI plugin. That's it. I think we got to stop. So I'm going to go to GatherTown and hang out on the stage. And I know that everyone else is probably going to go eat. But if you had questions, please come and ask. And then I won't feel like I was talking to an empty room for a really long time. Thanks.
Thank you so much, Andrew. That was wonderful. And as mentioned, if you'd like to ask any questions, please head over to the GatherTown virtual venue if you're registered for the event. Meet Andrew over there. There is a tile that you can step into as the audience. It's on the floor in front of the stage. So as you approach the stage, line up in front of that megaphone icon, you can step in, ask a question, and then everyone in the whole room will be able to hear you ask the question, and Andrew will respond. And when you're done, step aside and let someone else through. Otherwise, we'll see Andrew over in Gather. But if you're also joining us for the GatherTown side of things, we have two meetups starting at 5 o'clock. So those can be found in the Bristol Cityscape area, so just in the area outside of the auditorium room. And that's the Interactive Audio Special Interest Group and the Immersive Audio Network meetup. So they're both occurring at 5 o'clock. Otherwise, on the YouTube stream, in terms of talks, we'll be back at 1740 UTC with Eric Tarr. So we'll be taking a break until then. So please rejoin us at 1740. Thank you. Alrighty, welcome back everybody. So we're about to kick off the third block of talks for today's event. And next up we have Eric Tarr, who is going to be presenting automated analog circuit modeling using C++, Python, MATLAB, and XML. Eric is a pre-recorded session, but I believe he's online to say hi and chat to you in the Discord and possibly the YouTube chat as well. So over to Eric.
Hi everyone, my name's Eric Tarr. I'm coming to you today from Nashville, Tennessee. I appreciate your interest in my presentation. I also want to thank the conference organizers for giving me this opportunity. Today I'm going to be discussing a software toolkit available for audio developers that performs automated analog circuit modeling. When I set out to create this toolkit, I wanted to create something for everyone that made it possible for developers to take advantage of analog modeling in their own audio plugins, apps, or really any C++ software that needs to process audio in real time. This toolkit is called point-to-point modeling. It's intended for audio software development, but we also think there are aspects of it that will be great in education and as a creative tool just in music production, because we've released a plugin that's called the Analog Circuit Factory that's built on top of point-to-point modeling that you can load up and run in real time in any digital audio workstation. So there are several different versions of the library to know about. The primary one is C++, intended for software developers like you who are writing your own plugins and apps. We're also working on compiling this for Linux, so it could be used in the future on embedded processors. Next up, we have the plugin, the Analog Circuit Factory. This plugin is set up to read in very simple XML text files that represent the schematic information of circuits. The plugin will read in these XML files, automatically perform the circuit modeling, and then apply that DSP to whatever signals are running through the plugin in your DAW. We've included an enormous collection of these XML files for you to use. These examples can also be edited and modified if you want to see how that might change the processing in your DAW. You can also write these XML files from scratch for whatever circuits you'd like to be able to test. Next up, we have a Python version. This is intended more for prototyping because it's not going to perform real-time processing. But what we have done with the Python version is giving you some example test scripts that will perform all the common analyses, like looking at the waveform or oscilloscope for a signal running through the circuit, the frequency response, the harmonic distortion, those sorts of things. We've set that up for you straight away to make it easy to put in your own circuits and then be able to figure out how they're going to ultimately perform. Also with the Python version, we made it possible to read in your XML files and automatically output C++ code that you can then copy and paste into your own plugins without having to rewrite anything. Next up, we have the MATLAB version. This is again meant for prototyping. We think that this is a great way in commercial settings to be able to quickly write simple code that you can test and see how a circuit is going to perform. We also think it's going to be useful in educational settings for teaching. All right, what happens if we change this type of component or element of a circuit and see the effect that it has on the processing. Also with MATLAB, you can write your simple MATLAB code and then using a built-in function that we provide, output XML files that you can then load straight away into the Analog Circuit Factory and go from MATLAB prototyping into real-time processing in a plugin with just a click of a button. For the rest of this presentation, what I'm going to do is go through these different versions of the library and show you how quickly and easy it is to get started, but then also the creative potential that you have to open up unlimited possibilities for doing the circuit modeling. So the first thing I'm going to demonstrate for you is actually the Analog Circuit Factory plugin. Here, the XML circuits are loaded up as 500 series rack modules, and you can daisy chain them together right within the plugin. We have the circuits categorized by things like guitar preamps and tone stacks, and hopefully you can see here just the huge collection that's at your disposal to be able to work with. We have a lot of analog EQs that have been modeled if you want to get away from using the same standard digital EQs over and over again. We have lots of guitar pedals that are broken out as well, and saturation, analog saturation sections from diodes, transistors, and tubes. Again, these are all XML files that you can load up. So I want to show you what this looks like. So we have a very simple format for you to use. You can name your own circuits or edit the ones that we have for you there. You can edit the component values for things like resistors and all the capacitors that you'd ever want to lay out. in your circuit. And then we have potentiometers, and so you can specify things like the direction of the knobs that are automatically going to get attached to these potentiometers in the 500 series rack module. And then I'll also show you here with the diode what kind of parameters you have to adjust. If you want to change things like it being a silicon diode or a germanium diode, you can make a matched pair of diodes or a single diode and edit lots of the characteristics of those things. Also to go along with our XML files, we have a PDF of all the circuit schematics, over 100 of the circuits that are included. We have PDFs for, so you can use this as cross-reference to see some examples, how they're laid out, where we number all the nodes and give you component values to help you get started if you wanted to take these and build off of them to build other circuits. Next, we're going to move on from talking about the audio plugin, which we feel is a very powerful tool for experimentation. And we'll switch gears and talk about the C++ version of the library, which is meant really for the implementation of your real-time audio software. With the commercial version of the C++ library, you get access to this Circuit Examples Pro Juicer project that we've prepared. This is meant to serve as a template for your own audio software, whether you're creating a plugin or also an app. What we've done here is set up everything that you need to do to link the library in. So external files to link, and also set up the header search paths. Then we can open this in Xcode. Here is our Circuit Examples audio processor, highest level of the DSP code for our plugin. What we've added in here is just a single class, an instance of one of the circuits that's included in our library. And we'll just generically call it an effect. But if we wanted to change out the circuit to something completely different, we just need to change the name of it right here. So let's go through and check out the circuits that you can find and be able to either modify or use or take and build your own circuits off of these things. So we have our amp clippers, we have our amp tone stacks, our clipping circuits with diodes. These are all the same circuits that you'll find in the plugin that now you have the C++ versions at your disposal to use and modify. Again, we just go back here and we'll say, let's create the Baxendal 1 effect. And that's all it is, to just build the plugin again, and now you have a completely different circuit that you have running inside of the plugin. It's that easy. Let's take a second now to check out, well, what is a circuit actually made up of? At its core, every circuit effect that we're doing is a circuit model. And that's where all the magic and the DSP happens of the automated circuit solving. Circuit model gets a thing called a circuit layout. This is your schematic information. So how many nodes do we have as part of this circuit? What are the individual circuit elements in here? We're going to create vectors of all these things that we want to pass in. Then we have all the familiar callbacks that we would find for processing buffers of audio, whether it's an input and output or an individual buffer processing an individual sample. We've got to prepare it like a plugin with the sample rate and the buffer size. If we have parameters like potentiometers or variable resistors, we have internal smoothing that's already set up that you can control the number of samples for. And then when you want to actually change the values of the parameters, you set them using a vector right here. So this is where really all the action happens for when you're creating your own circuits, what you need to be aware of and what you need to set. So these circuits are then made up of these individual elements, and you can look at the documentation here in the class implementations to find out which circuit elements are available, and also how you can set the different parameters on them. So again, those go into a circuit model. Lastly, we have a circuit processor, which is our abstract base class that serves as the interface into the library. We have circuits that are implementations then of that circuit processor base class. Here, that's what you would use if you're just trying to create one circuit at a time, where you specify the individual layout for it and pass it into its circuit model. And that's how we would then use the individual circuits. But we also have this thing called a circuit chain that also inherits from a circuit processor. And why is this? It's so that we can create a vector of circuit processors. So if you want to create a chain of arbitrary effects, that could be a bunch of individual circuits together, or also a combination of circuits and other circuit chains that you've made before, you can do that and make this very powerful thing. So meant to be very, very modular. So again, if you just want to get started using it, you go in here, you change the name of your circuit, and then we go in here to prepare to play, like you would normally do in a plugin, and you need to prepare our effect with the sample rate and the block size. And then we go down here to our process block, and we go in here to our loop after we've grabbed our channel data, and then we pass that channel data into our effect, and that's all you need to do in order to get started writing code for the C++ version of the library. I'm going to go ahead and build this example plugin now so we can see it. It's a very basic Juice plugin with some few knobs. And so if you have these knobs, potentiometers mapped to parameters in your circuit, then they will update that and you can experiment with changing those things on it. So there you go. That's what you need to do to set up the and get started with the C++ version. We're going to shift gears and talk about MATLAB. The MATLAB version of the point-to-point library is available as a public GitHub repository. So you can use this for prototyping in your own commercial software, or you can use it as an educator and have your students be able to use this as well. They want to learn about how to use circuits and modify them and experiment with them. So if we dig into the repository, at the highest level, we have a number of test scripts that are set up that I'm going to demonstrate for you so you can get an idea just about how easy it is to edit and modify and see the results with different circuits. We have included in MATLAB all the same circuits that you find in C++ and also the Analog Circuit Factory plugin. And so it's just written in MATLAB syntax instead of some other programming language on it. But the same exact structure and architecture to the library is in MATLAB here too. So we have all the files for circuit model and all the different classes for our circuit elements as well. So now let's go back and take a look at the test script and experiment with it. So here I have the Boss blues driver clipping stage that we're going to play around with. I've set this up as going to be the circuit we're going to analyze. Down here we have these simple flags, these booleans that you can set depending on what type of analysis you want to use. So this is code that's already set up to plot the waveform, the frequency response, the harmonics, and that sort of thing. And you can even go in and change the MATLAB code if you want to say, oh, I want to analyze a different frequency or the number of cycles or some amplitude or even a different type of sine wave or square wave. All those things are easy to modify in MATLAB. So all I'll do is just go ahead and run this, and we'll see two plots will eventually come up. That one is going to be the waveform, and then one is going to be the THD or the harmonic analysis of what happens with it. So over here on the left, we have our cool analog distortion that's coming in. Over here on the right, we see our even and odd harmonics that come from sending a test signal through this particular circuit. And then if we wanted to, we could go back in and change some of the components or element values, change our resistors. We could change the type of diodes, and then go back and run our test script again and see in a matter of seconds, what's the result of swapping out these different kinds of components on our circuit. Another cool thing that we've built into the MATLAB library is the ability to take your MATLAB syntax of a circuit and have it spit out an XML file. So I ran the script this time, which called this function, and it created for us this new XML file that wasn't there before. And this XML file has the same exact formatting that we use with the Analog Circuit Factory plugin. So if you want, you can go from MATLAB, click a button, using your MATLAB Boss blues driver, have it create this XML file, and load that XML file up in your Analog Circuit Factory plugin, have it running in a matter of seconds in real time. Also with MATLAB, we have the ability to read an XML file. So if you have experimented with a circuit that you've written in XML, you can load it up into MATLAB and have MATLAB use that as part of your test script analysis. Next thing I'm going to show you is a second parameter test script that we have prepared. This is more for circuits where you have a potentiometer, a variable resistor that you want to adjust and see what happens when we change some of the different settings and plot like the frequency response for different values on it. So here I have this Baxandall EQ where we have a bass knob and a treble knob. And what I want to do now is run a frequency response analysis where I look at, well, what are these different settings going from the minimum setting of the potentiometer all the way up to the maximum. So I have this loop here of the resistor value going from 0 to 1, and I pass that resistor value in, the new one, each time into this before I do the analysis of the circuit, and then I plot the frequency response each time. So for the circuit, the resistor value in here first is for the bass. That goes along with parameter number 1. Parameter number 2 is treble. And so what I've done is I've set the resistor value of the bass is going to change, and the resistor value of the treble stays the same at 0.5, just its original value. So if I run this again and plot it, now we see the plot that shows us as we adjust this knob, we can get these different frequency responses. And so this is another really powerful way to analyze and make sure that your circuit is functioning properly for all the different range of parameters that you want to put in for any of these variable controls. So that's the basics of getting started with the MATLAB version of the library. Now we're going to shift gears and look at Python. So the purpose of the Python version of the library is for prototyping, just like what we were seeing before with MATLAB. But this was one of our highly requested features, was to make it possible to work in Python because a lot of developers prefer to work there. A cool thing about Python is we can utilize Python bindings, which allow us to call actual C++ code from Python and pass data in that way. And so the static version of the C++ library for point-to-point is actually what we're using to process all the data. And that's why you're seeing these .h and .cpp files within this Jupyter notebook. So what I'm going to demonstrate is here utilizing this test script that we've prepared for you to be able to use. This is very similar to what we were seeing before in MATLAB. Here we have these different sections of code though for bringing in specific circuits from different categories, setting up the analyses that we'd like to be able to run, like the waveform, frequency response, THD, and DC sweep. I'm going to assign the circuit here. This is a Baxandall one, but I could swap out that circuit for any of the other ones. And be able to test that. Really the one that's interesting is the frequency response. That shows us that bump down there at low frequencies. And then if we wanted to, we could also look at the total harmonic distortion, which isn't showing any harmonics for this linear circuit, or the DC sweep. So that's a very useful way to be able to go in and analyze specific circuits. We also have this second script that makes it possible for you to modify different parameters for different potentiometers of a circuit. And then we can run this entire script all at once. And what will happen is we'll bring up all four of those plots in one window to see what's happening when we modify parameters. I'm going to switch gears now and show you that with Python, we have this ability to work with XML files. And so if you have an XML file that you have worked on outside of Python, maybe with the Analog Circuit Factory plugin, and then we like to move that over and put it inside of C++, we have this automated script for importing an XML file that when you run it, it will output C++ code and put it in a user circuits.h file that then we could take this code and load it up in our plugin and be able to use it without even having to write any more C++ code. In conclusion, I hope you're able to see, with the point-to-point library, we really set out to try to create the complete software toolkit for you as audio software developers who are interested in having analog circuit modeling in your own products. We want to make it as easy as possible for you to get started by providing an enormous collection of over 100 circuits that you'll find the same ones across the entire suite of software tools. Again, we're also giving you the flexibility to enter your own arbitrary circuits into the library to really harness the power of what it has to offer. For more information, please head over to hackaudio.com. I'd love to connect with you over there if you want to reach out and contact us. Thanks again for your interest in my presentation. I hope to hear from you soon. Take care.
All right, thanks very much to Eric there for a great talk. And so next up, we have Sebastian Cruteau. Sebastian, if you want to turn your camera and microphone on.
Absolutely.
Perfect. Over to you, Sebastian, and off you go.
Thank you very much, Jim. Hello, everyone. My name is Sebastian Cruteau. I'm the CEO of the Monster Factory. A quick presentation. I've been doing voice acting in video games since 2005. Most specifically, monster and creature, people screaming and dying. That is basically what we do. So we are an audio service provider and also talent agency. And we probably work on, since 2005, on 40 plus video game and movie. Some of them probably heard about: Star Wars Outlaws, Baldur's Gate 3, Marvel Guardians of the Galaxy, Warhammers, and a few others. So today we will be talking about creature vocalization. So creature voice acting, the way that I would define it would be the art of bringing believable vocal life to monster and creature by producing natural an organic vocal effect or rough vocal effect, or some people call them, like sometimes myself, extreme vocal effect, because there's different types of vocal effects. Some of them are easy to do, some of them requires literally years of training. So if we want to define a little bit better what is creature voice acting, well, it's not just about the sound effect, and it's more than mimicry of sound, but it starts with mimicry of sound. If someone wants to be a good creature voice actor, trying to imitate the sound, whether it is an insect, an animals, or another metal vocalist or something else like that, usually the way that people go at it is just to try and mimic the sound. But it's not just about that, of course. Vocal techniques and ability to sustain sound matters a little more than acting. Now, usually people in actors or people in voice acting react strongly to that statement until I explain why I'm saying this. For example, if your character is an orc in Lord of the Ring, and you need to speak like this, you need to have this vocal effect, right? If you lose during the recording session the capacity to sustain the vocal effect, you lose the character. So in a sense, the voice technique is intimately tied to the character. So if you lose that capacity, well, no amount of acting skill will save you. Even if you're the best voice actor in the world, if you try to do a voice like this, but the character is like this, it's not going to work well. They're probably going to stop the recording session and schedule another one until you are better and you can redo the vocal effect. It's a world where raw emotion are expressed through sound instead of word. I can tell you, since I started doing creature vocalization, probably 95% of it is unscripted. There's no script, basically because we have to voice all the action. What some people refer to them as grunt, some other people refer to them as emotes, other onos, but that's basically it. There's no script, but we still have to convey emotion for all the different action that needs to be voiced in video game. And if you know a bit about the process of recording those sound in video game, well, you know that sometime we need to do 10, 15, 20, even sometime 40 variation of the same action. So it can become quite a long and difficult process. Nonetheless, it's fun. But yeah, it can be a little bit complex. As in human sound, for example, if you imagine any kind of NPC or human character that someone needs to voice, each action has a specific set of vowel and consonants. Basically, when we have no script, we still have to use vowel and consonant to do all the action that we need to record. So one of the things that we developed in the past, because if you know a little bit about that process, you know that voice talent have to imagine all the variation. This is not something that usually a voice director will come up with and say, hey, here's, the script for the emotes and let's work on that. You have to work, you have to imagine a lot. And at some time, the process becomes a little bit too mental instead of physical. The actor are less in the performance and more in their end trying to come up with all the variation. So this is why over the years we developed a phonetic script to help the actors actually go through all the variation necessary. But yeah, basically we're playing with vowel and consonants most of the time. Timing, context, intent, tone, and subtext are also key element, like in any human NPC, but sometimes they have less impact on the character. For example, if your character is a human in a zombie apocalypse, and he was abandoned by his family when he was young, or his family got killed in front of his eyes, and other events like this, surely this will influence the character, the way also that the voice actor will carry that character. If that character becomes a zombie, I doubt that you will hear a melancholic zombie thinking about his family, right? So all the elements that might have an impact on the narrative of this character will cease to exist if that character becomes a zombie. And for certain type of character, there's not really a background story. When you have to voice a little insect, sometimes there's no story, they just need the sound basically. Sometimes it's a little bit more complex. We have more backstory to it, but most of the time is that there's nothing like that. Improvisational skill. Oh, by the way, I'm French, so if I stumble upon word, like we say in French, pardon my French. I'm also tired. I'm just flying in from LA from GameSamCon. Anyway, so improvisational. Here you go. Got it. Skills, precision, and inventiveness are highly necessary. Like I just explained, basically when we are having to produce sound that are unscripted, and we have to come up even some time with what I call intelligent gibberish, which is basically trying to come up with false language, something that doesn't sound like any language but gives the impression of language. So as you can imagine, we have to be able to improvise a lot when doing that. And it often involves rough vocal effect, and some of those vocal effects are absolutely vocally stressing. As you might know, creature and monster voiced by human beings is a relatively new field in voice acting. When I say relatively, if you know amazing creature voice actor like D. Bradley Baker, Fred Tatasciore, even Steve Bloom voiced a few of them, Miss Tilly, who voiced the clicker in The Last of Us. There's a bunch of people who've been doing that for long. Myself, I've been doing it for 18 years, so it's not new to me, but for a lot of people, it's new for a different reason, because most of the sound that are made for monster and creature are coming from animal sound libraries or software to modify the voice of the actors and the actress, probably one of the most popular being Dehumanizer. So that's usually the go-to. So if you were to look at all the video game produced in 1 year, probably 95% of all monster and creature sound or sound design with animal sound library and other stuff. Another percentage is with Dehumanizer, and probably 0.05% of all the game being made are using actors who actually do the voice of those characters. So one of the challenge to work actually with animal sound library, there's absolutely some advantages, of course, because people have been using that for a long time. Of course, it's cost effective, so project with less budget sometimes rely on those because it's saving them money, because the cost of sound library are sometimes between $200 or $400 US, I assume. Canadian would be cheaper, but yeah, let's say US. Usually they're recorded, the sound recorded are high quality, and it's pretty much user friendly. Most of the time you just drag and drop, and sound designer are really to play with the sound. But there are some disadvantages for if some of you sound designers. Most of the time they're generic action. So let's say that in your project you have 35 action for a creature. Most sound library cover the basic one. So basically maybe sometime between 12 and 15 different action. And of course the sound are not flexible. They're recorded as is. You can play with it after that as a sound designers. And because they've been so used in the last 20 years, they're kind of no longer unique. Of course, depending on the work of the sound designer, but a lot of time, it's not necessarily tailor-made for each project. And of course, one of the main elements, I think, with the sound library is that, and I'm not saying that animals don't have emotion or intent, I'm just saying that taking random sound together, because we never know the context in which those sounds were actually recorded, right? So taking different sound and putting them together and trying to come up with fear, with sadness, with anger, with emotion like that, because sometimes we do need to apply those very human emotion to creature and monster, is hard because it's always the perception of a sound designer. The sound designer will listen to the sound, will say, okay, this is sadness, okay, this is fear, but it's still a perception. If you want real intent and emotion, this is something that needs to come from within, and that is something that needs to come from a performer. So working with performer, you're able to have that emotional depth to the sound that you're actually creating. Working with random sound without knowing the context at when those sounds were recorded, sometimes it's a bit more difficult to arrive at the same result. Regarding what I call vocal stunt performers, and the reason I call what we do vocal stunt work, it's primarily because if you think about a movie, because most of the stuff we do is, you know, screaming and dying and doing zombie wails, doing big voice for demon, doing a character who is dying by fire, stuff like that. So if you think in the movie industry, we have stunt people, right? Stunt people are usually highly trained. Nobody would think to send an untrained actor or an untrained stunt people to do a stunt, because those people train to be able to do what they do. And if you think about voice acting, well, there's some sound that are more dangerous to actors. Like, I've heard hundreds of stories, unfortunately never happened to myself, but I've heard hundreds of stories of voice actor and voice actresses who actually lost their voice during their recording session, and it took some time to actually recuperate from those recording session. So this is why usually when someone is trained and someone can do and can sustain those vocal effects longer than regular actors, for me they are vocal stunt performers. And the problem in the voice acting industry for video game is that we're sending people without formal training in those vocal effects to do the job. For me, vocal stunt work should be done by vocal stunt performers, like the equivalent in movie. Like when we do stunt, we need a stunt professional. That should be the same in voice acting, but unfortunately it's not the case. Of course, there are a few advantages, but also a few disadvantages in working with vocal stunt performers. The advantages is that most of the time it's natural and organic. Sound designer rarely need to have a lot of post-processing afterwards, because the sound themselves already creepy, scary, guttural, clicky, whatever they want. It's most of the time a little bit more original than just animal sound library. It can be tailor-made specifically for different projects. When we record, if you know, again, a bit about the recording process, you know that most of the time the voice director will receive the video animation and will work with the sound engineer to upload all the video animation and all the cutscenes. When you work with animal sound library, you make sure you need to work a lot to make sure that all those sound match all the movement and all the cutscenes. With a human being, it actually accelerates the process, so we can do stuff directly on the video animation and directly on the cutscenes. And overall, it's time saving. Multiple time when I'm talking to video game company, they always think this is kind of a part of the pitch, right? We're going to save you time. It serves to justify my cost or our cost or the cost of a creature voice actor. But I can assure you that 95% of the time we go through the process and they say, yes, it actually saved us time. So the sound designer can actually focus on something else because we are doing the job in a very fast amount of time. In a very short amount of time, I'm sorry. But also there are some disadvantages. As you can imagine, the difference of cost between a creature voice actor and a sound library is kind of huge. It's going to cost way more to hire a vocal stunt performers. Sometimes if they're not trained, you might hire someone who don't have the proper vocal insurance. So it might be problematic because you might have to stop after an hour. Let's say if the recording session is 2 hours. So you can have, unfortunately, bad surprises with that. And there's also risk of injury. So the voice talent can actually hurt themselves and completely stop the recording for a few days. One of the things that I always look, let's say some people here are actually sound designers or voice designers. When you're thinking about a specific type of creature and monsters, there's something that I call vocal archetypes. Basically, it's a sound or a voice design that is associated to a specific kind of creature. So vocal archetype, they can actually evolve through time, and I'm going to give an example to that in a few seconds. So depending on the new video game or the new trend, sometime what was the sound of a monster can actually change. Each monster and creature can have more than one. And again, I'll explain to you with an example right after. One specific voice technique can actually be associated with different kinds of monster and creature. Sometimes all that changes is actually the acting. If you are to record a zombie, a big bloater, you need to go down there like that. It's going to be equivalent to that. But with that voice tone, you can also voice a demon. But of course, you will have words. It's going to change. The acting is not going to be the same, but it's going to be the exact same voice technique. And usually, there's always one, what I call alpha vocal archetype. That is usually the safest bet. So for my example, I'm going to talk about the evolution of zombie voices. If you go back, I'm not going to go back as far as when the zombie were associated with voodoo. I'm going to start with George Romero. So basically, in the 60s, we had A Night of the Living Dead and some other movies until, really in the late 90s. If you did play like me Resident Evil 1 on PlayStation 1 at 2 a.m. in the morning with the light closed, you probably remember those you probably remember those sounds, right? And those sounds were actually the voice for zombie for a very long time. And then came along 28 Days Later and the remake of Dawn of the Dead by Zack Schneider. I know 28 Days Later, it's actually not zombies, they're infected. I'm well aware of the distinction. But this is actually where the zombie and the infected started running. So of course, if you try to apply the same sound on something that is running, probably would have not the same impact, right? And this is where we actually started to hear those kind of sound. So this is where the zombie became much more aggressive. And the funny thing is, if you listen to The Walking Dead nowadays, this is the exact same voice technique, but the zombie, they are slow. So they took the voice technique from the aggressive zombie and they put it on slow zombie, and it works perfectly, right? So this became the new vocal archetype for those characters. And then if you listen to some of the sound of the zombies in Days Gone, you can hear something new. It's actually called aggressive sound, so inhale voice technique. So it's something like ooh, 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 ooh. So this is one sound now that is associated with zombies. And of course, Last of Us, if you listen to the loads of different infected in the game, well, of course, there's the infamous clicker, which is now associated with that kind of character. And some of the bigger zombies, for example, there's one I think it's the Rat King or something like that. So it's really like a big one composed of different corpses of other zombie, and he's really like down there. So that's another vocal archetype for zombie. Of course, the main one being because this is the one that is usually associated with this type of character, but you can see that we can have other voice technique that can fit this type of character. And for me, vocal archetype are important to know for multiple reasons. It connects to audio references of players, of video game players. Still to this date, when people ask me to find a voice talent for an evil witch, their reference is still Wizard of Oz. So that little evil laugh that the green sorceress was actually screaming while she was disintegrating in the water. So a lot of people come to me sometime and they say, hey, we want something new for that creature, or that creature. And the thing is, if you try something new and people expect something else, and because they've been exposed to that type of character for a long time and that type of specific voices, they might find it really weird, and they might stop being immersed in the game. So sometimes it's a good thing to play within their expectation instead of trying something unique. So vocal archetype connect to audio references of player. Sometimes they do provide a more realistic and credible experience. Again, you're tapping into what people are expecting. If you see an orc and the orc is up there, oh, he's up there like this, maybe it's going to work, but people are expecting the Lord of the Ring orc. Meat is back on the menu, boy. That's what they're expecting. So you can always try the other one, but I do believe people will find more believable the second one. And if people are expecting something and you give them something else, they might stop being immersed in the game. And so for me, vocal archetype can actually enhance the overall immersive experience of player. One of the things that we have to do as creature voice talent is basically to make sure that we are up to date to all of those vocal archetype, is basically to listen to movies. As you can see, you're here right behind me. It's my collection of DVD. Yeah, I'm old school like that. I still collect those a lot. And on the other side, I have Blu-ray. And of course, I have Netflix and all the other one to watch other stuff. But that is basically part of the job. Listening to new trends in sound, keeping up with them. And when we get to do those voices, be as much as possible within the confine of those vocal archetype. Just to be sure, Jim, I think I'm done, right?
You are.
All right. I was just checking. I was like, so that's it. So thank you very much. I appreciate the invitation. Thank you for having me. And I'm actually going back to listen to a zombie movie to have more information about their vocal archetype. Thank you.
Thank you so much, Sebastian. That was brilliant. I'm sure everybody really enjoyed that. I certainly did. So I'm going to push you back to the backstage now. Thank you very much indeed.
Thank you.
So next up, we have Powell. Powell, if you'd like to turn on your webcam and microphone. Fantastic. There you are, sir.
Hi.
If you'd like to also start your screen share, and then over to you.
All right. Let me do screen share. Okay.
There we go. We see it. Thank you. Off you go.
Right. Let me start the timer because I want to be in time. Hi. I would like to present you my talk about scalable, efficient processing and analysis of huge, large audio data sets that we have right now, at least not maybe in recording studios, but around the world in specific terms when you create machine learning models. So I'm Pavel Serta. Let's just get to know each other. I'm an applied research scientist working kind of freelance way for some agencies, startups and companies in Spute and audio technology. Previously, I worked in Samsung, R&D, Earcom, RevAI, Bubble Ops, some Tuplux for now these media companies. I was a lecturer in Chopin music for also University of Music for interactive sound and design. Right now lecturing most technical studies about deep learning. And yeah, I'm also kind of artist in a way. I want to present and create my own instruments and learn others how to control and do installations. I was a technical curator for some of them. I do create a workshop since 2009, modeling of sound and Media Lab. I'm also a composer in interactive scene. Here is the generative composition that I've presented throughout the 6 weeks next to the river in Warsaw. It was interactive, so you can put your hands inside, and there are different shapes and objects like sands, like elements that are microphones, and also there are some sensors that know what the positions, and you can indirectly create the sound and also move around, so you control them. It was a more than 80 channel composition. But anyhow, that's on the side of more artistic side. Here I am quite into the technology. I was creating a speech recognition for European languages for Samsung for 6-7 years that were seen in, especially in S7. Also speech to text to speech, also synthesis part right now. So if you want to create such solutions, and also for some kind of audio recognition, like audio event detection or scene where you are, you need to have a lot of data. So you need to go through the high performance computer for large set of nodes, and that's my work. So that's my world inside of the audio world, machine learning in audio. But I want to just present you some challenges and that comes with the huge audio sets that I typically work with, and show you some solutions. This is not one of many, but let me just start and talk about details later on. So let me just guide you throughout the different dangerous waters of machine learning, and in terms of audio and the data inside. And the best thing is that there is this array about other techniques that you can cope with a lot of data, and we have plenty of data, and a lot of data more will come. However, we are kind of struggling to some point, because if you calculate how many data we have right now, probably terabyte of audio on your disk. If you try to record HD video, etc., there are plenty more, but it starts to scale in the terms of world of the published audio. And if you calculate how many of take all like 1 billion people, how much of audio they are creating, it's about a couple of zettabytes. And if you scale that to all like 10 billion people that will be in 2050, it will be more around a yottabyte. And in fact, we are in some terms right now, the whole data, I mean, not all audio, is around 15 zettabyte right now created in the world. Of course, I'm not talking, it's an abstract way of looking at it, but in some way, we want to know what the data is, and the model, of course, they generalize, but they want to create some. They need to create a lot of nuances. So we need to have a picture on that. Anyhow, the limits is the lovely 42, which is also calculated in some physics departments, physics theories. The whole the number stopper is probably 10 to 56, which is universe, whole entropy of the universe. Anyhow, there are multiple data, and for that we have a lot of GPUs, also from crypto. But before that, we just discovered GPUs, and there were talks about GPUs here. Of course, you can have one or more, and with more, you can create models like GPT or other related to audio, like Stable AI model or Suno, that just seen a lot of different things and take that into account for generation or prediction. And if you want to look through the numbers, we are getting crazy amount of scaling, and also the itself, the audio, because many the music is being generalized, like demographic growth. People are having microphones everywhere, and they record. It's not about recording studios sometimes anymore, but you have TikToks. You have, of course, the music is not well prepared. It's not a studio-like music, but it is. So you want to have and you can record next to the river, and then you can have a speech enhancement, audio enhancement, and also vocal enhancements models to somehow extract the best out of it and just keep that recordings. And in order to have the model enhanced, you need to have the bad quality audio to know what is the distortion, at least some of that. And there are plenty of audio bad recordings out there, so we can grab it. And I just wanted to show you the scale it grows and mimics yourself. But anyhow, the implication is that in order to process it, you need to have some large computer to do it. And for that, you don't have one like multi-threading, but and parallelization of the processing. But you need to distribute it throughout the nodes and scale it. And it's kind of not trivial. There are different classes, different departments related to multi-threads, parallel distributed computing, because there are different algorithms for that. You need to capture some kind of taste, how to mangle the data, what are the splits, what is the architecture and way you pass the data because of the memory and networking. So that's really complicated. And however, right now we, because of the machine learning, there are frameworks to go over that. Some are already known because of large computing of physics, of chemistry, of biology, of weather. Some are new because of machine learning, like pure machine learning. For me, myself, I tried to create a model for audio representation, like what's called right now fundamental model, that just seen a lot of data, like streamed a lot of data, not like even save them inside of the disk, but just pass through the data just to know what is the distribution of the just samples and how in a long context, like how they behave, and if you want that, you need to have a lot of data, and then you need to filter the titles. What are the titles of the open to filter the recordings that are open in terms of like Creative Commons. Take what is there and filter out into classify it and prepare for different like buckets to know whether this is recording of music in the wild, this is some studio, because then the training get better if you know the data before. What is the data a little bit, just to mix them while training. But the training itself of the model is not an easy one if you have such a large collection of data. In fact, all current models are trained the way that I'm talking about, like millions of hours. The biggest I've heard is like 15 millions of hours of audio from Google and from Amazon. And for me myself, I pick around 500,000 of recordings throughout like 2 years, and just to gather them, pass them for filtering, and from the bad ones that I don't want to really look into, I got half of them, and then 89,000 of a good quality noise, music, speech related, and around 100,000 hours of only speech. What you do with it, you pseudo label it. I mean, you take different machine learning model. You just run them, the data through them, just to collect a metadata. What is there? It's not perfect, but then you don't have to manually do it, because it was probably not possible to do it anyway. Like 30,000 hours, probably it's doable in some number of people, probably like 10 years of around 5 people, or like couple of hours when you take a whole city. Anyway, I'm trying to with all those data, was using our cloud or nodes in the cloud, most clusters, 100 to 200 nodes to muggle the data itself. And in terms of training, you define the architecture, pick some parameters, know what you want, and basically just run multiple times, look what is working, and set up the perfect parameters that you want to train for more days. And if you look through the data, the most important is that you it's a stopper, because amount of data, and you know that you need to pick those. You need to process data. Some of the experiments shows that it's perfect. You need to do it's very good results. So you probably do it once, and then you can reuse it to different tasks, like classification, when you then have little data and you fine tune the model to this particular task. And so typically, if you take this amount of data, it will be around, just for naive processing, like passing through the data, like quite intensive large node, 32 cores or 64 cores, because of the memory issues through output, which blocks you. It's around 30 days, and that's just passing the data without any touching anything else. And if you want to do more, it just grows. And for example, training on this 200,000 hours of data, not 500, it takes 190 days to do it. Then you can, of course, multiply the nodes and have like cluster of 12 with 8 GPUs, and shrinks down to some number of like 3 days or 4 days of intense computing. Of course, it can cost, but eventually you shrink down the time from 190 days to only for 1 week. You have the data, and then you can look through what is there, work out there, and repeat the experiment. But anyhow, the solutions can be multiple. Like you want to scale it, and I've shown you that just like grouping and renting a lot more compute, not buying them even. Right now, we don't need to kind of buy HPC, large, scientific university scale compute. You can just rent it from different providers. And there are those systems that called Slurm for scientific, Kubernetes, Hadoop, Spark, that are mostly used in business cases. But there is also Ray. It's a system coming from research of Berkeley University, which is one of the best in terms of distributed and parallelized computing. And is well connected to a PyTorch, which is another framework for machine learning computation. And it's a general purpose, a kind of distributed computing. So it's kind of it can run cluster also in locally, kind of even one computer. It's really simulation, but then also in the cloud with a very quick, rapid movement. So you can develop your algorithm on laptop, and then if you are done, test it here with multiple distributed functions on your computer, and then pass it through to the larger cluster and see how it goes, probably, and then debug it on your laptop and pass through. So the perfect thing is that you on pure Python you can use multiprocessing function, and also in Ray there is this Ray utility multiprocessing, which is the same, but it's kind of better. And if you are not using, you should probably. There is also JobLib, and you can mitigate a similar within the Ray itself. It is just a passing of the message passing algorithm and pulling of the workers that do the work itself. But the Ray is kind of three typical systems. One is the Ray core, which is a C++ library that do the basic worker and scheduling, etc. And there are those libraries like for data processing, training, tuning, serving, and reinforcement learning. I will not talk on many things, but about these libraries. But in general, there is this core, and there are like tasks, actors, and objects, and they are interconnected with various systems and libraries, so it's easy to kind of play around, to visualize, train. It's there, very usable, and it's for like around 10 years or 12 years right now being developed. It's open source, but there is a company that governs that, but they earn their money through renting the compute. The company is called Anyscale. But there is a large community that also play with the Ray itself. So as I told you, you can play on your laptop or on a virtual machine, or you can scale it to work it on Kubernetes. It can be within Kubernetes or outside. So it can be as well. I primarily use Ray without Kubernetes because it's similar to Kubernetes, and you just skip the Kubernetes. But some companies have large Kubernetes scale. And for clustering and for nodes, there is this arraylet. There are drivers that governs the machine. There are worker processes, and there is a scheduler that rent. But the most important that the whole system is asynchronous and self-rebuilding. So if the head node is gone, all workers are working until the head node. They try to compute the things. If the head node is up, then it will they will resync things and end the job itself. So I told you the most important here is Raylet and some global control store, which is asynchronous, and it shares the data, but it's not. It's a very delicate detail. I will not mention it. So all those are kind of interchangeable and know which authors are being created and recovered and destroyed. But the node itself is governing. There is no like master who governs everything. The primary component is Raylet. It's made in C++. It's for task scheduling, object management, passing and storing. Most of them, there is zero message data passing until so it's lazy data processing. And there are worker process, so you can write your code not only in Python but also in Java and C++ itself. So it's very good library also for for computing distributed. You can just use Ray Core to do it. Primary, they just share some pointers to a data space. As you use S3, or it's even faster, but also if you are trying to create a network drive, it will also pass some kind of pointers to the inside of the to the space itself. So it will not pass the data itself. The worker will just grab the data. The lifetime is governed by executing the task. Task is one of the things. Objects actors are objects, classes, let's call them, that just have multiple functions and can store a little bit of data. The actors can play with each other, so they can pass the information through one to another. And the work is done by calling like .remote, and also for tasks it's also .remote. It just triggers that. In terms of like prioritization, we can have like pure batch and passing the data like one by one, or some graphs that you define. And in terms of the course and abstractions of those, as I told you, there is a task that are just functions that are stateless. They depend on input-output. Actors are more message passing, kind of abstract. They can receive, they can store some state. And there are other like multi-processing pool of workers and some other prioritization. Objects definitely store only the data itself, and those are based on the research that I talking about, that it even started in 1973. And for actors, here's an example of the code. So you can read the file remotely, then grab that, return that, and it will be there in a cluster. You can pass that data to another function, and it will govern itself how to pass it. Basically, it will communicate. The nodes will communicate with each other depending on which node is computing that, and pass this information through the data store, RPC calls. Anyhow, you can see an example of classes and the task actors. So the primary thing, the call, the trigger is remote, and you just define similar to it's just this decorator at ray.remote or that's at ray that shows that this particular object is within the ray object. So and if you run that within the ray cluster with a framework, it will just read the itself the code and run it in this ray environment. The API is here, so I've shown you. It just passes the. It's just a cyclic graph of the data, and for host, it remotely shares the local state, but it's primarily you can even force the actor to be on one primary node. You can force to have a number of GPUs. You can have multiple actors on one GPU. So we can have, for example, one GPU and set it up that we have five. Five different models that with a graph one by one, it will govern yourself. There is something called workflow, so we can collect the data processing part with a number of functions, and it can bring together and be optimized for processing. I will not go to details. You can read it later on, and also in the documentation. Especially for ray data, it uses this very parallelization memory organization called Apache Arrow, and files that saves that representation into. It's called Parquet, and it's very column wise most often, but it's really efficient in terms of processing. You should look into it, and of course there are already some number of functions to read standard CSVs, Parquet files, also audio files in terms of wave. But also some organisms like Pandas, NumPy, memory management. You can group them in the map, batch, filter, and some aggregation states in order to, for example, read a file, grab a batch, then filter out and group the data in some way by a column, and they, for example, calculate a mean. And all of that is kind of lazy loading, and it's being governed by scheduler, so it maximizes the through output of the whole network. And also, if you use a GPU, it will organize and process and put the data, the exact amount of data. Of course, it's not as optimal as your own kind of kernels and code. But yeah, it's plenty of optimization then, and work almost like I've seen 80 or even 98%, depending of course on processing and functions to use. For data sets, there are some number of way to shuffle the data streaming wise, to load them, to group them while you do the training. There are of course functions to use really easily to scale the training. So you basically import Ray Torch Trainer, which will be a optimized version of layout of the actor that within knows what is the PyTorch Torch Trainer, and you can then run it, and it will be scaled according to your parameters, to number of workers, to GPUs. And there is RayServe to do the inference, to call that, to set up the APIs. You can connect the models in multiple ways, in chains, ensemble trees. You can even connect them dynamically, so switching on depending on some on the conditions. RayServe is just as previously. It's as like Fast API and other. You just write at serve decorator on the class, and goes as it is. It's an actor, in fact, just governs the model, the execution of the model, and the basic. I need to finish up. So I hope you grasp the knowledge how to deal with this large complexity of ML in data sets. And I've shown you kind of like the framework to couple of those tasks and challenges. Yeah, then everything just processes and grows and works, and you have the model. But always remember to take care of your data, because they just grow. Thank you.
All righty. Thank you very much to Powell. So we overran a little bit there, so I think we'll run the poster session that's about to start in Gathertown a little bit longer, just to compensate. So if you're joining us in Gather, if you're registered, please head over there and head to the poster room to check out some of the posters. But otherwise, here on YouTube, if you're watching online, we'll be back at 7:30 UTC for Matthew Yee King. And he's going to be presenting a session on teaching people how to build AI-enhanced audio plugins. So tune back in at 7:30 UTC. Thank you. Alrighty, so up next we have Matthew Yeking, who is going to be speaking on teaching people how to build AI-enhanced audio plugins. So Matthew, if you want to turn your camera and microphone on and start your screen share, and away you go.
Awesome. Thanks very much. Okay, yeah, so hello Bristol. I think I can say that. We're sort of in Bristol virtually, and yeah, it's great to be here. I'm in London right now, actually, and this is what I'm going to be talking about. I'm going to be talking about teaching people how to build AI-enhanced audio plugins. Okay, so my objectives with this talk are the following. So I want to describe the process of writing an audio dev book, in case you're wondering where they come from. So I'm going to talk about that, and then I think I'm going to talk about well, I'm going to demo some of my software that's in the book, but also explain a bit about the sort of thinking behind it. You know, why have I made it like that? What kind of technologies is it aiming to teach, and so on. And then I'm going to present some examples of the actual research that I've done that backs up those examples you see in the book. So why have I ended up making that particular example? Okay, so first question is, who am I? And the answer is, I'm a kind of musician. So you can see a couple of nice pictures of me playing music there, and I've even got a video. Actually, I think I've got a video of that top left one. I'm going to play that now, and there we go. Here's me playing with Alex McLean in our band called Keynote. Right, that's kind of fun. There's a lot of mad audio dev stuff going on there, which we don't really need to get into too much detail of, but I'm playing the drum kit. The drum kit's going into Super Collider. Super Collider's doing a statistical analysis of what I'm playing, and it's generating patterns of tidal cycles language, sending it over OSC to Alex. He's bringing it into his environment and then drinking beer, as far as I can tell in that picture. But anyway, that's all good. So that's the music, and then on the top right there's me and another line up with some more sort of traditional instruments, although the players aren't traditional. Like, you've got John Edwards on the bass, Finn Peters on the sax, who are fantastic players. And then the book at the top, which I'm going to talk about in a minute. And I'm also a researcher, and I also am the program director for the computer science degree at University of London. So I'm a professor at Goldsmiths Department of Computing, and we have this big international degree program that I run, and there I am teaching people how to do reinforcement learning. Okay, so I tried to sort of make sense of why the book is how it is, and this is part of my thought process. So I tried to make a timeline of all the things I've been doing over the years and all the technologies. So on the top is a bunch of releases that I've made, sort of albums and things, and then below that I've got some of the technology I use. So going from my early days working with Amiga trackers, which I still love. I've actually just been working on a new tracker recently, and which you can get on my GitHub page. And then you've got VSTs. I started working in Cubase and didn't really like it, honestly. Great system, great piece of technology, but I like trackers. And then went through Pure Data to Super Collider, and then at the bottom sort of also working with different languages. So I started out writing some Java, which I'll talk about in a sec, and then did a lot of research work actually with Super Collider, using it as a really powerful synth engine as well as a sort of performance tool, and then eventually sort of got into C++ and Juice and all those wonderful things you can do with that, and I'll talk more about why that happened here. So here's my sort of C++ journey. So I started, I guess, about 10 years ago. I taught lots of languages, and I sort of learnt C as an adult. My kind of the language I relearned, if you like, after doing a lot of programming as a kid and then stopping, was C. And then I went into Java and then C++. And the C++ was for teaching open frameworks, and just thought, yeah, this is a great language. I really like C++. I'm not sure I'm writing good C++ in this framework, because it allows me to write anything I want, really, because it's the sort of, a gateway drug from processing through to real C++, I suppose. And then in 2020, I developed a C++ course for the online degree. And I really wanted to teach object-oriented programming, and I really wanted to teach GUI programming. And so I was looking for a cross-platform GUI library. And as it turned out, Juice just was a really good cross-platform GUI library. Of course, we know it better maybe as being an audio library, and of course, so the GUI app we ended up building was this kind of DJing app that you can see in the screenshot there. But still, it just in my spreadsheet where I was comparing and contrasting, Juice just came out because it was just a really good with really good build tools and all that stuff. So yes, that's what I used there. And then later I started sort of mixing in some of the AI work with the Juice environment and tool to course at Politecnico Milano. And this, I've taught this for a couple of years, and this allowed me to develop a lot more of the examples that you'll see in a minute in the book. Okay, so what about writing a book? Okay, so 2022, sort of decided to pitch in for a book. I've been meaning to kind of write a book proposal for a while for a textbook, and so this is how long it took. So 2022 mid, submit the proposal. It goes to reviewers. Reviewers said, yes, go ahead, publish, this is a good idea. And then I also had to do a sort of analysis of other books out there, the sort of competitor analysis to prove that there was like a gap in the market for a book about kind of plugins and AI and audio. And then eventually signed a contract in September 22 saying, yes, of course I'll write 100,000 words in a year. No problem. I've got my sabbatical coming up, 4 months. I'll do it, some of it during that. And then, whoops, the sabbatical was actually in 2024. What a bit of a mistake. Never mind, carried on anyway. Lots of weekends spent writing lots of text. Eventually, only a month or two late, submitted the final text, 344 pages. And then, so basically in total a year and a half after starting the writing, I had the hard copy in my hand. I've got one here. There you go. A year and a half later, you get one of these. So there you go. And so that's the book. Now, how did I go about designing it? So the book these are the sort of some of the constraints I was dealing with. So firstly, that I had a dog that kept trying to write code, which is a bit of an issue, but she's not great coder, but good barker. And then the idea was that I wanted to aim the student at different groups, right? So students, of course, because I teach and I wanted to be able to use it for my teaching, but also for developers who wanted to get into machine learning and or audio programmers, and so different types of people using it. So I've kind of tried to pitch it at different people. Cross-platform, flexible workflow. So I came up with the idea of using CMake, Juice, libtorch, and C++. Obviously, those are my core technologies, and I'll talk more about that workflow in a couple of slides. And then I wanted to also teach a range of DSP and machine learning techniques. So I wanted to kind of pack everything I kind of thought was interesting and new about audio programming and machine learning. I wanted to pack it all into the book. And it started out probably more ambitious with like 6 big example programs that I'd make. But then it turns out that 3 was plenty to fill up the word count. And so I ended up with an amp simulator, guitar amp, sort of nonlinear distortion thing, and then an improviser, a musical improviser, and I'm going to demo these in a minute, and also a thing called a meta controller. Right, so those are the examples, and you can see in the top picture, that's just silly with the dog, and then the bottom picture, that is my sort of 3 computer setup that I used when I was writing the book with a Linux, Mac, and Windows computer there. Okay. So in terms of the build workflow, this is what I came up with. And this has come out from years of walking around labs, looking at people's screens, trying to solve their build problems and knowing what's good and what's not good, and what happens if the project builder for your framework breaks like the night before your new course starts or whatever, which has all happened to me. And so CMake seemed like a really sensible choice because it's really reliable, very widely supported tool which can generate projects for all kinds of IDEs. So it's got a flexibility, but also you can go right down to the command line and just do a build straight on the command line with very simple commands, and that is very good for debugging students' code, right? So if people have got issues, you can just say, okay, let's just forget the IDE because God knows what you've got configured there, and let's just drop down to CMake and just see if we can do a basic build on the command line and then build up from there, and solve the problem as you go. So that's a way of breaking problems down, build problems, which are a really big thing when you're teaching C++, is those really hairy error messages you can get, which really put people off. So yeah, that's one aspect of it. It also, of course, works for IDEs. So my preferred IDE ended up being VS Code because I was developing on those 3 machines you saw in that picture. I could move from machine to machine and have basically the same environment for my builds, and I found it was really great, and had excellent CMake plugin that worked really well, and you could do all the building, testing and running, debugging all in there. And so yeah, with a very simple interface. So I'm not very good at complicated interfaces. IDEs like Visual Studio Community and even Xcode really just overwhelm me. I can't really handle it. I just too many menus, too much stuff going on. So I really like VS Code because it reduces my cognitive load, and I think that's definitely probably true for students as well. Okay, so yeah, talking of cognitive load, the problem with teaching AI, or what we maybe machine learning, let's not argue about which is which for now, but teaching those technologies, and as well as teaching plugins and audio and DSP and how to use an IDE and what a project is, how to use some Python at the same time, and right, you've got a lot of layers going on there. And so my approach was to think of it as maybe making a few different types of cakes with those layers, right? So as you're working through the examples, maybe you start with a command line program that applies convolution to a bunch of numbers, and you can see really just print them out and see exactly what's going on before you get into 44,100 numbers a second, right? Let's just process a few numbers and see what's going on, and then gradually build in the layers until eventually you've really got a clear idea of what that DSP loop is doing, or whatever, or what that machine learning process is doing, and then you build it up into a plugin and start bolting on those extra layers, and then before you know it, you're running it in your DAW, and you've got a great big birthday cake with candles on it. Okay, to really stretch that metaphor there. So what I want to do now is kind of go through some of the examples in the book and tell you what they were inspired by, and what I've done previously leading up to that. So this example is, I'm going to just play it, but it's basically a genetic algorithm powered modular synth programmer. So the idea is that you can explore the space of possible modular synth patches using an interactive genetic algorithm. Now, I first built this thing, I'll just say that before I play it. First built this in the year 2000 as my master's project, basically my master's final project. And I wrote it in Java using Phil Burke's amazing JSON library for Java, which allows you to do real-time audio in Java. And you could even make it work in an applet. So in someone's web browser, you were doing real-time audio, with lots of modules and really quite powerful stuff on, 25 years ago or whatever. So it's pretty cool back in the day. And then in 2015, because there was no way the original program was ever going to run again, I re-implemented the whole thing in Web Audio API, and that's what I'm going to show you here. And you can access this at that website I just showed as well if you want to. So let's just watch this. This is me just clicking through. So each box is a sound, and so I'm listening to the different sounds. I'm selecting one for breeding. Okay. And you've even got the purple ones so the purple ones are ones that other people have created and submitted to the server. And that feature is in the original 2000 version as well. It had some hacky Perl script on the back end that would write a text file out, and then you could bring them in. So yeah, so it had a networked element as well. So yeah, so that's Evo Synth, and it's open source. You can get it. It's on GitHub and everything, or you can just run it. And the great thing is, in 2015, you can even run it on phones. So I had loads of people using it, and I did surveys with it and stuff like that. So that's the idea of exploring the space of sound synthesis possibilities, which I've always been super interested in. Here's another example of some work that was related to that. So this is the sort of sound matching idea, where in this one, I'm looking at how do you match a given sound with a given synthesizer. And the important feature of this that I want to highlight is that at this point I was really interested in doing it with VST, so not just making up my own synthesis engine that nobody's really interested in, or some crazy engine that nobody's ever going to use, but actually using ready-made black box VST plugins and trying to learn how to program those with different techniques. So we did it with genetic algorithms in 2017, did it with neural networks, and we're able to kind of automatically program the DexEd DX7 emulator in the paper for that one. But the problem with this is, unlike the previous one, it's quite difficult for people to access. So yeah, but it still had VSTs in it. So it's like you can kind of see where the angle I'm working towards. Okay, so this is the meta control. This is in the book. And what this does is it allows you to load, it's a plugin that hosts another plugin, which in and of itself is a cool example to learn about. But as well as that, you can then control the plugin that you're hosting using a neural network. So with this single dial that you can see on the GUI there, you can actually move through the space of all of the parameters of the synth in a sort of weird non-linear way, and you can even train it to move in particular ways that you want. So I'll just play some video of that. So that's a preset on the synth, or it's not actually. It's a random place in sound synthesis parameter space, So as I move the dial around, basically it jumps to like a completely different place in the parameter space. So with one dial, it's like a kind of super knob thing, like on the Yamaha things that you get, but instead of it just being a linear mapping, it's a kind of non-linear neural network mapping. And I should also say it's very much inspired by my synth parameter work, but also Rebecca Fiebrink's amazing sort of Wekinator research, which you should check out as well. Okay, next one. So the next demo is the improviser. Okay, so where did that come from? So in this one, this is more from maybe from my music practice, I would say, as well as sort of research as well. But this is the idea that you make an autonomous improvising system. Let's just listen to an autonomous improviser. This is Martin Speak playing with an autonomous improvising system. Okay, that's cool. So, and that was a live broadcast on Radio 3, did it at the Welcome Collection. It looks like I'm like heavily interacting with it, but actually I pressed go and stepped back, and the AI just played this Access virus for me. Why not give it a nice voice, you know? And then also I've worked with Finn Peters a lot, and am at the moment. And you can see him in the top right there, where I was actually programming, live coding an algorithm that would improvise with what he was playing. So that's on YouTube, you can check out as well. And then when I moved into doing this in VST plugins, I was sort of collaborating with a group at Monash, and we worked together to develop it into a Juice-based VST plugin. And the reason I've said spot the difference is the difference between the top and the bottom is, in the bottom one, I'm not there. I don't need to be there, because once you've got it as a VST plugin, people can just install it on their own machine and they can use it, and it's super easy for them to figure out ways of doing it. So you've got Mark Dinverno in the bottom left there, who I've collaborated with for many years. He's doing a talk about ethics and AI and data, and you know, what does it mean to interact with an AI and all that, and improvisation. And then on the bottom right, you've got Carlos Morigo, who I didn't know, but someone gave him the plugin, and we end up really getting on very well and have a good chat. And he built a whole stage show around it, which I just didn't anticipate at all, where he's using it here. So here's Carlos Morigo. So what's the plugin doing? Well, he's got it controlling the lights. He's got it. He figured out he could use an audio to MIDI converter to get the violin sound into the plugin, so and get it to play some synth sounds. So there's all kinds of layers he ended up using it for, in a really creative way. So that was really like inspired me to keep working on these plugins, and because it seemed to have a real impact on people, and when you make interesting sort of research tech available to them. Okay, so this is the second example then. So the improviser, let's do a quick demo of this. Again, this is based around hierarchical Markov models, and it allows people to learn about sort of agency, the idea that the machine has agency, and thinking about ethical data sets because it trains from scratch in real time. And yeah, so there we go. So let's play this one. This is the improviser, and so I'm playing drums into it. So I play drum kit. So yeah, this is a sort of drum solo. Okay, so I'm playing some drums into the improviser, and it's learning. It's now learnt from those drums. It's now playing back out what it's learnt. So this is statistically similar to what I just played in. And then in real time, I can just jump to another section of the drum solo and feed that in instead. So go, okay, how about this? Learn from this now. So, okay, so it's now learning from the more exciting bit of the drum solo. Sorry if that's really loud. There we go. So now it's improvising based on the two things that it's learned, the bit at the beginning and the bit later, and it will just keep going as long as you want. Okay, so that's the improviser plugin. And so that's the second example in the book. Moving on quickly. So the next one, the final example is an amp emulator. And this one is this kind of idea of neural audio processing. Right, so we've done, I guess, you know, symbolic audio, symbolic music control, and we've got sort of synthesizer parameter control. And this one is like, okay, let's just throw some audio through the neural network. And this is very much inspired by great work by Christian Steinmetz, then Damskag writes sort of guitar amp emulators and the Guitar ML project, all that stuff. So that's really cool, but I want to make it teachable. So that's what I did with this example. And also I've got my own work working on, for example, this paper with Louis McCullum, which is sort of network bending, where we were getting DDSP, trained DSP networks, DDSP networks, and plugging oscillators and things into them in the middle of them and trying to freak them out. We called it network bending. So that's that one. And yeah, but I mean, also I end up with a sort of amp emulator rather than something more, crazy and out there, because, there's a lot of guitar players out there. I wanted a more mainstream thing. And also, it's a bit easier to lock it down and go, is this working correctly or not? So it's an opportunity to take more of a deeper dive into the idea of training and validation. And also I could look at performance evaluation. How fast does it run? Could you run it on, for example, an ARM chip? So there's a bunch of stuff. It teaches people how to test the speed of things and all kinds of. So I found it was a really deep dive I could take there. And this ended up being, I ended up writing a mini DSP course on this one to teach people about, fur and ear and wave shaping and all that, and show why neural networks are different from that. So yeah, I got really into this one on the teaching front. And yeah, I guess we can hear a bit of this one. Now I'll apologize in advance because this one actually has me playing the bass guitar on it. So you won't be able to see it, but here we go. A bit of bass guitar. Okay, now we're going to switch the plugin on. Pretty tough. So yeah, I mean, you can hear there's some weird stuff going, artifacts going on. That's all part of the fun, is learning about the training and what happens when little weird things happen on the signal and how do you fix that and all that. So that's the third example, and yeah, that was possibly the longest one. I'm kind of nearly out of time, so I'm just going to flick. I've got one or two more slides. So yeah, just to say, bringing up that theme of what happened, do you have greater impact with your work? Do more artists get hold of your work if you make plugins? And I've done a bit of work. This is preliminary work. The stats are not that strong, but it looks like there's some interesting stuff going on. You can see that on the right-hand side there, plugins appear to get this much higher download rates than other types of projects on GitHub, for example. And it makes sense, right? Because if they get posted on Create Digital Music or Sonic State or whatever, then people are going to go and check them out. Whereas if a weird Python script goes on there, maybe it won't. So that's the thing. And so I think there's definitely a story to tell there about impact and how you can improve the reach of your and longevity of your work as well, which is a bit of an issue in the community of people working on this research side of things. Okay, so just to sort of get to the end here. Here's the book. It's called Build AI Enhanced Audio Plugins with C++, released in 24. And this was my greatest moment, is that we found it in the London Foyles bookshop, and it was nestled a few steps away from Björn Strahlstrop's C++ book, which is a great honour. And then a few steps along, you can't quite see it, but there's the Kernighan Ritchie C book, C programming language book there, which is pretty mind-blowing to end up on a shelf with those guys. I'm sure mine's a bit thinner, so I've got a bit of work to do on the width of the book, but that's okay. So there we go. So there we go. And so let's go back to the objectives. So I wanted to describe the process of writing an audio dev book and the thinking behind that and the sort of pedagogical approach and how I went about doing that, and then show you several examples of audio technology research that fed into the examples as well as the examples themselves. And I will say thanks very much for listening. There's that crazy diagram of my music technology life there for you to gaze at the end, and I'll say thanks very much.
Thank you, Matthew. Amazing. Really great talk. Thank you very much. Right, I'm going to push you back to the backstage. Thank you very much. Okay, so next we have two speakers. We have Adam Wilson and Trey Culver, who are going to talk about making accessible audio software. So just bringing in Trey and Adam now. Okay, over to you, Adam and Trey. Thank you both for joining us. Over to you.
Thanks, Jim. So I'll introduce myself first. I'm Adam Wilson. I'm an audio developer. I've been doing it for about 10 years now. And a few months ago, maybe about 5 months ago, I met Trey via a Bristol-based group called Music Connection, where music producers get to hear their tracks on a big sound system. And then Trey introduced himself as a blind music producer, and he's really interested in helping me make my software accessible. So I really wanted to give Trey a voice to speak to the wider audio developer community. So I'll hand it over to Trey to introduce yourself.
Thank you very much, Adam. Good evening, everyone. My name is Treherne Culver, or Trey if you prefer. I'm a musician and music technologist. I make electronic music under the name of Sound Warrior, and I also run a company called Endeavour Access, which tests music technology products for accessibility and assists music technology companies, both hardware and software, in making their products and programs and projects accessible to disabled people. So thank you very much, everyone, for joining us tonight. I'll hand over to Adam to kick things off.
Thanks, Trey. All right, so really my role here is going to be to ask Trey questions, really, as an audio developer. So my first question, Trey, is what is accessibility?
Okay, so you've heard a lot about accessibility in terms of screen readers, and you've heard a lot about accessibility in terms of inclusivity as a kind of jargonistic thing. So the concept of accessibility as it pertains to music technology development, both hardware and software, is to ensure that as many people with as many varied disabilities as possible have access to your software. And those disabilities could be hearing impairment, visual impairment, a physical impairment. I also have the use of one hand because of cerebral palsy. There are others who have more physically limiting disabilities. So accessibility really means making your software or hardware, if you deal with embedded systems and music tech hardware, accessible to disabled people across the spectrum of disabilities.
Okay, yeah, that's really useful to know, because I think a lot of times accessibility tends to be focused around screen readers, which I guess in your case is possibly the main way you access a computer. But that brings me on to the next question for you. Like, how do you access a computer? Because that's where it starts, really.
I'm going to explain the paradigm to you guys in under 5 minutes, which is entirely possible. So you as developers and as computer users in the modern age, you will move your mouse around the screen and you will click on particular icons, and you will point at those icons, and your eyes will show you what to click on. So as a blind person, I use something called a screen reader, which is a computer program, it can be inbuilt or it can be third party. On Mac OS, it's VoiceOver, and on Windows, there are several good third party alternatives, particularly NVDA, non-visual desktop access. Now, what a screen reader basically does is a system of keyboard shortcuts which you press to do basic things like open a file, load a track in a DAW. In a coding software, it might review your last line of code, for example, and the screen reader will speak what's going on. Now, in order for the screen reader to see those controls have to be made visible to the screen reader, and this is where accessibility comes in.
Cool. Okay. Thanks for that little brief primer. So why is accessibility important?
Okay, so there's a few things here, and there's reasons which I'm going to expound on. So first off, accessibility is important because creativity is important. As developers, you all want your software to reach a wider audience as possible, to make money, but also to see your creations out in the world because they're your babies, because they're your projects. Accessibility will ensure that everybody can use your creations on a level playing field. Accessibility is important to me as a producer because I want to be able to create different types of music. I want to have access to the same things everyone else does. And in the production process, you need to do certain things, for example, sequencing a pattern or slicing up a sample. And accessibility ensures that really, as a blind person, as a disabled person, I can do this the same as everyone else, exactly the same. Now, why is accessibility important as a developer? Another reason is not only to get your products out to more people and to get the software out to more people, but to ensure that those people have a loyal customer base and a loyal fan base. And a developer with accessible software, they will be in good standing not only with other developers, not only with musicians who are disabled, but also in this modern age in terms of things like corporate and social responsibility. Accessibility will put you in very good standing there if you have your products accessible and you engage with the community and the disabled community. Yeah.
Nice. All right. Thanks, Trey. What I'm particularly interested in your particular challenges with regard to working with music software when
Yeah,
you're
right.
when
So
you're
I'm
making
gonna
music.
I'm gonna break it down for you, and I'm gonna take it right back to back to the Stone Age when I began. Just joking. I mean the Stone Age. Sorry, I'm in the dubstep age because I wanted to initially produce dubstep. So what I was finding with a lot of the wavetable synths, for example, is they weren't actually accessible to my screen reader. So a big challenge for me in terms of music production software is making sure that the tools that are used to make electronic music and do complex sound design are accessible to my screen reader, which right now, sadly, a lot of them are not.
Yeah.
And when I say accessible to my screen reader, I don't just mean, oh yeah, open up the synthesizer, browse the presets, give them a little play, give them a little tweak and done. As an electronic musician, as a sound designer in my professional practice, I need to be able to create a sound from scratch. And I need to be able to know, for example, what waveforms an oscillator has, what the filter types are, and also in terms of modulation matrix, what is being modulated by what in the modulation matrix, where can I send the modulation sources, what the destinations are. That's a software synth. So in terms of a software sequencer, music production software, I need to know where I am on the timeline, where I am in relation to other things on the timeline, what position I'm in, what beat am I on, what bar am I on, what position within the beat am I in. These things are all some very common challenges which I've faced. And the biggest challenge which I face right now as a totally blind electronic musician and sound designer is having accessible musical instruments which are in software to make music with. So a lot of musical instruments now, we've reached a stage with accessibility where you can browse the presets, you can tweak the presets, and that's brilliant. But as a sound designer, I can't get much further than that with many instruments, not easily. And we need to be able to overcome that barrier. So I'd say that's my biggest challenge right now.
Yeah. Can you give us an idea of how many like bits of, how many software instruments, for example, you can actually use at the moment?
I am going to say, to my knowledge, a software synthesizer that you can use for ground up sound design that has been specifically designed for this, there's only Surge XT, to my knowledge. Now, what I'm going to say to you is this: there may be blind people out there that may be able to use software synthesizers after playing around with them and getting to grips with them and grappling them and bullying them into doing what they want them to do, but they're not accessible by design, and the developers haven't taken time to make them accessible.
Okay.
And I'm going to be honest with you, I think it's woeful and shameful that out of all the thousands of software synthesizers we have available, only really one has currently been designed for accessibility for blind people in mind.
When you told me that, I was shocked as well. So yeah, that's it. I just wanted other people to hear that from you as well.
And I want to qualify what I'm saying. I mean going beyond the presets.
Yes.
Going beyond the presets.
Going
because there are
deep.
several synthesizers now. If you're blind, you can access the presets and tweak them. That's great. But in terms of sound design, Surge is the main option right now.
And I know that you're a hardware guy as well. So I'm just curious how that compares to the situation with software. Is it like, I'm assuming that with hardware, like you ideally need things where like without a menu or anything, everything's everything's accessible with a knob and a button.
There's
and
two
you just sort of
things
work
here.
it out. Yeah.
There's two things here. So with hardware, you can, using modular synthesis, build yourself a bespoke digital system, which I've done. It could be accessible because it's no menus. So what you need in terms of hardware accessibility, if you are to access menus, either a client-side application which connects to a computer to speak the menus, as is the case with the new Ableton Move, and as is the case with Machina as well, and the Complete Control series from Native Instruments, they will have client-side applications. Or you need onboard the software if the software has onboard the hardware if the hardware has screens, a text-to-speech thing where you turn the knob or move the encoder, and that tells you what the menu options are. The one thing I haven't tested, and the one thing I'm looking to get into testing, is embedded systems in music tech. So if there's any developers out there right now in the audience or coming in the Discord or listening back on the video, whatever, who have embedded systems that want testing, shout me on the Discord, Sound Warrior 20. I'd be more than happy to help you.
All right, thanks, Trey. So, so you mentioned you've got a consultancy helping companies with accessibility. Can
Yes,
you
that's
tell
correct.
us about like some of the companies you've worked with?
Yes, I can. The most notable company I've worked with, and I'll be honest with you, I'm very lucky because I got to achieve my dream at the age of around 30 years old. And I got to make Ableton GmbH accessible, Ableton Live from Ableton GmbH. I got to help make them make version 12 accessible. I'll tell you a little story, Adam, little heart warmer for you, bro. So basically, people often ask as a blind person, what's the one thing as a blind person you wish you could see? And people would give stock answers. So I wish I could drive, or wish I could see the sun or a sunrise. And I'd always say I wish I could use Ableton Live. And
Right.
as a blind person, I got to achieve that dream of using Ableton Live, and I now use Ableton Live every day. I was
It's
part of the
amazing.
I was part of the accessibility efforts. I'd like
Yeah.
to give a shout out to AD Dickens, the rest of the team there. And yeah, I can talk
That's
more about that if you'd like me to expand.
it's amazing. Yeah. So, before that, before you got involved, was Ableton accessible at all, or just
No, no,
not just not at all?
Ableton from a totally blind person's perspective, Ableton was not accessible. So what would happen with me? Because Ableton, they actually have, or they had, I don't know if they still do, but they have a number that you can call. You can actually ring up Ableton in Germany. So periodically, I'd ring them up, I'd email the support, is it going to be accessible in the next version? And they'd always say, we're working on it, not this time, whatever. So what happened to me was I got an inbox email, from a researcher there, who I can actually tell you is who was a UK dubstep producer. We had a very interesting conversation.
Cool.
And the first time they reached out, said, "Do you want to sign an NDA?" I got a bit nervous. I'd never even heard of an NDA before, and I didn't do it. The second time they reached out, I signed the NDA instantly. They got back to me. We began a series of discussions, which ended up with me testing software with a good friend of mine called Chris Pratt. Shout out to Chris Pratt. After iterative testing, it got into the shape that it's in now, and there was a whole community of other blind people that tested it. So shout out to the wider base community of testers as well, who tested Ableton. But that experience really was a very good testing experience. And the great thing about Ableton was and is, and this is what I'm going to say to you as developers, okay? Ableton took a broad range of perspectives and a broad range of workflows and asked loads of people, how do you make music? And from that, they distilled what they did and
Amazing,
distilled it
yeah.
into what you see right now. Now, a mistake that I see a lot of developers make, they'll connect with one disabled person and they'll say, how do you do things? And then they write their software for that person's workflow. And what that means is they're not writing their product to be accessible. There is a difference between workflow accessibility and product accessibility. Product accessibility means looking at your product and saying, what bits of my product do I need to make accessible? But also, if you're looking at your product, you look at one to make it accessible, look at the most edge case that you can, the most complicated case that you can, try to make that accessible. The reason being, the more complicated case you're looking at, the more bits of the software you're going to be able to make accessible at once.
Interesting, yeah. It's kind of like it's a whole different UX paradigm, going from seeing everything together on a screen or having pages and things like that to having to label things and group things together in a logical way so that a screen reader can describe.
Oh, it's a very
screen.
different paradigm, but there are lots of resources out there to help you now, especially with the new Juice versions.
Yes, indeed. One thing I want to get onto, because I know time is short.
Hit me.
Something that I think, one of the things that I think holds a lot of developers back, apart from them thinking, this is a potentially complex thing, and I don't know how, I don't know how to test it properly and things like this. But one of the concerns may be like, what's the market? So the question is like, the question for you, Trey, is what can you tell us about the market?
I'm
The
going to
market
tell you that
for
right now. I'm
the
going to tell you
market
that
for
right now,
accessible
mate.
audio software. Like
Yeah, I'm
how
going to tell
what
you
is
right now.
because it's not visible to us.
No, I'll tell you right now. I'll tell you right now. So, two things. Firstly, the earlier on in the development cycle you tackle accessibility, the easier it's going to be. If you're doing it midway through the development cycle or after the third release, you're going to have a hard time. That's a fact, right? Secondly, I'll tell you about the market now. So there's a lot of people here, and we think of Europe and the Western market as big for software, which it is. And there's a lot of blind musicians in Western Europe and Eastern Europe, in the West, in America, Canada, these kind of things. Markets that are big for accessible software. The global South, Africa, Asia, Indonesia, Thailand, the Philippines, South America. Yeah, I'm gonna tell you something right now. There's a DAW called Reaper. You all would have heard of it. Rapid Audio Production Environment. I use it every day. It's accessible via a thing called OSRA, OSARA. Now, there's a WhatsApp group for blind users, and the amount of people we have in that group and in the mailing list as well from different countries and different around the world is staggering. And what I will say to you is this as developers. If you build your software, make it accessible, then promote that on social media, you will get your hand bitten off by blind people for your software. They love new software to play with, yeah? And they will come, and if it's accessible, they will be your loyalist customer base, and they'll keep coming back, and they'll want to help you on your journey, yeah? So don't be afraid. Don't be afraid to come on social media and say, yeah, I want to make my software accessible. Where's the disabled people at? Because a lot of disabled people have social media, and they'll be more than happy to help.
That's great. Thanks, Trey. Yeah, something you mentioned a bit earlier, and it kind of flipped things around for me. It's like rather than generally, when you're developing a plugin or some audio software, you're thinking about, what's the use case and what's the market and stuff like that. But in this case, what I'm hearing you say is if we make it properly accessible, it's going to be exciting for those people that it will be able to serve, blind
There's
people
two
or
things you
disabled
do.
people.
There's two things you do as a developer. Build it, bellow about it, and they will come. That's it. If you build it accessibly and you shout about that over social media, Reddit is a great place. Yeah. Twitter, it still is a great place. Mastodon, absolutely brilliant. Facebook, brilliant. Yeah. People will come. They will come, believe me.
Okay. You've answered, there was another question, but you've kind of answered there. But the last thing is really like, you've kind of answered this already, but how can we as developers verify that our products are usable by people with disabilities?
Okay, well, I will say it comes down to this. That there's a few things. Reach out to communities on the internet. Do a little Google search, disabled technology forums, disabled music technology. So there's a website called AppleVis that you can use for blind users. But the most simplest
what was that website, please?
AppleVis, applevis.com.
AppleVis, okay.
Yeah. The most simplest way as a developer is to verify your software. You put a call out on social media. I'm developing this bit of software. I want to verify or do some testing sessions with disabled users. I'm looking for disabled users, and then it'll go out, it'll get retweeted, and of course, even non-disabled people in that space, they'll retweet it and they'll give it a boost and they'll love it, and then disabled people will come and they'll say, yeah, I want to make your software, help you make your software accessible. Yeah.
Right. Thank you, Trey. I think that's it. That was my little timer going off to say yeah, that our time's up. Just checking to see if there's no questions come up.
There's actually one more thing I want to say, actually.
Please, we've got another minute.
If you have questions in Discord, feel free to reach out. If you want my email, feel free to approach the organizers and say you want Trey's email, and they'll get back to me and just say, yeah, Trey said it was fine in the talk. And you can have my email, we can connect. But what I will say is, don't be ashamed to ask any questions. No question is too silly. There's no such thing as a silly question. Question made for ask. So go ahead, ask the questions. Let's have a chat. Let's connect.
And another thing, Trey, you're gonna be at the physical conference as well, aren't you, next week?
Yes, I want to say this as well. I am going to be at the physical conference. I'm going to be there with an organization called Sound Without Sight, soundwithout.sight.org, and I'm going to be interviewing different people about accessibility and their careers in the music development space and their software and their new products. So I'm really excited. If you want interviews, get at me on the Discord, Sound Warrior 20, and let's make it happen, guys. Let's promote your software, ladies and gents. Let's promote your software, let's promote accessibility, and let's do it for ADC 2024.
Great stuff. Thanks, Trey. All right, Jim, I think that's us done. Thank you.
Thank you, Adam. Thank you, Trey. That was amazing. We really appreciate it. And look at all those applause coming in.
My pleasure.
Wonderful. All right. Thank you. As mentioned, if you have any questions, please drop them in the Discord for Adam and Trey to follow up there. But otherwise, we thank you very much and look forward to seeing you again soon. Alrighty, so next up we have Jatin Choudhary. I'm just going to bring him in from the backstage now. Hey Jatin, if you're there, can you turn your camera and your webcam on? Oh, sorry, your camera and your microphone, not your camera and your camera. There we go. And if you want to start your screen share, we'll hand over to you and please take us away.
Awesome. Yeah, thanks, Jim, and thanks everyone for tuning in. So yeah, I'm Jatin, and I'm going to be talking a little bit about analog electronics and kind of introducing them to people who are maybe primarily software developers or haven't really worked with analog electronics before. So a little bit about me. I'm an audio signal processing developer based in Seattle. And previously, I studied at the Karma program at Stanford University and worked for a little bit at Tesla. And what I do now is mostly developing plugins using Juice and various other software tools. And so the idea for today's talk is just to kind of introduce some of the basic elements that are used to build analog circuits, and also some of the basic concepts of how people analyze electronic circuits. And this analysis is more or less the same regardless of whether you're building a circuit to have a circuit that works, or whether you're looking at maybe modeling a circuit for a piece of software. And this talk is mostly designed for beginners, people who haven't really worked with electronics very much. But hopefully, if you're someone who has worked with electronics, it's a useful review for you as well. So a circuit is basically just a connection of wires and different circuit components, but we'll go into it a little more deeply. So in the world, we have these things called electric charges, or things that are electrically charged. And when you have two things that are electrically charged, you have an electric force between those two things. And so this is where the common phrase opposites attract come from. So if you have two positive charges or two negative charges, the electric force is going to repel those two things away from each other. But if you have a negative charge and a positive charge, the electric force will attract them together. And so when you have two electric charges, this electric force is what's called a force field, because it is a field that kind of encompasses all of the area around these charges. And it's similar to the gravitational field that we're always a part of, since Earth has a gravitational force associated with it. And so this is where the idea of voltage comes from. So a common analogy here is, again, thinking about gravity and thinking about height. So if you have a ball in your hand and you just drop it, it's not going to fall very far. It's not going to go very fast because you're pretty close to the ground. And so we say that ball doesn't have very much potential energy. But if you go and you climb up to the top of a mountain and you drop the ball from the top of the mountain, it's going to fall a lot further. It's going to go a lot faster. And so at the top of the mountain, the ball has way more potential energy. So if you think about that analogy and you apply it to an electric field instead of a gravitational field, that's basically what we call voltage. So a voltage is kind of that difference in potential energy between two places in an electric field. So now the idea with circuits is that we have wires, and wires have electrons in them, which are negatively charged particles that can move, maybe not freely, but can move fairly easily in wires. And so if you have a wire that has a difference in voltage at each end of the wire, then the electrons are going to move towards whatever has the positive voltage in the wire. And that movement of electrons is called current. And so the idea with an electric circuit is that we want to harness that voltage and that current to do some work. So for example, if you're listening to this on speakers or on headphones, there's some speaker driver that's moving back and forth, and the speaker driver moving back and forth is being driven by changes in current and changes in voltage in some circuit behind the speaker. A lot of biological functions are also electrically driven in similar ways. And of course, for our purposes, we care about audio signals. So if we have the voltage or the current represent some audio signal, then maybe we can process it or manipulate it in some way that sounds interesting. So when we look at circuits on paper, we usually look at them in kind of this drawing form, which is called a schematic. And I'll explain over time what the different things in the schematic mean. But of course, in the real world, circuits look more like this. So this is a guitar pedal that I helped to repair a few months ago. And so the red kind of platforms here are printed circuit boards. And they have kind of, you can think of it as wires built into the circuit boards. And then all of the electrical components are soldered into the circuit board, so they're connected by the traces in the PCB. And we'll talk a little bit more about that towards the end. So the first kind of circuit component that we'll talk about is a voltage source. And in schematics, they're usually drawn something like this. There's a few different variations on them. And so the idea is that a voltage source is just a circuit element that can create a difference in voltage between two nodes in your circuit. And there's different ways it can do this. There's alternating current and direct current, which I'm not going to get too deeply into. But there's many examples of voltage sources that we're very accustomed to. So batteries are voltage sources. The wall outlet where you plug in your vacuum cleaner or whatever, that's a voltage source. And of course, signal generators. So if you have like a synthesizer or something, maybe you have some signal generators in your synthesizer, and those can be used as a voltage source. Probably the most common thing we see in circuits are resistors. And again, in schematics, they're usually drawn in any of these forms. And a resistor is named as such because it resists the flow of current. And so usually what happens is as current tries to flow through the resistor, some energy is lost, right? And typically that's lost in the form of heat, but there's many types of resistors. So you kind of lose energy as current flows through this thing, and that dissipates power. And the fundamental idea that you need to know to analyze what's happening with a resistor is this thing called Ohm's law. And Ohm's law just states that voltage is equal to current times resistance. Now, kind of important bit of terminology. So if two resistors have the same voltage across them, we say those resistors are in parallel. If two resistors have the same current across them, we say that they're in series. So let's jump into a little bit of circuit analysis here. So let's say that we have three resistors, and we'll notice that we have the same current flowing through all three. So we have a current going through the wire here, and after it gets through the resistor R1, it doesn't have anywhere to go, so it's going to go through R2 as well, and then R3 as well. So all three of these resistors are going to have the same current flowing through them. So if we think about Ohm's law, we can say, okay, well, we know that the voltage across the first resistor is just going to be the current times the resistance value. And if we add up all three of the voltages across each of these three resistors, we can again express that using Ohm's law. And if we add them up, we might notice that we can kind of do some algebra to get something that looks very similar to Ohm's law once again. And if we decide to name these R1 plus R2 plus R3 variables something we'll call R equivalent, then we can define an equivalent resistance that is essentially the same as all three of these resistors together. So sometimes you'll have a circuit where you might have two resistors in series, and when you're analyzing that, you can think of them as just a single resistor with the values added together. But what if we have resistors in parallel? So here, we'll notice that we have a voltage drop between node A and node B, and all three resistors are also going from node A to node B. So these are going to have the same voltage across them, but they might have different currents. So again, we can use Ohm's law to figure out what's the current through the first resistor. and we can add up all three currents, and again, use that, express that using Ohm's law. And now again, we can get kind of a variant of Ohm's law with some R equivalent that in some way collapses all three resistors into one. And now the equation that we'll use for R equivalent is a little bit different, but again, there's a way to kind of collapse all three resistors into one just using some manipulation of Ohm's law. So that brings us to our first example circuit, which is what's called a voltage divider. And the idea with a voltage divider is that we have some current going through both R1 and R2. And again, if we do some Ohm's law tricks, we can figure out what the output voltage is as an expression of the input voltage. And we end up with this handy fraction here where we know that the output voltage divided by the input voltage is just a function of the two resistors. So the idea here is that you can take the input voltage and make it some smaller value than what it was before. So you can imagine if R1 and R2 are the same value, then this fraction here just becomes 1/2. And so that basically makes your signal half the voltage as it was before. So this is a common way that people implement, for example, a volume knob in an audio circuit. You start with a, let's say, full-scale signal, and then as you change the values of R1 and R2, you can get some quieter version of that signal. So next we have capacitors. And again, these are widely varied in the way that they're constructed and in the way that they're drawn in circuit schematics, but these are a few examples of how they might look. And so the idea with a capacitor is that you have kind of two plates that can be charged, and the capacitor might store some energy in an electric field that lives between those two plates. Now, some capacitors are also polarized, which means that one plate is kind of designated to hold the positive charges, and the other one is designated to hold the negative charges, but some are non-polarized, and either plate can do either job. And with capacitors, we have a different equation that kind of governs how they work. And this equation states that the voltage across the capacitor is equal to the charge being held by the capacitor divided by the capacitance. Now, there's another way to write this, where we recognize that the charge is equal to the integral of the current. I'm not going to get into calculus here, but that's just a way to look at it. And I'm going to do one more bit of math without much explanation, which is the Laplace transform version of the capacitor equation, where we say that the voltage is equal to the current divided by the capacitance times some variable S. And S is what's called the Laplace variable, and I'm not going to explain it right now, but it's an interesting thing to learn about. So this leads us to our second circuit, which is a low-pass filter. Oh. There we go. And so again, we can use our capacitor and Ohm's law equations to figure out what the current going through capacitor 1 is. And now if we apply our capacitor equation again, we can figure out what the output voltage will be. And this allows us to come up with what they call a transfer function, where we have the voltage out divided by the voltage in terms of this Laplace variable S, and in terms of our component values, the resistance and the capacitance of the resistor and capacitor in our circuit. Now, a common thing to do is to replace this Laplace variable S with j omega, where j is an imaginary number, the square root of -1, and omega represents the frequency of the input signal. And so this allows us to construct a new version of our transfer function, which we can plot using what's called a Bode plot. And so here we see that this is in fact a low-pass filter. The magnitude of the signal coming out is going to be 0 decibels relative to the input in what's called the pass band. And then after this corner frequency or cutoff frequency, the signal is going to be attenuated with some slope, which here is going to be -20 decibels per decade. I wanted to talk a little bit about op amps, but I'm a little short on time here, so I'll go pretty quick through this. But basically, an op amp is a voltage amplifier, and it's usually packaged in the form of an integrated circuit. So this here is an LM741, which is a pretty common op amp. And so typically you would buy it in the form of this little little thing here. It's probably about the size of the nail on your index finger or pinky, depending on how big your hands are. And it's got these pins that correspond to the different input and output terminals of the device. And so an ideal op-amp behaves in a way that follows certain equations. So one of the properties is that it has infinite input impedance, which means there's no current going into the device. And the other property it satisfies is that the positive voltage terminal and the negative voltage terminal will be equal. But real op-amps don't always behave this way. They have things like clipping and a slew rate and input impedance that is not infinite and output impedance as well. And so I have a little bit of math for this non-inverting voltage amplifier that I'm going to go through a little bit too quickly here, but hopefully you can follow. So we're going to say that because our positive terminal and negative terminal need to have the same voltages, we're going to say that the voltage at the negative terminal will be equal to V in. Then we can use Ohm's law to figure out the current going through the resistor RG. Now, because we know that there's infinite input impedance, we know that the current going through RG has to come from the current going through RF. And so that allows us to figure out the output voltage in terms of the voltage across RF. And if we put all of our expressions together here and do a little more Ohm's law stuff, we end up with this expression here for the voltage out divided by the voltage in. And so unlike the voltage divider, which could only attenuate the signal, this circuit can also boost the signal and make it louder, which is obviously very useful for a lot of things in audio and in other domains as well. So just a brief kind of note on where you can go after this. So if you're interested in building circuits, there's a lot more to learn. You might want to build guitar pedals or synthesizers or things like that. I'd recommend buying some breadboards and getting familiar with how they work. I'd definitely recommend learning to solder. I think that's very useful. If you're interested in circuit modeling, then I'd recommend learning about some different modeling paradigms and some different discretization schemes. You probably also are going to want to learn about some equation solving methods like the Newton-Raphson method and so on. Some of the modeling paradigms that are quite popular are nodal analysis and modified nodal analysis, wave digital filters, the Port-Hamiltonian method, and of course there's many more. So yeah, there's a lot of things to learn about beyond what I've talked about here. Hopefully this is an introduction that has invited people to learn more about this topic. So yeah, thanks for listening to the talk, and yeah, I'll be on Discord to answer questions if people have things they want to ask, and hope you enjoy the rest of the presentations today.
Thank you, Jatin. Amazing. Alrighty, so we're now going to our ultimate session of ADCx Gather, and that will be presented by Julius Smith. And so I'm just going to bring Julius in now to say hi. He'll be with us in just a second.
Nice hearing you.
Hey, Julius. There you are. You're here. You're on the stage. Say hi to everybody.
Hello, everyone. Hello from sunny Palo Alto.
Amazing. So you'll be around afterwards if people have any questions. You'll be in Gather, and you'll also be watching the Discord channel, right? And if people have questions during the talk and
absolutely,
perfect.
Yeah, I'm on both now, and I can stick around for an hour after my talk.
Amazing, wonderful. Well, thank you very much. We're going to roll the video right now.
All right, see you then.
Hello, I am Allwin Williams, and I'm going to be talking about playful interfaces.
No, that's not the right video.
Experimental music. A bit about me. My background is in interaction design, and I'm...
Apologies for that. We'll try that one more time. All right, there we go.
Welcome to the talk, scipy.cbp, using AI to port Python's scipy.signal filter-related functions to C++ for use in real time. This was driven by a need to do filter design in an audio plugin. So this is Plugin GUI Magic's equalizer example with some buttons mocked up here to show basically what I'm trying to do. Instead of just, turning these knobs and getting your EQ how you want manually like that, we'd like to add an automatic fit button. And so there are a lot of methods for filter design that'll do that. And once you like what you see, then you can save it out. And so I want to be able to draw whatever you want here, and you also want to be able to load a desired magnitude frequency response that's, maybe measured in the wild, that sort of thing. So to do this, you need the filter design stuff to run in real time. And where is most of our filter design software? Well, it's not in C++, as far as I know. Now, here's a quick lightning review of filter design. Probably the easiest method, the most straightforward method, is frequency sampling. You just draw what you want. It's a magnitude frequency response. And the only thing tricky that a lot of people don't know how to do is to make it minimum phase. Because if you leave it 0 phase, then when you inverse FFT, it will be non-causal. It'll be symmetric about time 0. But if you make it minimum phase, then it'll be causal, and you're also keeping it as compact in time as possible. And then you can take the inverse FFT and get the desired impulse response. And so now you can work in the time domain. And you do have to implement in the time domain. And so that's one of the reasons we want to think in the frequency domain and implement in the time domain. So then it'll be causal, but it'll probably be too long because you just drew something arbitrary. So what you do then is you window it with like the right half of a Han window or something like that. Take it down to the affordable length. And windowing in the time domain is smoothing in the frequency domain. So you're going to get a smoother response. So you should actually forward FFT and make sure it's still okay. It'll be smoother after the windowing. And then, of course, we just use convolution to implement an FIR filter, finite impulse response filter. And this is typical for things like amp cabinets, very, very commonly used. It's even used for reverb nowadays. We can afford it more and more. And so the only problem really with it is that it can be really expensive if you've got a lot of it going on. And in my case, I really do want to minimize the CPU load, and I don't have access to the GPU. So it is valuable to get it down. And so there are recursive methods, and those are things like mfreqz in MATLAB and Octave, but that's not C++. And so AI's all around. Let's try the chatbots to translate something to C++. And they also are good at writing unit tests. I'll show some of that. But the situation for filter design is that there's a lot of stuff in MATLAB, but that's completely proprietary. And it's not even precisely documented. You can say help on the functions and not actually know what they're doing. And some of the stuff is in Octave, but that's GPL, and a lot of people don't want to mess with that because they're making a plugin, and they don't want to give all their source code with the plugin. Now Python's really great, and it's got a great license, but it doesn't have everything, like it doesn't have mfreqz. And so that's something that I can fix, and so I did. I implemented mfreqz from scratch in Python, and that was interesting. I actually pasted the algorithm description from actually my thesis into Claude 3.5 Sonnet and just debugged the result, and it wasn't that much to do. It was pretty straightforward, did really good. I was able to give it the LaTeX source, so I was pretty happy with that. So here's the actual web page, and so I have the LaTeX source for that, and that worked out well. So that was really fast. And then I had to write unit tests, and it really went well. So then here's the first prompt I use. I think this is an interesting thing to point out. And the test program worked out nicely. And so if you go to the fork of SciPy that I have on my website, my GitHub repo, you can see the test programs and run through the unit tests and see how it looks. And so that's the, and here's a link to it. This is mfreqz.py. So this is my test program in my fork where you can check it out. Okay, so I have to tell you this other one. This is a little bit on the side here because this is not in SciPy, but I also needed a spectral tilt filter. I like these EQ filters. You just set the spectral slope, and I have a paper on this. And so this is the abstract from it. And I think this is the heart of the abstract where it really says what it is. And I do try to write abstracts to be as complete and self-contained as possible. You should always do that. A uniform exponential distribution of poles along the negative real axis of the S-plane with the zeros interleaving the poles. Arbitrary spectral slopes are obtained by sliding the array of zeros relative to the array of poles, where each array maintains a periodic spacing on a log scale. It did it, and it did it really well, and it worked the first time. This was Claude 3.5 Sonnet, and I was amazed. And here's the actual paper, if you want to take a look. So this is what a spectral tilt filter, you basically think of it as a Bode filter design like used in classical control. If you know classical control, you know about these Bode stick diagrams for designing filters. And so if you just switch them back and forth fast enough between poles and zeros, you'll get a nice smooth slope that's arbitrary. And it turns out that it's got a closed form representation, exponentially distributed on the negative real axis. So it turns out to be a very simple thing to specify, really. And so figured we should write a paper on that. And actually, you know, there's a good chance that that's in the training data. The whole paper's been online for many years. So, you know, this may not be as amazing as it appears. It may be an example of regurgitation, as they say, where you're actually accessing directly, because I had implementations in MATLAB and in Faust, and so it could have been working from those under the hood. Who knows, right? And so sometimes people ask me why I like to write things in Python. This is not coming from SciPy. Why would I need it in Python? Well, it's because it's a good starting point. You know, the test main block, you can easily use all those NumPy, SciPy, and matplotlib functions to get your displays, look at your poles and zeros, look at your frequency response. It's just good signal processing development environment. But there are other reasons, chatbots have seen a lot of Python, and it's a relatively simple language, so they tend to get it right. C++, I find them tripping, slipping, and sliding all over the place. And chatbots are not good at signal processing yet. Even simple polynomial algebra trips them up, and it's well known that they trip up on plain arithmetic. So they're just not. They didn't go to high school and learn all that. So they didn't work enough problems or whatever. And on low-level signal processing, they tend to get it wrong and give you toy things and just get confused. And I sympathize with some of the errors. A lot of corner fence post errors. Not doing the right thing at the beginning or the end of the loop, and it's fairly reasonable the errors they get. But they're also hard to debug. We don't like to debug that stuff either. So I try to push them to work on well-documented high-level APIs, and Python does that. Who works with samples in Python, right? You've always got some scipy.signal function or something like that, and so it kind of forces the chatbot to think in terms of function calls at a higher level, where the functions are well documented, and so that tends to work out better in my experience to date. And then from a Python function to a C++ function, it's a much more restricted C++ translation. It's like a very straightforward, take this, linear algebra function and implement it in eigen. It will spontaneously think of using eigen to do the algebra stuff, linear algebra stuff. And so that I think is just a smoother path. It's a simpler path, and it's in terms of the best known language, which is a good idea. You want to stay close to the majority of the training data as much as you can, of course, obviously. Okay, so as I said, mfreqz is working, and I have a SciPy fork that's going to become a pull request, and so you can go there now. And feel free to pile in and help me with it if you want, because the thing I have to do now is integrate it into the filters function. So I'm also offering some new features, like a min phase option, which I have to leave false for the default, just to behave like everybody expects it. I don't want to break a lot of scripts that people expect to be able to port over unchanged. But it is a good idea to always set this true, because you really do want to be doing minimum. This is a phase-sensitive equation error minimization. And so you do need minimum phase, and stabilize is a good thing to do, just to make sure the filter is stable. It's not guaranteed by default, so you have to ask for it. And now, in the original FreakZ, there was also an iterative thing added after me that ran Stieglitz-McBride iterations, and in that case, it did do stabilization, but the original was just equation error minimization, and it works best with minimum phase. And if you're going to if you stabilize it, then it's more robust. And so those should both be set true. And the Stieglitz-McBride iterations I've implemented, but I don't like how the gain is floating up. I feel like there's probably a bug there, so I'm going to try to find that. I went ahead and threw in Prony's method because I like it a lot, use it a lot, and the name is mFreakZ. The name is not inverse, it's not equation error filter design. So the name supports any method, right? And all sorts of new methods have been coming under the hood for the iterative case. So why not the non-iterative case as well? So Prony's method, pod A Prony. And then if you look at the documentation for mFreakZ for the iterative case, MATLAB says it uses a recursive Gauss-Newton iteration, which that's a well-known technique. It's probably the most common technique for online system identification. And it's basically Newton's method where you approximate the second derivative matrix with the sum of outer products of the gradient. And that should be upside down. That should be a del, not a delta or grad. Okay, but so that's something. But they don't really tell you what they do, and there's no paper cited. And I did implement this and didn't get exactly the same results. So I'm lukewarm about that. I don't really think I want to even bother with it. But I don't know. I'm still figuring out what I'm going to do. So everything but Stieglitz-McBride and Gauss-Newton are passing their unit tests. And so I have to decide what to do and integrate it. I have to read filterdesign.py and really see how they're doing things. And, you want to conform to exactly how everybody's writing code. And, you just try to, do it the right way and then make a pull request. But right now it's in separate files with my name sort of, underbar JOS at the end. There's the test and then there's the non-test. And so that's where it is. And so, so since Claude uses these scipy.signal functions when it generates Python, we also need those. So these are the ones that I translated using Claude. Claude translated them, and I did a little bit of debugging, and once in a while I had to do some work, but almost always it just worked right off the bat. And it was interesting that for the polynomial roots case, it spontaneously used eigen3, which uses the companion matrix method to find the roots. That was nice. It just worked. And so there's support for transfer function to pull zeros or back, and transfer function to second order sections. And so there's these are just basic conversions between different filter forms. And then bilinear goes from analog to digital. And I really need that actually for the spectral tilt filter, because that designs in the S plane and I need to digitize. So I do the closed form over the S plane negative real axis and then digitize it with bilinear, and that looks good. And then this is your basic frequency scaling thing, low pass to low pass, changes the cutoff frequency. And I'm very careful to ask for unit tests for every single translation. I go one function at a time, and I ask for a progressive series of unit tests. And you really need this. And you'll have to debug the unit test as well as the code sometimes, but you got to know that it's really working. And so you just don't do this without doing unit tests. That's my conclusion. Now, maybe next year that won't be the case, right? Maybe we'll have some self-playing AlphaZero type software engineer that just gets everything right and it knows how to test itself and get it all right. That's probably just a year away. We'll see. And then I'm going to put these in my modules on GitHub, and it's just what I really need. And once that's done, then maybe I'll think about, especially if somebody else wants to help, do a complete, scipy.signal.cpp. The other scipy directory is in good shape. FFTs, we've got lots of those. linalg is covered pretty well by eigen as far as what I've needed. So I'm really just focused on filter design and then more utilities and signal processing that support the Python style stuff. All right, so that's it. So we translated Python to C++ for real-time use, and Claude helped a lot. I mean, it basically did, I would say, 80-something% of the work, and probably accelerated me by, I don't know, pretty close to 10x. Well, I'm going to say at least a solid order of magnitude. Really very, very happy in general. But you do have to get your workflow down and figure out how to make it, you don't want to ask for the wrong thing, right? It's easy to get wrapped around the axle and get screwed up and get into an iteration of translating a big program back and forth, you know, and then a line just disappears for no reason, and you have to debug it, and it gives you back the program with a bunch of stuff elided, and you've got ellipses you have to catch every single time, and you ask for diffs, and the diffs are very buggy. It's not good at just telling you diffs. They're very, very error prone. So, you know, it's just so close to being fantastic. But, you know, if you focus your workflow down, it can be fantastic. You just have to find that tunnel that works and then run with it. So they struggle at the low level, keep them away from the low level. And got some functions done and more to go. I'm kind of in the middle of that whole thing, and so I'm liking Python as an intermediate language, not only because it's so simple and confined on the way to C++ and leverages libraries that are good to leverage, but it also is a test environment where you can, you know, get your usual plots and see all the poles and zeros and analysis that you like to see. So. And infreqz is available now in my Python SciPy fork. Oops, and the subset of SciPy.signal is going to go to GitHub in my modules, but I haven't pushed it yet just because, I don't know, it's just a little bit of a mess, that's all. But if anybody's in a hurry to get it, let me know, and you can translate anything you need pretty fast. You know, the main point is show you that you really can quickly go from Python to C++, and some of the, you know, tips for best results are really the main point of this talk. But also, you know, what's available is available. Okay, that's it. So see you next time.
Thank you, Julius. So now we're going into our closing address from Bobby Lombardi. Take it away, Bobby.
All right, give me a second here as I share my screen. How's everybody doing? Thanks for making it to the end of the day. All right, I hope everyone had a lovely time today. For those of you that were in Gather, I hope you had a chance to explore. There were some lovely community meetups going on. I saw a lot of activity. I saw a lot of people bumping into each other. Remember to hit that G key and ghost yourself so you can walk through objects and people if you have to. I couldn't get out of a room at one point, and I was like, oh my gosh, where's that key? It was all good. I saw dancing. I saw confetti. I saw it all. So that was great. Show of confetti dance, hearts on YouTube. If you liked some of the presentations, did you have some fun today? I hope you did. That was the whole purpose of today, was to show a glimpse of what we do at the Audio Developer Conference. So if you have not been to ADC before, you probably did not know about the Gather, but if you had been to ADC these past couple years, you likely have seen Gather, because we did use the same platform for the conference for the online portion. So the whole purpose of today was to give you a glimpse and get you in for free and kind of check out the Bristol landscape we've created here. Sorry for those on YouTube who didn't register in time, but we'll make sure that you get in there next time, and I'll have the sign up for the subscribe to the newsletter, and we'll make sure you get advance notice and you'll know that it's going on. However, the fun does not stop. So if you did have fun today, just know that this venue does come back in just under 2 weeks on November 11th with even more talks and more of everything. So more of the community meetups, if you saw some of those, more posters. There'll be another quiz event as well, and a really fun open mic, which has a tendency to be an absolute blast. A lot of memorable things. And then we even had an impromptu rave last year, which probably will make a comeback. So ADC, it's going to happen on November 11th to the 13th. I hope you are considering joining us. You can join us in person. There's a few in-person tickets left. There's quite a few online tickets left as well. That's where I hope you will join us. And why should you join us? Well, think of what you saw today and now imagine it as a 3-day event. And today's programming was really in this sort of ADCX programming style, where you see very short 18-minute talks, very rapid fire. The idea is to get, the creative energy flowing and have you thinking about a lot of different topics. That way, as you're bumping into people and networking and Gather, you're talking about what excited you, whether it was in a poster session, an 18-minute talk, a community meetup. The whole goal here is to get people networking and speaking. And for those of you on YouTube, I hope you did take some of that away from you. And please get involved by following us on our social channels or getting on the newsletter. There's so many different ways to get involved. But going back to why attend ADC 24. So it's that 3-day event. The first day is in that ADCX style 18-minute talks, as running alongside of our workshops. So we do have 8 workshops happening on day 1. 6 of the 8 of those are actually streamed to our online community as well. So that's a change from previous years where we've streamed, say, 2 workshops. So this time you've got 6 workshops streaming. So much more to do in the workshop space. Or you may may want to listen to the stream of the 18-minute talks instead, or bounce in and out. The second 2 days are normal programming, not ADCX style programming. Those are 50-minute talks, and those 50-minute talks are happening across four completely different tracks, all of which have been scheduled to have beginner level talks, intermediate talks, advanced talks. Those are all clearly labeled in the schedule, so you can make yourself a schedule based on your interests and kind of difficulty level you want to experience for that day. So yeah, 3 days of that, 75 talks pretty much all together, and workshops as well. What's new that you did not see today, we had the sponsor exhibit hall was closed during this ADCX event. It will be open for the 3 days of ADC 24. Think of it as a similar experience to those of you that were in Gather when you went into that poster session. Imagine now a full exhibit hall of our sponsors there with a bunch of self-service items, but also representatives of the companies speaking to people. And it is indeed a big recruiting event. There will be lots of job posts there, and there'll be recruiters on staff to meet you if you happen to be looking for a job. Poster sessions will return, and then there'll be a new thing called installations for the in-person event. We will have several student installations in place, thanks to Chris Nash. And I'm really looking forward to see what those look like, because I think that'll be fun. And then more going on in the social event space too. So please consider it. How do you find out more of what's going on there? You just go over to audio.dev. All the information's there, from information on registration, ticketing, and the schedule. So you could be able to see, just like you saw today with the ADCX schedule, you'll see that full schedule for the 3 days, the workshop titles, the 75 talks. It's all in there. I would be remiss not to spend a little time talking about how we were able to pull this off today. So the reason why we're here and who made it possible, it's our sponsors. So our sponsors contribute to keeping this going. ADC 24 is run as a not-for-profit event, so any money made goes directly into the event itself. It also goes into paying some of the staff that are contractors. As you can imagine, there's a large video staff needed, not only to pull off today's event with the streaming of the speakers, but imagine next week when we have 4 tracks going on, 75 talks, those workshops. That's a big ask. So I wanted to say a personal thank you from me and the ADC team to Jim Roper, who you've been hearing today as your MC, who represents Digital Medium. Behind the curtain, you have Jonathan Roper. Both of them have been working tirelessly for several weeks, if not months, and then absolutely round the clock today to make this happen. So thank you so much. This was absolutely an amazing event. Also want to say thank you to the ADC team who is listening. They've been a joy to work with, and they have also made this possible in so many different ways, from the graphics that you see to the management of the speakers. I hope you can all come in person one day to the Audio Developer Conference and meet this wonderful team in person. They are just fabulous. So thank you, sponsors. It does not happen without you. I also want to mention briefly the Celebrating Diversity sponsors. So each year we do have a diversity scholarship. So if you are interested in that, we have an application process that opens about 4 months before the event each year. And these companies sponsor basically your ticket to ADC. They pay for that full in-person ticket. And in this year, in the case of Acoustics, they have also covered hotel rooms, which is a first for us. So that is just incredibly generous on their part. And we're so happy about that. So thank you, sponsors. How do we learn more? How do we just stay in touch? The best way to do it is just go over to audio.dev, click on that subscribe button. We don't spam you constantly. We really try to only send newsletters every now and then to kind of let you know what the events are. We won't spam you with goods to buy, none of that. It really is about what's going on and the great things happening with the Audio Developer Conference. You'll also hear about things like the mentorship program that we talked about this morning with Derek had presented that. If you weren't awake that early on the US time, Derek presented this lovely mentorship program that we have with over 100 mentors, a couple hundred mentees. It resets every year. So if that's something you're interested in, whether you want to become a mentor or a mentee, sign up for the newsletter because you will see that we do a call for mentors and a call for mentees. Let's see. This would be great. If you had a good time today, if you took screenshots, if you were telling other people about it, how about please sharing it with the audio developer community? We've got several social sites. They're on the bottom of this slide here. All of the properties are under Audio DevCon. Please share your experiences today. We'd love to hear from you. We'd love to hear what you think. We'd like to do this again, and we'd also like to improve. So you could send something to info@audio.dev, which is also on the audio.dev website if you want to give us feedback. But please share your experiences. And if you took any screenshots today, please share those as well. We, of course, would love to take a look at those and share those with the community. So what's up next? What are we doing? It's not over yet. If you're still here, you may have seen, if you're in the Gather space, I will hand this over to Jim because I don't know exactly. I don't believe the YouTube audience will be taking part in this. It will be just for the Gather folks. But if you're in Gather, you're going to make your way down to the docks, and you may have seen the chuck. You're going to board the chuck, and you're going to descend down into the chuck where we will be waiting for you. And I will be tending bar, as you can see down in that corner. So if you have a non-alcoholic or alcoholic beverage, please raise it and let me see it in your video screens as we are playing the quiz. I hope you had fun. Thank you for joining us. It was wonderful. I got to meet so many people during the breaks and walking around. The speakers were tremendous. Thank you, speakers. Some of these talks, I did not, it wasn't the content I thought it would be. The creature sounds was absolutely terrifying. I now I always thought those like zombie sounds must have been created by some processor. I don't know if I can get some of those sounds out of my head now, but it's a great thing. Thank you, speakers. This happens because you participate. And thank you, everyone who attended. So have fun. Let's keep socializing. Let's meet each other. And I'm going to hand it back over to Jim.
Thank you. Thank you very much. Thank you, everyone. Great message to do this. And yes, there's Jonathan here. Jim's is just setting up the quiz. Thank you very much, everyone. Thank you to the ADC team. And yes, I think we'll leave it there. Thank you, everyone.